All right, welcome back. Welcome to the DeFi section of this course. If we scroll all the way down here, Foundry DeFi, we can see the code that we're going to work with for this course. Now, I gotta say ahead of time, DeFi is an absolutely massive topic. Quite frankly, that deserves an entire video of itself. So we're just going to give you a brief rundown of what DeFi is, what you can do with it, and some of the most popular apps out there. So first, to get started, we can use this site called DeFi Llama to get a snapshot of what's going on in the DeFi world right now. The total value locked in DeFi, some of the dominant apps, and what the dominant protocols are doing. For me, we can look at some of these top 5 for now too. Lido is a liquid staking platform, which I'm not going to go into right now. MakerDAO is a CDP, or a collateralized debt position protocol for making stablecoins, which is what we're going to be building. Aave is a borrowing and lending protocol, like an open source decentralized bank. Curve Finance is a decentralized exchange, more specifically for working with these stablecoins. And then Uniswap is a general purpose exchange for swapping tokens and different types of assets. To me, if you understand some of these top ones, as you go down the list, you can get more and more intricate or more specific different types of DeFi protocols. The beauty of DeFi and decentralized finance is that you get access to sophisticated financial products and instruments in a decentralized context. If you're not super familiar with financial terminology, some of this might be a little bit difficult to grasp, but it is a phenomenal rabbit hole to go down, and it is an absolute ton of fun. There's so many cool things you can do in DeFi, and in my mind, DeFi is one of, if not the most interesting and most important industries and applications that smart contracts enable. So I highly recommend you get used to some DeFi. Some great places to learn about DeFi are going to be places like Bankless, which has a podcast that I listen to. Again, like I said, MetaMask Learn, to learn more specifically about wallets and safety about wallets, and honestly, so many more. Most concepts that you've learned in Web 2 or traditional finance translate over to DeFi really well. One of my favorite things to tell people to do is to try out Aave and Uniswap to really see how some of these protocols work. So if we scroll down here, we can go to the website. Same thing with this one. We'll scroll down. We can go to the website here. In Aave, we can even launch the app, and we can see what this app even looks like. Let's go ahead, connect our wallet here. I am going to switch to, I'm going to check my chain that I'm on. We're on Sepolia testnet. If you look up at the top, one thing that's really cool is you can see this little IPFS thing here. This little IPFS thing only happens with Brave, but it means that this site is also hosted on IPFS, right? Web3, all about decentrality. But if we scroll down, we can see we can supply different assets and get an interest rate on those assets if we supply them. For example, if we were to supply USDC, which is a United States dollar peg stablecoin, we'd get 2.45% interest, similar exactly to how a bank account works. The reason that we get this interest is because there are other people who are borrowing these assets, again, similar to a bank, and they get charged an interest rate for borrowing these assets. So if you supply assets, you get given an interest rate. And if you borrow assets, you have to pay some interest rate. This is why this protocol is so cool. It's permissionless banking, permissionless borrowing and lending of assets. Uniswap is another really cool application where you can very easily swap tokens between each other. For example, if I were to switch to Ethereum mainnet, I could choose something like ETH and swap to an asset, the Aave governance token. And it's a permissionless, decentralized exchange and really enables access to financial markets in a much more transparent, more accountable, and fair way. And I just get absolutely excited about working with these. For those of you looking to get started here, I definitely recommend trying to use some of these on testnets. Unfortunately, not all of these work on testnets, but I have a couple of videos that shows actually working with some of these that we can go ahead and actually watch, such as leverage trading in DeFi, become a DeFi quant, Flash loans with Aave, which is an advanced DeFi tool, and a couple of more. And when working with these, I don't recommend doing this on the Ethereum main chain. I would recommend doing something like Polygon, Optimism, or Arbitrum, where it's going to be a lot cheaper to make transactions. Ethereum fees right now are too high, and that's why we have scaling with layer 2s like Arbitrum and Optimism. One other thing that I should absolutely mention now that we're getting into DeFi is that there's this topic that we're not going to have time to go over called MEV. MEV, or minor extractable value, or maximal extractable value, depending on who you ask, is something that plagues the DeFi industry. It's something that a lot of ETH core devs and protocols like Flashbots are working on right now. Basically, the concept is if you are the validator who gets to order the transactions in a block, you can order those transactions in such a way that benefit you. There are a lot of different protocols working on mitigating MEV and preventing MEV in the future, or making it more fair. And there's all types of opinions on MEV. I 100% recommend that if you're looking to go more into really deep MEV, more into really deep DeFi stuff, you check out this flashbots.net new to MEV repo and check out some of these videos and blogs. They are absolutely astonishing to read. They're a ton of fun to read and also show a terrifying side to the Ethereum world as well. But in any case, the project that we're going to be building in this course is going to be a stablecoin. Now, the concept of stablecoins is a bit of an advanced topic, believe it or not. Maybe you've heard some stuff about it, maybe you haven't. In any case, we're going to watch a video that I made previously about stablecoins and what they really are and what a lot of mainstream media actually gets wrong about them. And by doing this, we as developers are going to have a much better understanding of what these stablecoins really are and how they actually work under the hood. This is going to be a tough lesson. I'm going to say this straight up. It's going to be very difficult. There's a lot going on here. I want you to be absolutely sure to go to ChatGPT and ask ChatGPT questions. Absolutely, in the GitHub repo associated with this course, be sure to use this discussion tab and ask a lot of questions. In fact, if you want, you can even browse around the MakerDAO forum, which is the protocol behind the DAI token, which is what our project that we're going to build is very roughly based off of, and kind of read what people in the industry are actually working with and actually doing. Like I said, there is a lot to DeFi. And this project that we're making, I'm actually planning on getting audited after we release this course. And this is easily going to be our most advanced project in the course, hands down. Even though we have a couple lessons after this, upgrades, governance, and introduction to security, this Foundry stablecoin project is the most advanced product we're working with, hands down. If you're able to go through this and understand everything in this lesson, you should be incredibly proud of yourself and incredibly excited to move forward, because this is a hard project and that's okay. Take your time, don't overburden yourself. There's a lot to go through here. If you've never understood DeFi, take some time and look into DeFi. If we go to Google, we look up like learn DeFi, we get a Cointelegraph article, get some Medium articles, maybe even Udemy, Coinbase. Coinbase actually has a great article on this. There's a lot of places to learn about DeFi. So yes, I do recommend, if you're completely unfamiliar with DeFi, pause the video now, take at least 15, 20 minutes just to do some Google searching around, right? Any knowledge that primes you for this next section is great. And there's really just so much to DeFi. The main thing is that DeFi is permissionless, open source finance. And to me, it is the absolute best thing about smart contracts. With DeFi, we can actually move away from financial institutions and products that have no transparency, that don't help you, that have centralization risk. And the last 20 years have been a history lesson on why we need DeFi to take over the world. So definitely want you to do a little bit of research here. So let's do a walk through the code, and then let's walk through this video on what stablecoins actually are. So here's our code base. If we go into SRC, we see two main files. We have decentralized stablecoin.sol. And if we look into here, it's a real minimalistic, very basic-ish ERC20. We've got some more interesting, more advanced imports, such as ERC20 burnable and ownable. But here, it looks real similar to an ERC20, right? We've got a constructor with ERC20. We have a burn function where we can actually burn tokens, remove tokens, and we have a mint function where we can mint and print new tokens. But the main contract is this DSC engine.sol. So this decentralized stablecoin is controlled by this DSC engine. And this has a ton of stuff in here. Some of the main functionality in here is going to be where we deposit collateral and mint DSC. So this stablecoin is going to work because it's going to be backed by collaterals that have monetary value. We'll talk about more about that in a minute. You can redeem your collateral, remove your collateral. Look at all this NAT spec, by the way. Look at all these comments. We can burn DSC. We can burn our decentralized stablecoin. People can get liquidated. What the heck is liquidation? We'll talk about that later. They can mint DSC if they have enough collateral, and we'll talk about collateral soon, deposit collateral, redeem collateral, etc. But there's a whole bunch of collateral stuff, and we'll explain that in a little bit. We have this test folder where we have our unit tests, where we go over engine, where we test the engine, the stablecoin, and also this Oracle lib thing. We have mocks, which we know what mocks are, and then we have this thing that we kind of briefly went over, which is fuzz tests. And we have this invariant thing that, what is this invariant thing? And we have this new type of invariant underscore tests, which we're going to go over and we're going to explain. These invariant tests, in my mind, separate mediocre Solidity developers from incredibly powerful, incredibly advanced Solidity developers. We've got our scripts as well, real minimal here. We mainly just deploy the stablecoin. We're going to be using Chainlink price feeds to measure the price of the underlying collateral. Again, we'll talk about that soon. But this is really the high level walkthrough, and you can find all the code and all the information you need on this repo. Like I said, this is going to be an advanced section. Take your time with it. Be sure to ask questions. Use all the tools you have at your disposal to code along and understand what we're doing. But the other reason why I wanted to make a stablecoin here is because I strongly believe stablecoins are going to be one of the most important DeFi primitives or DeFi products that Web3 has to offer. And in my opinion, right now, the current solutions aren't good enough. So hopefully this inspires some of you to go out and build a better one. But let's go ahead. Let's go into this video. Let's learn about stablecoins and take your time learning this. All right, let's watch this video. When you research stablecoins today, you get a lot of misleading information. And that's what we're here to clarify today. In this video, we're going to teach you everything you need to know about stablecoins. But actually, what are stablecoins, why we care, categories and properties, designs of top stablecoins, and then the real reason behind what they do, what stablecoins really do. This video is for both everybody technical and non-technical. And we're going to correct a lot of the misleading information out there. There's going to be a lot of information here for people less familiar with DeFi. So as always, don't be discouraged if something doesn't make sense the first time you hear it. Buckle up. Buckle up, dum-dum. We're in for a volatile ride about stability. A stablecoin is a non-volatile crypto asset. That's it. Fleshed out, we could rephrase it to a stablecoin is a crypto asset whose buying power fluctuates very little relative to the rest of the market. And this is the first place where we disagree with traditional media. If you Google, what is a stablecoin, you'll see something like this response everywhere. Stablecoins are cryptocurrencies, the value of which is pegged or tied to that of another currency, commodity, or financial instrument. And to that, I disagree. I think that's an easy initial way to understand them, but not the whole story. A stablecoin is a crypto asset whose buying power stays relatively stable. A good example of buying power would be an apple market. If you went to a market to buy apples with Bitcoin 6 months ago, the number of apples you could buy would be drastically different than the number of apples you could buy today. That's an example of buying power changing and not being very stable. However, someone buying apples with dollars would probably be able to buy the same amount of apples 6 months ago to now. That's an example of buying power staying relatively the same. Since we could buy the same amount of apples today than 6 months ago, a dollar would be considered a more stable asset, whereas Bitcoin would be much less stable. This is what we mean by buying power. An asset whose price fluctuates rapidly all the time is a poor example of stable buying power. Oh, it went to zero! Yeah! This, for example, would not be a stable asset. Now, a stable crypto asset is just a stable asset that's a cryptocurrency. Most cryptocurrencies, by nature, aren't stable, but we will give examples of stablecoins. So summary here, a stablecoin is a crypto asset whose buying power stays relatively the same. And if that's all you take from this video, perfect, great. Let's keep going. Now, why do we care about stablecoins? Because money is important. But not like, oh, I love money type of important. In everyday society, we need some type of low volatility, aka stable currency to fulfill the 3 functions of money. And for Web3, we need a crypto version of this. The 3 functions of money are storage of value, unit of account, and medium of exchange. Storage of value is a way for us to keep the value and wealth we've generated. Putting dollars in your bank account or buying stocks / cryptocurrencies is a good example of storing your value. Apples would make for a poor storage of value since they would rot over time and lose their value. Unit of account is a way to measure how valuable something is. When you go shopping, you see prices being listed in terms of dollars. This is an example of the dollar being used as a unit of account. Pricing something in Bitcoin would be a poor unit of account, since the prices would change all the time. Medium of exchange is an agreed upon method to transact with each other. Buying groceries with dollars is a good example of using dollars as a medium of exchange. Buying groceries with car tires would make for a poor medium of exchange, since car tires are hard to transact with. In order for our everyday lives to be efficient, we need money to do all these three things. And like I said, in Web3, we need a Web3 money. We need to be able to know the value of stuff in Web3, to be able to pay for things without prices going crazy, and we need to be able to store our wealth in Web3. In a decentralized world, we need a decentralized money. Assets like Ethereum work great as a storage of value and medium of exchange, but fall a little bit on their unit of account due to their buying power volatility. However, maybe in the future, as Ethereum becomes more adopted, it'll become stable and we won't even need stablecoins. But right now it's a little too volatile. And yet, I'll still tell you it's ultrasound money, since I do think it's an amazing store of value, but that's a conversation for another time. Bankless, don't kill me. I'd love your content. Also, if you're here, be sure to like and subscribe because we're just cooking the fire up and we are about to pop off. Anyways, okay, so now we know what a stablecoin is, why we care. Let's talk about the different categories of stablecoins. And here is the second place I strongly disagree with traditional media. If you search for types of stablecoins, you'll get something that pulls them into categories like this: fiat collateralized, crypto collateralized, commodity collateralized, and then algorithmic. Now, this isn't too bad of a categorization. It does make it easier for new people to understand, but I think it paints an inaccurate picture. So let's categorize stablecoins. But actually, the categorizations that I like are relative stability, stability method, and collateral type. So what are these categorizations? Let's start with relative stability. When we talk about stability, something is stable only relative to something else. The most popular type of stablecoins is pegging or anchored stablecoins. And these are stablecoins that are pegged or anchored to another asset, like the US dollar. Tether, DAI, and USDC are all examples of US dollar pegged stablecoins. They follow the narrative of one of these coins equals $1. And that's how they stay stable. It's stable because they track the price of another asset that we think is stable. And most of these stablecoins have some type of mechanism to make them almost interchangeable with their pegged asset. For example, USDC says that for every USDC token printed or minted, there is a dollar or a bunch of assets that equal $1 in some bank account somewhere. So the way it keeps its value is that at any time, you should be able to swap your USDC for the dollar, or at least hypothetically so. Something like DAI, on the other hand, uses a permissionless over-collateralization to maintain its peg, but we'll get to understanding that a little later. However, a stablecoin doesn't have to be pegged to another asset. It can be floating. Remember, to be considered a stablecoin, its buying power just has to stay relatively the same over time. So a floating stablecoin is floating because its buying power stays the same and it's not tied down to any other asset. With this mechanism, you could hypothetically have a stablecoin that's even more stable than an anchored or pegged stablecoin. Let's look at an example. Let's say I can buy 10 apples for $10 today, but in 5 years, I can only buy 5 apples with $10. So it would cost me $20 to buy 10 apples. This isn't an unheard of phenomenon to happen, and is commonly just referred to as inflation. Now let's introduce a stablecoin whose buying power floats up and down with the market. For now, let's just pretend it does so magically, and let's call it Applecoin. Today, you can buy 10 apples with 10 Apple coins, and in 10 years, you can also buy 10 apples with 10 Apple coins. Which one of these assets would you say is more stable? Yes, the Apple coin's buying power stayed the same over the 5-year period. So we'd say it's a more stable asset, even though it's not pegged to something like $1. And yes, stablecoins like this do exist, and they use a lot of clever algorithms to do this. One such example is the Rye stablecoin by Reflexor Labs. How Rye works might be its own video, but we've left some links in the description for you if you want to learn more about how it works. Because this concept can be a little hard to grasp, to further explain it, let's go through another analogy. Let's look at the anchor and the buoy in this image. Which of these do you think is more stable? The anchor or the buoy? Well, it depends on what you're comparing them to. Compared to sea level, the buoy is more stable, since it'll always be at sea level. As the water level rises and falls, the distance between the anchor and the sea level is constantly changing. The buoy is an example of a floating stablecoin. Now, if we compare these two to the ocean floor though, the anchor is more stable of the two, since it'll always be right on the ocean floor. This is analogous to a pegged/anchored stablecoin. Now, if we're going to be really serious with this analogy, then the question might be, well, what happens when a storm comes, or what happens when the water's crazy or the tide's crazy or something? And to that, I'd say you're right, and a stablecoin needs to take extra precautions to take these into account and maybe get the average sea level over the course of time. And most popular floating stablecoins have some mechanism to account for turbulence like that. Summary: peg stablecoins are tied to that of another asset, while floating stablecoins use different mechanisms to keep the same buying power over time. Number 2, stability method. The stability method is this mechanism that keeps the coin stable. If it's a peg stablecoin, what is the pegging mechanism? If it's a floating stablecoin, well, what is the floating mechanism? And it typically revolves around minting and burning the stablecoins in very specific ways, and usually refers to who or what is doing the minting and burning. These are on a spectrum of governed to algorithmic. In a governed stablecoin, there is a governing body or a centralized body that is minting and burning the stablecoins. You can imagine the maximally governed and least algorithmic coin would be a single person/entity minting new stablecoins, promising that the coins are not volatile. But it could also be an organization like a government, or even a DAO choosing to mint and burn new coins. These governed coins are typically considered centralized, since there is a singular body that is controlling the minting and burning. You can make them more decentralized by introducing a DAO, and that kind of makes them more algorithmic, but we'll get more into that later. Coins like USDC, USDT, and TUSD are examples of governed stablecoins. On the other hand, an algorithmic stablecoin is a stablecoin whose stability is maintained by a permissionless algorithm with no human intervention. And this is the third place where I disagree with traditional media. A coin like DAI I would consider much more algorithmic than governed because it uses a permissionless algorithm to mint and burn tokens. Whereas traditional media might say an algorithmic stablecoin is always under collateralized or follows seigniorage shares or something like that. But an algorithmic stablecoin is just when a set of autonomous code or algorithm dictates the minting and burning. There are zero meddling humans.
Would have been mine if it hadn't been for those meddling kids.
Examples of algorithmic stablecoins are going to be DAI, Frax, RAI, and yes, the $40 billion disaster, UST. Yes, we're going to talk a little bit more about classic UST and Luna. Now, a token can have algorithmic and governed properties in the same way that it can be somewhere in the middle of being floating and pegged. DAI, for example, does have an autonomous set of code that dictates the minting and burning, but it does also have a DAO where they can vote on different interest rates and what can be collateral types and different things like that. So technically, it is a hybrid system. It has some governance mechanisms and also some algorithmic ones. USDC would fall purely in the governed category because it's controlled by a centralized body. UST and Luna would fall almost purely in algorithmic. The Dirt Roads blog has some amazing takes on these pieces and a wonderful visualization of where on a spectrum of coins that are more algorithmic or governed. They use dumb as the opposite of algorithmic instead of govern, which probably isn't wrong. Most classically categorized fiat collateralized stablecoin almost all fall into the govern or dumb section, since they are dealing with fiat currency and you need a centralized entity to onboard that fiat to the blockchain. You'll also notice on this chart, they have anchored versus reflexive on the x-axis. That's referring to how the collateral type affects the stablecoin, and collateral type is what we're going to cover next. So the summary here though is algorithmic stablecoins use some sort of autonomous permissionless code to mint and burn tokens, whereas a governed stablecoin have some human interaction that mints and burns the coins and keeps them stable. Now, before we go into our final category, let's look at this chart again. We could replace the word anchored with exogenous and reflexive with endogenous. And we'd have a chart that shows collateral type versus stability mechanism, which brings us to number 3, collateral type. Now, when we say collateral, we mean the stuff backing our stablecoins and giving it value. For example, USDC has the dollar as its collateral, and it's the dollar that gives the USDC token its value, because you hypothetically can swap one USDC for $1. DAI is collateralized by many assets. For example, you could deposit ETH and get minted DAI in return. And UST was, in a roundabout way, collateralized by Luna. Exogenous collateral is collateral that originates from outside the protocol, and endogenous collateral originates from inside the protocol. So one of the easier ways to define what type of collateral a protocol is using is to ask this question. If the stablecoin fails, does the underlying collateral also fail? If yes, it's endogenous. If no, it's exogenous. If USDC fails, the protocol, does the underlying collateral, the dollar, fail? No. So the protocol has exogenous collateral. If the USDC stablecoin fails, the dollar is going to keep being the dollar. If DAI, the stablecoin, fails, does the underlying collateral, ETH, also fail? No. So the DAI system is exogenous. The value of ETH isn't dependent on the value of DAI. If UST fails, does the underlying collateral, Luna/Terra, fail? Yes, absolutely. And this is exactly what happened that caused the system to lose $40 billion in what seemed like a day. Exogenous collateral originates from outside the protocol. Endogenous collateral originates from inside the protocol. Two other good tests that you can ask are, was the collateral created with the sole purpose of being collateral? Or does the protocol own the issuance of the underlying collateral? If the answer is yes to either one of those, then it's endogenous collateral. Now, the traditional media usually says that algorithmic stablecoins are to blame, but I think what they're really referring to is endogenously collateralized stablecoins. It makes sense that they can be scary and potentially dangerous because their value kind of comes from nothing. Exogenously collateralized stablecoins are typically over-collateralized, meaning there's more value of collateral than there is of the stablecoins. Here we have another image from Dirt Roads comparing different stablecoins, the exogenous versus endogenous collateral of the protocols and how much they have. MakerDAO/DAI has almost all exogenous collateral. Frax, which is another stablecoin we haven't really spoken about too much, has a mix of exogenous and endogenous collateral. And the old Terra Luna and UST system had mainly endogenous collateral, which is how the system was able to crumble so quickly. So yeah, endogenously collateralized stablecoins don't have a great track record. So why would you want to make one? Well, the answer is scale. And oftentimes people also say capital efficiency. With exogenously collateralized stablecoins, the only way you can mint more stablecoins is by onboarding more collateral. You can only have a stablecoin market cap that is high or as high as that is the value of all your collateral. So if you want to have $68 billion in stablecoins, then that means you need to have $68 billion worth of collateral. And that's a lot of money that you would need to onboard to your system. If you have an endogenously collateralized stablecoin, you can have $0 worth of collateral, meaning it's much easier to become massive faster. Now, I agree with the Dirt Roads publication when they say that exogenously collateralized stablecoins can't scale. And I talk more about that in the blog associated with this video. So if you're interested, be sure to check that out after the rest of this video. But watch the rest of this video because we're just getting started. In the blog, we also talk more about seigniorage shares and shelling coin logic, which if you're interested in that stuff, definitely check it out. Most of these endogenous coins can be traced back to a paper written by a man named Robert Sams, where he talks about how to build an endogenously collateralized stablecoin using a seigniorage shares model, which again, I'm not going to go into, but I wanted to mention it because it's probably one of the most influential papers when it comes to these endogenously collateralized stablecoins. Endogenously collateralized stablecoins. That's a lot of words. Now, there's more information on the endogenous collateral debate in the blog, but let's do a thought experiment that I do think is compelling for endogenous collateralized stablecoins. Endogenously collateralized stablecoins. Imagine you have a currency and it's collateralized 100% by gold. And you run a bank and it's open 24/7 to allow people to exchange your generic coin for gold in your vaults. People love the convenience of our stablecoin instead of having to lug around their gold. So they treat our stablecoin as if it was gold because they know that at any time they can exchange it at the bank. This is an example of our generic coin being exogenously collateralized by gold, pegged to its price, and governed by us, by me, by our entity, since we own the issuance and burning of the coin. You come to our bank, we'll issue this coin, or we'll burn it once you redeem your gold. And since you can always exchange our coin for gold, our coin keeps its value. Now, let's say the bank is only open 5 days a week. Does our coin lose its value now that you can't always exchange it for gold? Well, probably not. The market probably won't even care. Now, let's say you need to close the bank for a week for renovations. Does our coin lose its value now? Well, let's say we close the bank for a month or a year or a decade. Forever? If we get to the point where you can never actually exchange our coin for gold or the underlying collateral again, maybe do people just use the coin as its currency backed by nothing? In a way, now it's moved from being exogenous to now being endogenous, since it's now backed by, well, itself. This is why Dirt Roads has reflexive on their chart. One of our coins is no longer equal to some amount of gold. It now equals one of itself. Okay, I know there's a lot here, and there's even more in the blog. So if some of this confused you, don't be discouraged. You can always come back. There's a ton of supporting documents and blogs and links that I personally watch to learn a lot of this as well. So be sure to use that if you get confused. But now let's look at some of the top stablecoins, what their properties are, and then we're gonna get to some really interesting stuff. We're not gonna go too deep into the architectures of these stablecoins. We are gonna go over DAI a little bit more though, because the DAI/MakerDAO system is a pretty standard model for what a stablecoin could look like. And it was one of the most influential stablecoins ever created, so there's that. And it's important that we go through these so we can understand what's currently out there and why they're currently out there. And then we can reveal why they're really out there. Why there's so many stablecoins. What are the incentives for people to mint them? And it may just blow your mind. So let's start with DAI. As we've mentioned before, DAI is a pegged, algorithmic, and exogenously collateralized stablecoin. It's one of the most influential DeFi projects ever created and was a huge factor in supercharging the DeFi space. Roughly, the way it works is you deposit ETH or some other crypto collateral into the smart contract that has this DAI algorithm code. And based off the current collateral to US dollar or ETH to US dollar price, it'll mint you some amount of DAI. You can only mint less DAI than the total value of collateral or ETH that you have. This way, the system always has more collateral than they'd have minted DAI. Additionally, every year or so, you'll get charged something called a stability fee, usually around like 2%. And now you're free to do whatever you want with your DAI. If you want to get your ETH back, you have to give your DAI back to the smart contract, which will then burn your DAI. It'll use the current price of ETH to figure out how much money it should give back to you. It's because of this stability fee and collateralized ETH that people often refer to this system as a collateralized debt position, since we technically owe DAI back to the protocol at some point. So yes, all the DAI that's in existence, somebody minted from the Maker protocol and needs to pay it back at some point. If you can't pay your stability fees or the price of ETH tanks and now the value of our collateral is less than the value of the DAI that we minted, people can liquidate us, which means they can take our collateral. Protocol always needs to have more collateral than minted DAI. So this is sort of your punishment for not keeping the collateral up and a way to save the system from becoming under collateralized. And then there's also a Maker token that's used to vote for stuff. Now, the reason I give this overview is I want your brain to be asking the question, hey, I get charged to mint a stablecoin? All the DAI in the world, somebody's being charged to have it out there? Someone could take my collateral if I don't monitor the balance? And most importantly, why would I spend money to mint this stablecoin? Why would I be the one to do that? Great question. That is the fundamental question, and we'll get to that. USDC. USDC is a classic pegged, governed, exogenously collateralized stablecoin. It's backed by real-world dollars in a bank account. Not much else to say here. UST and Luna. The classic old UST and Luna. We know it collapsed, but we can learn from what happened to hopefully prevent it in the future. UST was a stablecoin pegged to the dollar, algorithmic and endogenous, and it imploded on itself. Using what we know about stablecoins, can you guess why? Well, since the system was endogenous, once UST lost its peg, Luna became less attractive to hold. Since people weren't holding Luna, the price fell and it made it harder to keep the peg of UST, which made Luna's price fall, which makes UST harder to hold its peg, which makes, you see the pattern? People still want to try using these endogenously collateralized stablecoins because they do scale so quickly. So protocols like Frax have come a long way to do some type of hybrid between endogenous and exogenously collateralized stablecoin. RAI. RAI is one of the few floating stablecoins where it's not pegged to any other asset. It's focused on minimal governance, being floating, and using only Ethereum as their type of collateral with a nearly purely algorithmic stability mechanism. In a way, one could argue that because their collateral is only ETH, the price of RAI will always be somewhat pegged to the price of ETH, but that might be a longer argument. Due to these, it's floating, algorithmic, and exogenously collateralized. Now, they use some really cool supply and demand mechanisms to keep the price stable and non-volatile, but it's not really important how it works for the purpose of this video. So once again, I'm going to leave some links in the description if you want to learn more about RAI. The video on screen right now, I think, is particularly good at explaining exactly how it works and explaining why it's such a good stablecoin for normal average people to have. So now that we've gone over some stablecoins, we've gone over the categories, why we care, what is a stablecoin, let's talk about what they really do. We can start by asking the question, okay, which one of these is the best stablecoin? And to that, I need to ask, the best stablecoin for who? Centralized governed coins obviously have the issue of centrality, which sort of defeats the purpose of being in Web3. So maybe we want some flavors of algorithmic stablecoins. Maybe that's probably what we want for Web3. But these algorithmic coins might feel untested to non-crypto people, and the fees associated with them might be a little bit scary. For me personally, like I said, I really love the idea of RAI. The idea is to have stable buying power as opposed to being pegged to some other asset, and it's algorithmic in nature as opposed to being centralized. So it's a decentralized stablecoin. That's what we want. But every coin has their trade-offs, and I'd argue there is definitely no best coin right now. The stablecoin that's best for the average person might matter much less. It's the stablecoin that's best for rich whales might be what's more important here. Yes, the stablecoins the whales like might be what's more important. Now, for most algorithmic stablecoins, you'll see this. Some sort of fee associated with minting the coins. Protocols do make money off of these stablecoin systems, which I think is good. Sometimes they need money for maintenance, incentives for the stability of the coin, or money for improvements. So I do think these fees are good. And we need stablecoins for the three functions of money: storage of value, unit of account, and medium of exchange. But are you going to be the one to pay these fees to mint them and keep them in circulation? Someone has to pay to mint these coins and often keep paying. The market cap for some of these stablecoins is in the billions. If there is a 1% fee on these and the market cap is 1 billion, we're talking about $10 million. Are average people going to collectively pay $10 million a year to keep these in circulation? No. So average people aren't printing these for the three functions of money. Well, then who is minting these? So let's play a little thought experiment. Let's say I have ETH as an investment and I've bought up all the ETH. I've sold my house, I've sold everything I own, and I've used everything I have to buy Ethereum. But I want more. What can I do? I can put my ETH into one of these stablecoin protocols, get the minted stablecoin, and then sell the stablecoin for more ETH. You might have heard concepts like leveraged investing or margin trading, and this is essentially the Web3 equivalent. It's kind of funny. Why are stablecoins good? Well, because we need those three functions of money. But why are stablecoins minted? Well, because investors want to make leveraged bets. In fact, most stablecoin platforms have this as one of the biggest reasons to mint their stablecoin: to multiply exposure or to maximize your position on some crypto asset. Now, for sophisticated investors, this isn't new information at all. This is like investing 101. However, it does feel weird that we need stablecoins for the three functions of money, but that's not why they're minted. So even though I said I really like RAI as a stablecoin for the people, a reason DAI might be higher market cap is that investors like the leverage opportunity much more than they like the leverage opportunity that RAI offers. It could be something else, but that might be a big reason. How much stablecoins are minted are based off of how much investors think they can use that stablecoin to get more exposure to assets that they really want. So I know we've gone over a lot here, and the rabbit hole really doesn't end there. Curve.finance, being one of the most important protocols for stablecoins, is a really interesting story as well. My friend Garrett, who teaches about technology and finance, has a fantastic example as to why a stablecoin exchange might be so important.
You might wonder how a stablecoin exchange ever got off the ground. Is there really any demand out there to trade $1 for $1? Then I think back to my university days. One weekend, my laundry pile grew so disgusting, I was desperate to use the washing machine immediately. But the laundry machine took quarters, and I only had dollar bills. Quarters were in such short supply around the dorm room that I was willing to pay more than $1 for 4 quarters. In this urgent moment, I had specific utility in mind, and that changed my personal equation for this.
And Aave and Curve, both looking to launch their own stablecoin soon, is going to be really interesting as well. So we'll just have to see how these unfold. I do think, though, that we are going to get better and better at creating these stablecoins because we do need them. They are important. And for you developers watching who want to build one of these, we have some minimal stablecoin contract examples in our DeFi minimal repo. Link in the description. So if you're looking to tackle this problem, definitely be sure to get started there. I'm really excited for the future of DeFi and for the future of stablecoins, as I think they are a wildly important primitive for DeFi. And I know that this was a long video, but I hope you all learned something. And I hope this gives you a better idea of what stablecoins really are and how they're created. If you learned something, leave a comment in the comment section. If you didn't learn something, leave a comment in the comment section. Or if I got something wrong, leave a comment there. Thank you all for watching, and I'll see you next time. All right, we have now learned a ton about DeFi, and hopefully I piqued your curiosity on how much more there is still to learn. But now we're going to move on to creating our own stablecoin here. So again, you can follow along with all the code that we're going to be going over in this Foundry DeFi Stablecoin F23 section of this course. And like I said, I'm planning on getting this code actually audited. So be sure, if you have your GitHub repo, be sure to watch this repo and look for updates, because I will be posting the audit reports in this as well. I've got a couple videos on what smart contract audits are and why they're so important, and I'll leave a couple links in the GitHub repo associated with this course. For those of you looking to go down the security track, definitely be sure to watch this video. But all right, we are finally in our GitHub repo. Let's build this stablecoin. MKDIR, Foundry, DeFi Stablecoin, F23. Let's open this up with code, or you know the drill, file open folder. We're going to be going a little faster this lesson because a lot of what we're doing is just going to be drilling in information that you already know. We have a couple of new things to go over, such as stateless fuzzing, which we'll talk about in a bit. But a lot of the coding aspect of this, you already know. All right, we're in our folder. Forge init, clear. Let's make a little README over here and talk about the design of our protocol. So we're going to make a stablecoin. But if you watch that stablecoin video, we're going to make a stablecoin that is one, anchored. So when we're talking about the relative stability, it's going to be anchored or pegged to the US dollar. So this means we're going to have to put some code in here to make sure that our stablecoin is always worth $1. Number two, the stability mechanism, or the way we do minting, is going to be algorithmic. This means that this is going to be a decentralized stablecoin. There's not going to be any centralized entity that's going to mint or burn or maintain the price. This is going to be 100% on-chain and algorithmic, which is ideally what we have for the future of stablecoins. There's no controlling entity that controls our stablecoin. So this is great. A better stablecoin for Web3 probably isn't anchored or pegged. It's probably floating, but that's a much harder mechanism to do. So we're going to go ahead with the anchored or pegged for the moment. And then finally, the collateral type is going to be, you guessed it, exogenous. And it's going to be crypto collateral. We're going to use cryptocurrencies as collateral for this currency. We're going to use Ethereum and Bitcoin as the collateral for our system here. So with this being our architecture, we're going to keep this in mind. Okay, how can we actually make sure that this is always pegged to $1? And one way we can do this is with a Chainlink price feed. So with a Chainlink price feed, we get the price feed and we set a function to exchange ETH and Bitcoin for whatever their dollar equivalent is. And this way, if right in our contract we have this exchange set up, the price of this stablecoin should hypothetically always be around $1. To make the stability mechanism algorithmic, we're going to say people can only mint the stablecoin with enough collateral. And that's going to be coded directly into our protocol. And the collateral type being exogenous, of course, we're only going to allow these two types of cryptocurrencies to be deposited. Specifically, we're going to use wrapped ETH and wrapped Bitcoin. So the ERC20 version of ETH and the ERC20 version of Bitcoin. Some might argue that this wrapped Bitcoin is a little bit centralized depending on who is onboarding the Bitcoin into Ethereum, but that's another conversation. So over collateralized stablecoin with WETH and Bitcoin as the collateral for this. Let's do this. So the first thing we're going to do is we're going to get rid of all these. Goodbye, delete. And now we're going to create our two main contracts. New file, D decentralized stablecoin, do a capital C .sol. And this is just going to be the actual token. So I'm actually going to copy paste my layout of functions because I like them. I like to have this. And at the top, of course, SPDX, license identifier, MIT. If you want, you can just copy this directly from the GitHub repo associated with this course, SRC, right in here, copy this layout here. I like to have it as a reference. Then you already know, Pragma, Solidity, 0.8.18, and we'll do contract, decentralized stable coin, boom, like this. And now this is going to be one of the main differences between this code we're writing here and all the other products that we've done. We're going to be very verbose with our code documentation. And the reason for this is when it comes to security professionals who are going to review this code, we're going to make their lives so much easier if we have a ton of text explaining what our code is doing. Additionally, if you work with AIs are fantastic at reading and understanding language. So the more language that we have to explain what our code should do, the better off our code can be sent through some AI model to make sure that it doesn't have issues. So we're going to go ahead, add a little bit of NAT spec here, right from the get-go. Add title, decentralized stablecoin, all one word. At author, Patrick Collins, or put your name here. Yep, this is open source, MIT license. You can do whatever the heck you want with it. I'm even going to say collateral, exogenous, ETH and BTC. Minting, or the stability mechanism, is going to be algorithmic, meaning it's decentralized. Relative stability is going to be pegged to USD. Then I'm going to say under here, this is the contract meant to be governed by DSC engine. This contract is just the, I'm going to toggle word wrap here, ERC20 implementation of our stable coin system. So that's what this is going to be. This decentralized stablecoin is purely going to be an ERC20 with minting and burning and stuff, right? It's not going to have any of the logic. The logic is going to be in a separate contract. So let's go ahead and let's make this. So first, constructor, boom. And we're going to use OpenZeppelin to get this kick-started. So right at the top, import, well, actually, before we even do that, forge install OpenZeppelin / OpenZeppelin -contracts --no -commit. And we went ahead and installed that. Now we're going to open up our foundry.toml. We're going to add some remappings in here. So remappings equals at OpenZeppelin /contracts equals lib /OpenZeppelin /contracts /contracts. That looks pretty good. Right up at the top of this now, import, little named import, ERC20. We're going to import this ERC20 burnable contract. I'll explain this in a second. And then also ERC20 from at OpenZeppelin /contracts /token /ERC20 /extensions /ERC20 burnable.sol. Did I spell this right? Looks like that's right. So what did oops, looks like I spelled contracts wrong. Let's spell it right. Okay, cool. That looks good. Now what we're going to say is that our decentralized stablecoin, let me even zoom out a little bit. Yep, this is going to be a big one. So we're going to zoom out a little bit here. Hopefully you all can see this, is ERC20 burnable. Okay. And the reason that we're going to use this contract, if we command click in it or just look it up, is it has this burn function. And we want this burn function because this is going to help us maintain the peg price. We're going to be burning a lot of these tokens. You'll understand that in a bit. Now, same as an ERC20. So the ERC20 burnable contract is an ERC20, which is why we can import the ERC20 contract from it as well. And the ERC20 burnable constructor is an ERC20, which means we have to use the ERC20 constructor as well, which takes a name where we're going to call ours decentralized stablecoin and DSC, like this. And that's it. This is going to be our whole constructor. We're not going to touch it. That's all we're going to do. Let me zoom in a little bit. I'm going to keep zooming in and out. Hopefully it's not too crazy. Now, we want this coin to be 100% governed by our engine. And our engine is going to have all this stuff about what collaterals to use, how to use it, what to peg it to, etc. This is purely just going to be the token. So since we want this token to be 100% controlled by our logic, we're going to make this ownable as well, which means we're going to have only owner modifiers where the owner is going to be that immutable logic we're going to create. So OpenZeppelin has a package for that too. So we're going to do import ownable from @openzeppelin/contracts/access/ownable.sol. I'm going to copy this. So our contract is going to be ERC20 burnable and it's going to be ownable. And there's going to be two major functions that we want our engine to own. And those functions are going to be function burn, where it takes in a uint256 underscore amount public. We're going to override the burn function in burnable. And this is going to be only owner, so that only the engine, only the logic that we give it can mint and burn. And we're going to say uint256 balance equals balance of message.sender. And we're going to make sure that when somebody tries to burn some token, they at least have that much token. So we're first of all going to say if the amount is less than or equal to 0, then they can't burn, right? We don't want people to try burning 0. That's silly. So we're going to revert with an error. We're going to put all of our errors right up at the top here. Error, decentralized stablecoin __ must be more than 0, like this. So we're going to revert with this error. And then we're also going to say if the user's balance is less than the amount that they're trying to burn, then we're going to revert with another custom error. I'm just going to copy paste. And I'm just going to say burn amount exceeds balance. Boom, paste that in like this. And then finally, we're going to do this thing called super.burn, which we haven't talked about yet. So this super keyword basically says, hey, use the burn function from the parent class, which in this case is the ERC20 burnable. So all of this code is going to run. It's going to hit this line. It's going to say, hey, go to the super class and use the burn function there. So our code's going to go, oh, okay, well, ERC20 burnable, that's the super class or the parent class. Just use the burn function in here, which calls the burn function here in the ERC20.sol, which does all this stuff in here. So that's what the super keyword does. Only owner, only engine's going to add this. Now we're going to do this function mint. This is going to be an address 2 and a uint 256 underscore amount. This is going to be public. Excuse me. This is actually going to be external. Also only owner. This one probably could be external as well, but that'll come out in the audit. External only owner. And this is actually going to return a Boolean. When you do mint, you want to have a return a Boolean here. When you do a mint, we're going to return true if it actually works. But we're going to say if 2 equals address 0, we're going to do a little sanitization of the inputs here. Then we're going to revert with a new error. Error, decentralized stablecoin, not 0 address. We're not going to let people accidentally mint to the 0 address because that happens kind of a lot. And we're going to say if the amount is less than or equal to 0, then we're also going to revert with this more than 0 error here. Boom. And then finally, we're going to return true. Oh, and then obviously we should run mint _2 amount. So we're not overriding any functions in here, right? We're just calling the mint function. Over here, we had to do super because we're overriding the burn function. We're saying, hey, do all this stuff and then do the regular burn. There is no mint function. There's an underscore mint function that we're going to be calling. And guess what? That's it. This contract's done. We're not doing any more here. Forge, build, cool. And then we probably want to write some tests for this, write a deploy script, but we're going to do all that in a little bit. Now, what we're going to do is we're going to build the engine to the car, the main components of this contract. If you want to take a break and be proud of yourself right here, go for it. If you want to even pause the video, start writing some of your own tests, write your own deploy scripts, go for it. But let's go ahead and start building this engine. And we're going to be building this a little bit different than some of the other projects. We might even be testing some of this along the way to make sure we get things right. So I'm going to go ahead, create a new file, dscengine.sol, decentralized stablecoin engine. And let's build this engine to this car. All right, let's go back to, I'm just going to copy paste this beginning part. Let's come to the engine, paste that in. We have SPDX, layout of contracts, pragma solidity, contract, DSC engine, like this. And let's give this a lot of nat spec. All right, title, DSC engine. I don't want that. At author, Patrick Collins. The system is designed to be as minimal as possible and have the tokens maintain a $1 1 token equals $1 peg. I'm going to toggle the word wrap. This stable coin has the properties genus collateral, dollar pegged, algorithmically stable. It is similar to DAI if DAI had no governance, no fees, and was only backed by wrapped ETH and wrapped Bitcoin. At notice, this contract is the core of the DSC system. It handles all the logic for minting and redeeming DSC, as well as depositing and drawing collateral. At notice, this contract is very loosely based on DAI, on the MakerDAO DSS DAI system. You might be asking, Patrick, that's a lot of text here. Yes, we want a lot of text. When people read our code should be readable. Remember, your code is going to be written once, read hundreds of thousands of times. I have read the Aave and Maker code so many times, and so many other people have as well. You want your code to be very verbose so that other people can come and understand what's going on. So let's begin. So let's think about what are the main functions that our project should have. What are the main things that we should do, right? Before we even start coding anything. And oftentimes, a lot of people will take this step and will actually create an interface for their code. They'll create an interface and say, hey, here's all the functions that I want this to do. And then they'll say, hey, our contract is that interface so that they don't forget any of those functions. For us, I'm just going to go ahead and write them out here. So I want one function to be function, deposit, collateral, and mint DSC. I want people to be able to deposit their DAI or their Bitcoin and mint our DSC token. I want people to redeem their collateral or DSC, right? When people are done with doing whatever they want with the stablecoin, they can turn the stablecoin, the DSC, decentralized stablecoin, back in for whatever collateral they originally used. I want people to be able to function burn their DSC. And the reason for this is if they're nervous that they have too much stablecoin and not enough collateral and they want just a quick way to have more collateral than DSC, they can quickly burn stuff, which is another part of the system. We should even put a point in here. Our DSC system should always be over collateralized. At no point should the value of all collateral be less than or equal to the value of all the DSC, or the dollar-backed value of all the DSC. We should always have more collateral than DSC in the system at all times, and we need to code in such a way. So burn DSC is a function that will make more sense in a little bit. We should have a function called liquidate, and this is going to be a really important function. The reason that we're always going to have more collateral, if the value of their collateral drops too much, let's say I put in $100 worth of ETH and I minted $50 worth of DSC. I have more collateral than DSC. That's good. What if the ETH price tanks to $40, 40 ETH? Now we are under collateralized, right? Now we have less ETH than we have DSC. And this user should get what's called liquidated. They shouldn't be allowed to hold a position in our system anymore. So ideally we set some threshold that's too low. Maybe it's 20%. And if you hold $60 worth of ETH and $50 worth of DSC, you should get kicked out of the system because you're way too close to being under collateralized. This liquidate function is going to be the function that other users can call to remove people's positions to save the protocol. And we'll talk about that a little bit more very soon. And we're going to want a function health factor. This should be an external view function, or get health factor. And this will allow to see how healthy people are. So let's go back up to this example here. So if the price of ETH dumps to $40, we're now $10 under collateralized, right? And that's not good. That's really bad. We never want this to happen. So what we can do is we can set a threshold to, let's say, for this example, 50% or 150%. So if you have $50 in the system, you need to have at least 75 ETH at all times. This way, there's a little bit of a buffer. That way we can never be under collateralized if the price tanks here. If you go to $74, now what we can do is we can liquidate and we can say, hey, if someone pays back your minted DSC, they can have all your collateral for a discount. So maybe we say, hey, somebody pay back this 50 DSC and you can have this $74 worth of ETH. Somebody's going to be very incentivized to do this because they're going to make $24. So we'll set some threshold, maybe 150%, and we'll say, hey, anybody who liquidates your position, if you're under the threshold, they can have, as a reward, some of your extra collateral. And this will incentivize people to always have extra collateral. Otherwise, they're going to lose way more money than they borrowed. If that didn't make sense. So one more time, let's do that example. So if I put down $100 worth of ETH as collateral and I mint $50 worth of DSC, now I'm going to go off and do whatever I want with DSC. Price of my ETH tanks to $75, or better yet, let's say $74. Some other user is going to see, oh my God, under collateralized. And we're going to let people liquidate their positions if they become under collateralized based off the threshold. Some other user is going to see that and they're going to say, okay, I'll pay back the $50 of DSC. I'll pay back the $50 of DSC. So now this person has zero debt, and in return, get all your collateral. So now this person has $0 worth of ETH, and this user got the $74. And all they had to do was pay $50 of DSC to get $74 of ETH. So this person is now up, just made $25 or $24 by liquidating you. They're incentivized to make money, and this is your punishment for letting your collateral get too low. So hopefully that makes sense. If this system of liquidations doesn't make sense to you, you know where to go. Come to the GitHub repo associated with this course and start joining the discussion. All right, so hopefully this made sense. If it doesn't, use the discussions tab, of course. Now these are kind of this combination function. We're probably going to want a function just called deposit, deposit collateral, external. We're probably going to want a function redeem collateral, external. And then we're probably going to want, along with a burn DSC, we're probably going to want a function mint DSC, external. And these look like these are probably going to be the majority of what a protocol does. And what a lot of people even do is sometimes they'll even write tests right now, describing what each one of these should actually do to the system, right? We're not going to do that, but we may actually write some tests as we go along here. And I like to write my deploy script kind of early, and you'll see me do that here. That way I can write tests using my deploy script. So let's go ahead though. Where is the best place to start tackling this? Well, to me, the easiest place to start is actually with the depositing, right? Because that's the first thing people are realistically going to do with this protocol is actually deposit the collateral. So I'm going to start there. So for this deposit collateral function, what are they going to want to do here? Well, we're going to need to let them pick what collateral they want to deposit. So we'll say address token collateral address, and then also the UNT56 amount collateral. And we're going to do a little toggle word wrap. All right, cool. So deposit collateral, the token collateral address, and then the amount that they're going to want to do. So already we can see that there's going to be a whole bunch of stuff that we're going to want to do here. So let's even do a little bit of NatSpec, here. We'll say @param. We'll just explain what the params are. And this is where GitHub Copilot is really helpful because oftentimes it's really good with docs. So we're going to say @param, param. So both of those look good. Token collateral address, the amount of token to deposit as collateral, amount collateral, the amount of collateral to deposit, right? Real simple. So we're going to want a couple of things here. We're going to want to sanitize this a little bit. So the amount collateral, we're definitely going to want this to be more than 0. So we're probably going to want a modifier called more than 0 that we can use throughout these functions. Sometimes people might accidentally send a 0 transaction. We want to automatically revert those. So if we scroll up to the top here, we can see our modifiers come before our functions. So we're going to create our modifiers here. And we're even going to add like a little section, a whole bunch of these here. Boom, 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 boom. Modifiers like this. Cool. And we'll say modifier more than 0. And this modifier will take a UNT56 amount. And we'll just say if amount equals 0, then we're going to go ahead and revert with a new error. Where do errors go? Let's go to the top. Errors go right underneath imports. Actually, it's not quite right. They're going to go right underneath the contract. So we're going to copy this whole section. We're going to say errors. We're going to go here. So we're going to say error, DSC engine __. What do we want to call that? What, just needs more than 0? Needs more than 0. Like this. And we're going to revert with needs more than 0. And of course, add the little underscore here. Cool. So now we have a more than 0 modifier. So we can make this external more than 0, and we'll pass the amount collateral. And boom. Okay, cool. We're doing a little sanitization here. What else should we do? And you know what? Let's even copy this. We'll paste this here. We'll say functions, and we're going to have a constructor. So I'm just going to put this here for now. Constructor, I should spell constructor right. And then we're going to have a section after functions, like a subsection. We're going to call it external functions, like this, external functions. Cool. Because we want to go receive and fallback. We're not going to have those, but then external and public. So external function first. Anyways, okay, more than 0, got that. And we probably don't want people to use any collateral, right? We probably only want them to use certain collateral that we allow. So we're gonna have to create a new modifier called isAllowedToken. So we're gonna do modifier isAllowedToken. And this is gonna take a address token. Basically, we're gonna say, if the token not allowed, the token isn't allowed, then revert, right? However, at the moment, we don't have like a token allow list. So let's create that. This is probably going to be a state mapping. So let's scroll to the top. Where do state variables go? So errors, type declarations, state variables. Okay, errors. Great, let's put it here. State variables. Okay, and let's create an allowed list of mapping. So we'll do mapping address to bool, private s underscore token to allowed. And we could do this. However, I already know that we're going to need price feeds. So instead, what I'm going to do is I'm not going to do an address to bool. I'm going to do an address to address. And this is going to be our price feed mapping. So this is going to be s underscore price feeds. And normally I do the syntax token to price feed, right? But for this one, we're just going to call this price feeds, and we're going to use the newer Solidity named mappings to make this a little bit clearer. So I'm going to say address token maps to address price feed. So now this is S price feed, and anybody can look up and go, okay, so this is token to price feed. Cool. So we're going to have this list of price feeds. And where should we probably set this? Well, we're probably going to want to set this up right in the constructor, right? Right when we deploy this contract, that's when we're going to say, okay, these are going to be the allowed tokens. These are the price feeds. And that way it's going to be like that forever, right? We're never going to be able to change this. So what we'll do is in our constructor now, we'll take in the allowed tokens and their price feeds, right? Because in order for this system to work, we go to like data.chain.link. In order for this entire system to work, if we want to know how much value our Ethereum that people deposit in here is worth, we need to have the pricing, right? The only way for us to know if we're over collateralized, if we know the value of our ETH and our Bitcoin. So we're going to use these two price feeds to maintain that. Because these price feeds are going to be on different addresses on different chains, you already know that we got to parameterize it. So we'll do an address array, memory, token addresses, comma address array, memory, price, feed addresses as input parameters. And we're going to say token address 0 maps to price feed 0, token address 1 maps to price feed 1, etc. And while we're in here, I already know that our DSC engine is going to need to know about our decentralized stablecoin. Why? Because our DSC engine is going to need to know to call burn and mint. So in here, in the constructor, this is also where we're going to pass the address, DSC address, decentralized stablecoin address. And so in here, let's do some sanity checks on this. We'll say if the token addresses .length does not equal the price feed addresses, price feed addresses .length, we have an issue, right? Because if there's more tokens or more price feeds, that means we messed something up. So we're going to go ahead and revert with a new error. We'll go to our errors here. We'll say error DSC engine __ token address is and price feed addresses must be same length. It's a massive error, I know, but I like being verbose, like I've told you before. So if those don't match, we're going to go ahead and revert. Then we're going to loop through the token addresses and update our mapping that we just created up here to say, okay, the token address is mapped to the price feed address. Now, in order for us to get a pricing, we're going to have to use the USD price feeds, and every price feed that we're going to have to use is going to be the USD backed price feed. So for example, it's going to be ETH, USD, BTC, USD, MKR, USD, etc. Okay. So we're going to loop through. We're going to say for UN256, I equals 0. I is less than token addresses .length, I++. So we're going to loop through this token addresses array. And we're going to say s_price feeds of token addresses I is going to equal to price feed addresses of I. So we're going to set up this price feed. So whatever the token, so the token of I is going to equal the price feed of I. And that's how we're going to set up what tokens are allowed on our platform. If they have a price feed, they're allowed. If they don't, they're not allowed. And then I know we're going to do a lot of stuff with our DSC. So this is where this is definitely going to be an immutable variable. So we can scroll up, make a immutable variable. We'll say decentralized stablecoin private I_DSC, because we're going to make this immutable. And since we're using decentralized stablecoin, we're going to have to go ahead and import this. So let's go to the top here, do import decentralized stablecoin from /decentralized stablecoin.sol. So now decentralized stablecoin private IDSC. We can now do, this is going to be private immutable. Go back down to the constructor. We're just going to say IDSC equals decentralized stablecoin DSC address, like that. Again, using GitHub Copilot. If you don't have GitHub Copilot, that's okay. There's a lot of other free AIs that you can use as well. Okay, cool. So we set up our constructor. We're going back down to deposit collateral. The whole reason we were doing this is we're saying, okay, we should only allow certain kinds of collateral on our platform. So now we can create a new modifier called isAllovedToken, where we can just say if s_price feeds of token equals address 0, then we can go ahead and revert with a new, oh, that looks like a good one. DSC engine token not allowed. I'm just going to copy that, go to the top, and thanks GitHub Copilot, just auto-filled it in for me. Okay, great. And then of course we need to do this down here. Cool. So is token allowed more than 0 is allowed, or excuse me, is allowed token collateral address like this. All right, cool. And then additionally, I'm going to add a non-reentrant modifier here as well. And we're going to grab this from OpenZeppelin. Whenever we're working with external contracts, it might be a good idea to consider making your function non-reentrant. Reentrancies are one of the most common attacks in all of Web3. And to be honest, sometimes I'll just rip a non-reentrant modifier, even if I'm pretty certain it's not vulnerable to a reentrancy attack. I feel like, to be honest, most functions should be non-reentrant by default, but especially when working with external contracts, it's a good idea to maybe put this modifier here. Now, this might go to audit and we might say, hey, well, we don't need this non-reentrant modifier and maybe we get rid of it, but maybe we don't. The trade-off is it's a little bit more gas intensive to have this here, but it's also safer. So I'm just going to stick it in here, even if I'm pretty certain I don't need it. We're going to get this from OpenZeppelin has a non-reentrant modifier from their reentrancy guard. So we'll import, actually my GitHub Copilot automatically had it. Reentrancy guard from OpenZeppelin, contracts, security, reentrancy guard.sol. Yep, that's actually exactly correct. And then what we can do is scroll down and we can see our DSC engine is reentrancy guard. And by doing this, we now have access to this non-reentrant modifier. And now this function is non-reentrantable, which is what we want. Okay, cool. Now we can finally start doing some collateral stuff. So we're going to go ahead and deposit this collateral. First thing we're going to need to do is a way to track how much collateral somebody has actually deposited. So what's that look like? Well, that probably looks like a mapping to me. So let's go to the top. We'll create a mapping of address user to mapping of an address token to UN256 amount private s_collateral deposited. So this is a mapping to a mapping. Crazy, right? So we're going to map the user's balances to a mapping of tokens, which is going to get mapped to the amount of each token that they have. All right, so let's scroll back down to our deposit collateral function. So now we have a collateral deposited mapping. So we can do s_collateral deposited of message.sender of this token collateral address. Now that we know it is an allowed collateral address, it's going to be plus equal to the amount collateral, right? And I'm actually running into an issue here where when I do forge formats the code look like this, but right now when I'm saving, it's reformatting in a different way. So what I'm going to do is it looks like it's using a different formatter that I don't like. So I'm going to go to the extensions, Solidity hard hat, hit the settings here, extension settings, and we're going to change this from prettier to forge because I want to use the forge format settings. Now if I hit save, okay, great. It saves and formats the way I want it to. Okay, great. So as you can see here, we're updating state. And what should we do when we update state? We should emit an event. So we're going to emit collateral deposited. We're going to have it be the message.sender who is depositing the token collateral address and the amount collateral as well, which means that we have our first event. All right. So let's go on up here. Zoom back out. Scroll all the way up to the layout. Where do events go? Events go after the state variables. Okay, so I'm going to copy this. They go right after the state variables before the modifier. So we're going to say events. We're going to go here. We're going to say event. And GitHub Copilot automatically filled it in for me. Awesome. Address indexed user, address indexed token, UN256 amount. We don't really need to index that. Maybe we do. Why not? Let's just index it. All right, cool. And just to note, a keyboard shortcut that I use a lot is Control back or Control minus, which allows you to go back to the last spot you were in your code. If you do Control Shift minus, it'll go forward. And I use this all the time. So for example, if I'm way down here in my code and I hit Control back, I'll just go right back to the last place my cruiser was. And I use this all the time. I'm not sure what the keyboard shortcut on Windows or Linux is, but on a Mac, it is Control back and Control Shift back, and I use it all the time. Anyways, so we are in deposit collateral. We have this emit here. We finally have the event, and okay, cool. So we're updating the collateral, internal record keeping. We're emitting event. Now, of course, we should actually get the tokens, right? And you can see here, we're following CEI, right? So we do a little notice follows CEI, checks, effects, interactions. So all the checks are happening in our modifiers here. These are all the checks. Our effects are right here. And then finally, our external interactions. So this is where we're going to do that transfer from. And we're going to need to wrap our collateral as an ERC20. So we're going to need to call transfer from on it. So I'm going to go ahead and import IERC20 from at open zeppelin/contracts/ token /ERC20 /IERC20.sol. Control minus to go right back down to here. Isn't that nice? And we can finally do IERC20 of the token collateral address dot transfer from message.sender to address this amount collateral like this. And we'll say, so this function actually returns a Boolean, bool success. And we want to make sure that this is actually being true. So we want to say if not success, we'll just revert DSC engine underscore transfer failed like this. What's this? An error? You bet it is. So we're gonna put this at the top. Error DSC engine transfer failed. And I'm gonna hit Control minus to go right back down to the code that I was working with. Okay, cool. So this function looks pretty good to me. I'm able to deposit collateral in here and update our mappings. Now might be a good time for us to start writing some tests for this, right? And we could do something similar to what we did before, where we just kind of threw together a real quick setup in our unit tests and then had our integration tests be what our deploy script actually uses. Well, let's write a couple more functions first, and then we can go ahead and do all that work. So we have a way to deposit the collateral. Okay, awesome. What should we do next? Well, the next thing that we should do is have a way to mint our DSC token, right? Once they deposit the collateral, they should be able to mint the DSC token. And then the combination of those two will be this function, deposit collateral and mint DSC. So let's go ahead and actually create this mint DSC function. Because now that they have some collateral, we should be able to mint some DSC. And now this is actually going to be a surprisingly involved method, right? Because in order to mint DSC, we need to check if the collateral value is greater than the DSC amount. And this is obviously going to involve a number of things, right? It's going to involve price feeds. We're going to be checking values. We're going to be checking a whole lot of stuff, okay? So this is actually going to be a little bit more of an in-depth function here. So let's create this mint DSC function, and we'll have this get passed in a uint256 amount DSC to mint. So people can pick how much DSC they want to mint. So let's say, for example, someone deposits $200 worth of ETH. Maybe they only want to mint $20 worth of DSC, right? So they can pick how much they want to mint here. So amount to mint here. And let's add some checks here. We should have them mint more than 0. Amount DSC to mint, like this. What else? We probably want this to be non-reentrant, even though we probably don't need this to be non-reentrant because it's our DSC token, but let's put it in here anyways. It's probably all we need for now. We probably want to do some, looks like GitHub Copilot even gave me some follows CEI. Yes. Oh, that's wrong. Amount DEC to mint, amount DSC to mint, the amount of decentralized stablecoin to mint. At notice, they must have more collateral value than the minimum threshold. We're going to figure out what that means in a second. So mint DSC, we'll need to keep track of how much everybody has minted, right? So whenever they're minting DSC, they're in a way, they're minting debt, right? So we're going to need to keep track of that. Where can we do that? Well, we can do that as a state variable. So we'll do mapping of an address user mapped to their uint 256, which is going to be an address user mapped to the uint 256 amount DSC minted. It's going to be private s underscore DSC minted, like this. Now I can go back down here with this new mapping, sdsc minted, message.sender plus equals amount DSC to mint. So we're going to keep track of all that they minted. Again, this is going to follow CEI. So now we want to do a little check here. If they minted too much, for example, like they minted $150 worth of DSC, but they only have $100 worth of ETH, that's going to be way too much. We should 100% revert if that happened. So I'm actually going to make a function. I'm going to make an internal function called revert if health factor is broken with the message.sender being sent. So we're going to create this new internal function. So up here we have external functions. We're going to scroll down here. We're going to make this private and internal functions like this, and we're only going to be able to call this internally, right? So we're going to create this function revert if health factor is broken, address user. It's going to be an internal view function. And we're going to basically check health factor, which is basically, do they have enough collateral, right? And then revert if they don't have a good health factor. So this health factor is actually a term that I borrowed from the Aave documentation. For each wallet, these risk parameters enable the calculation of health factor. And you can see a little bit of an image here that shows it. So additionally, we're going to need to make a function that checks the health factor. Actually, these are going to be private and internal view functions. So first we need to make a function that can get the health factor. So we're going to make another function here called function underscore health factor. We're going to take an address user. And you see we have this leading underscore to tell us as developers that this is an internal function. So let's actually give this an underscore as well. Function, health factor. This will be a private view. It's going to return a uint 256. So what this health factor thing is going to do, give it a little bit of nat spec. We can say this is going to returns how close to liquidation a user is. Say if a user goes below 1, then they can get liquidated. So we're going to figure out what the ratio of collateral to DSC minted that users can have with this health factor function. We're going to be building a lot of stuff here. So in order to figure this out, what do we need? Well, we're going to need to get both their total DSC minted, right? And we're going to need to get their total collateral value, right? Not just the total collateral. We're going to need to get the total collateral value and make sure the value is greater than the total DSC minted. So we're going to have to make another function. We're going to need to get the uint 256 total DSC minted and the uint 256 collateral value in USD. And we're going to create a new function called get account information from that user. So we're going to do another one. Boom. Function underscore get account information like this. We're going to take an address user. This will be a private view. And we're going to return two things, uint 256 total DSC minted and uint 256 collateral value in USD. Two functions here. To get the total USD, that's easy, right? We just do total DSC minted equals this array, this mapping that we just created, right? We're keeping track of this exactly. So all we got to do is this. To get the total collateral value in USD, we're going to need to do some more math. So I'm going to say collateral value in USD equals get account collateral value, and we're going to pass some user. So this is going to be a different function. And we're going to make this a public function so that anybody can call this function themselves. So we're actually going to copy this, private and view internal functions, public internal view, and then we're going to do view and pure public and external functions all the way at the bottom. So we'll say private, we'll say public and external view functions. We'll do function, get account collateral value, address of the user. This will be a public view so that anybody can call it. Returns a uint 256. Stay with me. I know we're kind of going down this tree. Stay with me here. We're about to go even further. Now, to get the actual value, what do we need to do? Well, we need to loop through each collateral token, get the amount they have deposited, and map it to price to get the USD value. So we're going to need to loop through all the collateral tokens. Do we have a way we can do that? Let's scroll to the top. Well, we have a mapping of the price feeds, but we don't have a way to loop through them. So what we can do is we could just have like, address WETH and then address wrapped BTC. We could just have two tokens like this and we wouldn't have to loop through anything. We're going to make this system a little bit agnostic so that you could deploy this with any amount of stablecoins, any amount of collaterals. So we're going to make a new state variable. It's going to be an address array, private s_collateral tokens. And what we're going to do is write in our constructor, when we update our price feeds with the token and the price feed, we're also going to add the tokens addresses of I to this array. Now we have this array of collateral tokens that we can loop through, and that way we can calculate how much value people have based off of all of the tokens. So get account collateral value, we're going to say for uint 256, I equals 0. I is less than s collateral tokens dot length I plus address token equals s collateral tokens of I, and we'll get the amount. So this is the token that we're working with. We'll get the amount by uint 256 amount that is deposited by this user by s_collateral deposited user token like this. Then total collateral value in USD plus equals, now that we have the amount, we're going to need to get the USD value of this. And this is probably a function that we're going to want to have be public so that other people can use this as well. So create a function, get USD value, where somebody passes in an address token, uint 256 amount. This will be a public view, returns uint 256. And this is where we're going to do some price feed stuff, some stuff that's very familiar. So we're going to need to get the price feed for the token and then times the amount by the price. So we're going to have to work with aggregator v3 interface again, that Chainlink data feeds. So import, and I know we've worked with this before, aggregator v3 interface from, it looks like GitHub Copilot's got my back at Chainlink/contracts, blah, blah, blah. This means we're going to have to install that. Remember, we can install the smaller one with forge install smart contract kit /Chainlink brownie contracts at 0.6.1 -- no commit like this. Chainlink brownie contracts. Awesome. Then we're going to have to go to our foundry.toml, add some remappings in here. So we're going to put a little comma. We're going to say at Chainlink/contracts equals lib/Chainlink brownie contracts/contracts like that. So now we have the aggregator v3 interface. Scroll down to the bottom, get USD value. I know we've done this before. I know this is familiar to a lot of you. But we're going to say aggregator v3 interface price feed equals aggregator v3 interface of s_price feeds of the token. So we're going to get the price feed of the token we're looking to get the value of. Now we have the price feed here. We're going to do this. Wow. GitHub Copilot. Spot on. We're going to get the price by calling price feed.latest round data. And this is where we're going to do a little bit of math, right? Let's say 1 ETH equals $1,000. The returned value from CL will be 1,000 times 1E8. How do I know this? Well, if I go to docs.chain.link, go to data feeds, I can scroll down to price feed addresses, and I can see if I do show more details for ETH USD, ETH-USD, it has 8 decimal places. And I know Bitcoin USD also has 8 decimal places. We could add some code in here so that we make sure we're getting the right decimals, but I'm just going to go with 8 for now. And now we can do a little bit of math here. So we're going to need to do the price times the amount, right? But is this all we need to do? Return price times amount? No, because the number is going to be way too big, right? Let's say the price is 1,000 times 1E8. And now we're multiplying that by, let's say the amount is 1,000 times 1E18, because it's going to be in way. This number is going to be absolutely massive, right? So first, we need to multiply this 1,000 by a number to get this number to match this one. So these need to be the same units of precision. So that's going to be, we're going to have to multiply this first by 1E10. And because I don't like magic numbers, we're going to scroll to the top, create a new state variable right in here. We're going to do a uint256 private constant additional feed precision equals 1E10 like this. And now it's not a magic number. So instead of doing this now, we're going to say, okay, price, and we're going to wrap it as a uint256 so that everything's now in 256. We're going to say the price first needs to be multiplied by the additional feed precision so that now both of these are uint256s and they both have 1E18. But then we're going to have to divide all of these by 1E18 as well, so that this number doesn't look super wonky. So we're going to have to wrap this whole thing by 1E18. And as I hate floating magic numbers like this, so we're going to scroll back to the top, copy paste this. This is now just going to be called precision 1E18, grab precision, divide by precision. So uint256 price times additional feed precision times amount divided by precision, and we should be good to go here. This is where my brain immediately goes, okay, definitely need to write some tests for this. So once we finish going through this, we're definitely going to write some tests, at least for get USD value here. So let's go back up through our massive tree of functions that we just created that are not complete. So let's go back to get account collateral value. And this is going to be the total collateral value in USD. It's going to be get the USD value of the current token we're on times the amount that we're working with. Total collateral value in USD. Actually, let's put that there. Boom. And that's it, right? So we just loop through all the tokens in the token array, and we just add up the value in USD of each one of these tokens. And I know we don't need a return here, but I'm going to add a return here anyways. Return this. So cool. So now we have a way to get the collateral value in USD. We needed that way up here. Oops, let's do collateral value in USD. Get collateral value. Oops, let's do this. And awesome. So now our get account information is going to return the total USD minted, the total DSC minted, and then the total value of all the collateral here. Okay, great. Now we can scroll up again. We have this revert if health factor is broken, which is still busted because this function doesn't do anything. But now we can actually have it do something because we have this health factor here. We're going to update our health factor function because now we have the two of these. What we can do is we can just get the ratio of these two. So we could say collateral value in USD divided by total USD minted. This is what we're going to return for a health factor, right? Well, not quite. So let's say we have 100 collateral divided by 100 DSC, right? This is 1-to-1. If we go down If we go down a penny, we're going to be under collateralized, right? And we don't want to go under collateralized. We always want to be over collateralized, because if this ever goes below 100, our system is bunked up, right? So we want to set the threshold to be like, hey, if you go under 150 collateral, you can get liquidated, right? If we go under 100, it's already too late. So we want to say, hey, we want you to go at least 150. So we're going to create a liquidation threshold, and we're going to do this at the top. So we're going to say uint 256 private constant liquidation threshold equals 50. And this means you need to be 150, or no, this means you need to be 200% over collateralized, I think. It might be 150, but we'll find out in the test. So now if we go back down to where we were, to get our health factor, we're not just going to divide these two. And even this doesn't really work, because if we have 150 over 100, 150 divided by 100 is equal to 1.5. Decimals don't work in Solidity, so it would just be 1. I guess that would work, but we want to know exactly what the health factor is, right? With precision. So first off, let's, instead of just doing this, let's say uint 256 collateral adjusted for threshold equals the collateral value in USD times liquidation threshold, and then we should divide by 100, right? Because the liquidation threshold is multiplying, it's making our number much bigger. So we should divide by 100, as I don't like floating numbers. So we'll do uint 256 private constant liquidation precision equals 100. So we'll go back down, divided by the liquidation precision. So now we have this collateral amount adjusted for this threshold, right? So now you can kind of think of it as, instead of, say we have $150 of ETH divided by $100 of DSC, right? This would be 1.5, but now they need to multiply by 50 as well. But now this collateral value is multiplied by essentially 1 over 5, right? Let's do the math here, right? If we had, say, $1,000 of ETH, we just times that by 50, which gets us to 50,000. But then we divided by that by about 100, which equals 500. So if we had $1,000 of ETH times 50 equals this, divided by 100 is 500. Same thing with this example down here. If we had $150 worth of each ETH, we say 150 times 50 equals 7500 divided by 100 equals 75. And then if we do 75 divided by 100, that is going to be definitely less than 1, right? So we're basically saying with this 50 threshold, 50 over 100 is essentially 1 over 2. We're saying you need to have double the collateral in here. So yeah, so now that I'm talking it out loud, this 50% liquidation threshold means we need to be 200% over collateralized, right? We need to have double the collateral that we have the minted DSC. Anyways, so a whole bunch of math. Hopefully this makes sense. If not, definitely work with your AI to make sure this makes sense, or ask questions in the discussion, right? I know some of this math can get a little bit tricky here. So collateral adjusted for threshold. And now we can return the collateral adjusted, this collateral adjusted for threshold times precision divided by that total DSC minted. And now this will give us our true health factor. And if this is less than 1, you can get liquidated. Now, this is one example, right? Let's look at another example. Let's say, I guess this is 2 examples. So let's say they have $1,000 worth of ETH and 100 DSC, right? So let's do the math here. 1,000 times 50 equals 50, 1, 2, 3, divided by 100 is equal to 500, 500 divided by 100, which is definitely greater than 1, right? 500 divided by 100 is 5. So this person with $1,000 of ETH deposited and 100 DSC minted would have a health factor of 500. Nice. So now that we have a health factor, we can actually finally do this revert if health factor is broken function, where we say, we can even put this above this as kind of like a pseudo nat spec. We could say uint 256 health factor equals underscore health factor of the user. And we say if the user, excuse me, actually let's do user health factor. And if the user health factor is less than some min health factor, which is going to be 1 health factor. So let's go ahead and create this. Let's go to the top because we hate floating numbers. Unit 256, private constant min health factor equals 1. If the user health factor is less than the min health factor, then we're going to go ahead and revert. I don't love this. We're going to do DSC engine __ breaks health factor. We're going to pass in this health factor that we break with. Boom. New error. Scroll to the top. Error. Engine breaks health factor. Unit 256. Health factor. Backdoor. All right. Looks like we still have some red here. What did I forget? Okay. Revert if health factor is broken. Underscore like this. Boom. Now it looks like nothing's red. Let's just make sure. Forge build. Successful. Nice. Okay, where were we? Mint DSC, okay? Mint DSC. So we added some more DSC minted. And if adding this DSC breaks the health factor, because breaks the health factor, we should revert. We should not let anybody mint DSC if they're going to cause themselves to get liquidated. I mean, we could go ahead and let them do it, but like, let's not, because that's not a very good user experience. Now, what we want to do is we want to actually mint the DSC. So this is where the DSC has this mint function that's only owner, and the owner of this is going to be the DSC engine. Now we could say, and if we look at this mint function, it returns a Boolean. So we'll say bool minted equals I_DSC dot mint. And what does it take for parameters? Address 2 and amount. So address 2 is going to be message.sender. And amount is going to be amount DSC to mint. And then we'll say if not minted, we'll just say revert DSC engine __ mint failed, and which is a new error. So we'll scroll up to the top. Error DSC mint failed. Okay, cool. So now we have a mint function. And we have a deposit function. So we can deposit collateral, we can mint DSC, but additionally, we can get account information, we can calculate someone's health factor, we can calculate the USD value of these different tokens. So at this point, I'm like, oof, I have no idea if what I'm doing makes any sort of sense. I want to make sure I write some tests here. So this is where we could go ahead and create a new folder, unit tests. And if you wanted to, you could skip writing the scripts and just kind of deploy in your unit tests and then do some integration tests. But I'm just going to have my unit tests also be my integration tests for this one. So let's go ahead. Let's write a script. Deploy dsc.s.sol. You already know the drill for this. SPDX. License. We can even zoom in a little bit. Identifier MIT. Contract. Deploy DSC is script. Import script from forge std script.sol like that. Pragma solidity 0.8.18 looks good. In here we're going to have our function run external. We've done this 100 times. External, and this is going to return a couple of things. It's going to both return the decentralized stablecoin and the DSC engine, and it's going to return something else, but I'm not going to put it in quite yet. So to do that, we're going to have to import decentralized stablecoin from /src/ decentralized stablecoin.sol. We're going to close and reopen my VS Code. It's being really weird right now. There we go. All fixed. So the two of these, what are we going to do? Well, we're going to do a VM.start broadcast like this. VM.stop broadcast like this. Oh, and we need the DSC engine. Import DSC engine from /src/ DSC engine.sol. And in here, we're going to deploy both of these. So we'll say decentralized stablecoin DSC equals new decentralized stablecoin. Does our decentralized stablecoin have any parameters? It does not. We're also going to deploy our DSCE, our DSC engine equals new DSC engine. This takes a whole bunch of stuff, right? This is going to take, go to the constructor, token addresses, price feed addresses. If we toggle the word wrap, addresses, price feed addresses, and the DSC address. So we have the DSC address. Boom. It's going to be this one. Where do we get the price feed addresses? And you guessed it, we're going to make a helper config. So what does this DSC engine need? Constructor, an array of token addresses, an array of price feeds, and then the DSC address. So where are we going to get those addresses from? You guessed it, a helper config. So new file, helper config.s.sol, spdx, license, identifier MIT, pragma, solidity, 0.8.18, contract, helper, config is script, import script from forge std/script.sol. For now, let's do this on the Sepolia chain. So we'll do struct network config. What do we need in here? We're going to need WETH and wrapped Bitcoin, those price feed addresses and those DSC addresses. Address, WETH, USD, price feed. Address, wrapped Bitcoin, USD, price feed. Again, WETH is the ERC20 version of Ethereum. I've got an example WETH token contract on Sepolia. And if you look at it right here, we go to write contract. It's got this function deposit where you deposit ETH and it'll return to you an ERC20 version of ETH to your MetaMask called WETH. Then whenever you're done with it, you just withdraw your ETH and burn your WETH. Wrapped Bitcoin is something similar, but with Bitcoin. The difference is since Bitcoin doesn't originate on the ETH blockchain, there is some risk in bridging it over, but I'm not going to go into that. That's something for you to look up. So we're also going to need the address of the WETH token itself. We're going to need the address of the wrapped Bitcoin itself. And we're going to need a UN256 deployer key, kind of like what we did in one of our previous lessons. We're going to have network config, public, active, network config. And then we're going to have constructor, like here. We're going to have a function, get Sepolia ETH config, public view returns, network config, memory, this. And then we're going to return network config. We're going to have WETH USD price feed be, let's go to docs.chain.link. Let's go to Sepolia, where's ETH BTC? ETH USD right here. Copy that, paste, comma. We're gonna need wrap Bitcoin USD price feed on Sepolia, Bitcoin USD right here. Grab that. We're gonna need the WETH contract address, which I have here. This is one that I deployed. WETH here. We're gonna need wrapped Bitcoin. And if you're looking for all of these and you want to just copy them out of the GitHub repo associated with this, you can go to SRC. You can go to script, helper config, and they're all in here if you want to just copy paste, by the way. But also wrapped Bitcoin, which I guess is this address. Thought I had a different one. Well, whatever. We're going to use this one. And if it doesn't work, that's fine. We're going to use this one. Then, of course, deployer key, vm.env unit, private key, like this. Okay. And then we're going to do function get or create anvil ETH config, public returns, network config, memory. And we're going to do a little bit of mock deployments here. But we're going to say if active network config dot WETH USD price feed does not equal to the 0 address, then we've already set it. Turn active network ETH config. We're going to do some broadcasting. So we're going to need a couple of mocks in here. We're going to need some mock price feeds and some mock ERC20 tokens. So we're going to need a mock v3 aggregator, which we're going to go to test, new folder, mocks, and I'm going to copy paste a mock from this repo. If you want to copy paste as well, go for it. Test mocks, mock v3 aggregator. Copy this. New file, mock v3 aggregator.sol. Cool. Import that. Import mock v3 aggregator from // test / mocks / mock v3 aggregator.sol. So we have that. We're also going to need some mock ERC20s. We can get those actually directly from OpenZeppelin. So if we do import ERC20 mock from at OpenZeppelin /contracts /mocks /ERC20 mock.sol. And if we command click into this, or you open this up, you can see there's a whole bunch of stuff in here. Like we can mint as much as we want, burn as much as we want, do transfers and stuff. We can do pretty much whatever we want. And that's why it's a mock token. Good for testing with. So down here, vm.start broadcast. We're going to create a mock v3 aggregator, ETH USD price feed equals new mock v3 aggregator. And what does this take for the constructor? It takes decimals and an initial answer. So we're going to scroll up here. We're going to say uint 250, or excuse me, uint 8 public constant decimals equals 8. And we'll say uint, or not uint, excuse me, int 256 public constant ETH USD price equals 2000 E8. And then we're going to do the same thing, but instead of ETH, this is going to be BTC, and we'll make this 1000 E8. ETH USD, scroll down. All right, new mock. What does it take? Control click. uint 8, decimals initial answer, control minus to go back. Decimals, and then the initial answer. Those, okay. Oh, and let's do vm.stop broadcast. Now we're going to do ERC20 mock, weth mock equals new ERC20 mock. What does this one take? Name, symbol, initial account, initial balance. Okay. Say weth, message.sender, 1000 E8. We probably want to do more than, we probably don't want to have these floating numbers in here, but yeah, it's just a mock. It's not a big deal, I guess. Now we're going to copy paste all of this for BTC. We're going to say BTC. It's going to be the wrapped BTC, like that. Stop the broadcast, and then return network config. Weth USD price feed is going to be address. Oh, thanks. GitHub Copilot. Thanks, GitHub Copilot. Thanks, GitHub Copilot. Thanks, GitHub Copilot. And this is actually going to be the default Anvil key, which if you want, you can just go back to here again and copy paste it out of here. Or, you know what? You just run Anvil, scroll up, boom, private key right here. Cancel that. We'll say uint 256 public, or excuse me, int 256 public default Anvil key equals, paste that in, and we'll say, we'll just use the default Anvil key if you're working with Anvil. Okay, nice. So now we have getter create Anvil, get Sepolia. Let's update our constructor. So we'll say if block.chain ID equals 111555111, then active network config equals get Sepolia ETH config, else active network config equals get or create ETH Anvil config. Nice. So we've got a little bit of a helper config here, a little semicolon down here. This looks pretty good. What's wrong here? Sorry, this is a uint 256. Okay, cool. So now that we have a helper config, we can go finally back to our deploy DSC. Let's import that in here. Import helper config from helper config. Right at the top, we'll say helper config equals new helper config. And out of this config, we're going to get all of this with Bitcoin, with Bitcoin, deploy key, etc. So I'm going to say address with USD price feed. Oh, I can even just hit tab and it looks like it has most of it. Yep. With USD, wrap Bitcoin, with wrap Bitcoin, deploy key equals config.active network config. Cool. That's good to me. I'm going to toggle word wrap so that it wraps around. Okay, cool. We have all of those. Now our DSC engine takes an array of token addresses, an array of price feeds. So we can say, so right at the top, let's make those arrays. We'll say address, array, public, token addresses, address, array, public, price feed, addresses. And we'll say token addresses equals with and wrapped BTC, price feed addresses equals with USD price feed address, wrap Bitcoin, USD price feed. Okay, cool. I think that's everything, right? Yeah, so now we can go back to this line now. DSC engine, new DSC engine, and it takes the token addresses, price feed addresses, and DSC. Okay, cool. And then finally, something we haven't really talked about too much, but this decentralized stablecoin, like I said, it's ownable, but it needs to be owned by the engine. So this ownable actually has a transfer ownership function, and we're going to call that to transfer ownership to the engine. So we'll go back to our deploy here. Oh, sorry, this isn't DSC. Maybe address DSC. So then we're going to call DSC.transfer ownership to the address DSC engine. Now only the engine, only the engine can do anything with it. And then we're going to return all these. Return DSC and engine. Nice. Oh, and the deployer key is going to go here. Okay, cool. So the reason we did all this was because I wanted to write my unit tests using actual deploy scripts because I prefer to do that. But like I said, it might be a good idea for you to write unit tests before you write your deploy scripts and then integration tests with your deploy scripts. But in any case, let's go ahead and finally create a test in here. DSC engine test.t.sol. And remember, the whole reason we're doing all this, I know we've been coding a lot, is in the DSC engine. We added a ton of functions in here. Some of them like get USD value, which we definitely want to check. Get collateral account value. We want to make sure minting works. Our constructor works, depositing works, etc. So we're just kind of testing as we go along. Which, like I said, when I'm actually coding this, I did write tests and I did write deploy scripts because I did want to test as I was going, right? I didn't want to have to go back and refactor and rewrite my code if I made some glaring mistake, right? It's really good to test while you're building as well. And to be honest, I feel like it makes me go faster because I have more confidence that what I did was correct while I'm coding. So SPDX, license, identifier, MIT, Pragma, Solidity, 0.8.18, little caret here. Contract, DSC engine test is test, import test from forge std/test. That's all, like this. All right, cool. Function setup, public or external. We're gonna need to deploy our contract. So we're gonna import deploy DSC from //script/deploy dsc.s.sol. Deploy DSC deployer. We're gonna say deployer equals new deploy DSC, like that. Again, I'm using a lot of tabs here. And we're going to say, we're going to need the import decentralized stablecoin from //src/decentralized stablecoin.sol. We're also going to need to import the engine, the SCE from, Again, this is where GitHub Copilot can really make your life a lot easier. Just being able to hit tab here, or just whatever AI that you're working with. Now we're going to say DSC. Let's actually make these. We'll say decentralized stablecoin, DSC, and DSC engine. We'll call DSCE. If that's confusing, you call this like engine or something. I'm going to call mine DSCE. So now our deploy returns DSC and the engine. So we're going to say return DSC, DSCE equals deployer.run. Okay, that looks pretty good. There's a bunch of stuff more for us to do, but at least we have our tests set up here. So one of the first tests that we want to do is this price feed test, right? We want to make sure this get USD value, this math that we're doing here, because we're doing some weird math stuff, we want to make sure this is actually working correctly. So I'm going to set up a little price feeds tests section, price tests, like this. We're going to say function do test get USD value. And here we're going to test our get USD value function. So it gets passed a token address and an amount. So we're going to need to get those tokens that we use to deploy this. We can get that pretty easily from our helper config. So what we can do actually back in our deploy, we can also have this return the config. And just at the bottom, we'll also have a return config, comma config, and config will be the helper config, config, import that, import helper config from .script, helper config.s.sol. Okay, cool. And now we can get the WETH address, and we can also get the ETHUSD. So we'll put those up at the top too. We'll say address ETHUSD price feed, and we'll say address WETH. We'll get those from the helper config. So those are the first two. So it's ETHUSD price feed. Bitcoin price feed goes here. So comma WETH, comma, this is the Bitcoin token, comma, this is the deployer key, equals config dot active network config. Cool. We have the price feed and we have WETH. So now we can finally go down here. We set this function up. So we'll say uint 256 ETH amount equals, let's say there's 15 ETH, right? 15 ETH. If we have 15 ETH times that by $2,000 per ETH equals what? 30,000, 30,000 E18, right? Real simple math. So let's do that. uint 256 expected USD equals $30,000. And we'll say uint 256 actual USD equals DSCE dot get USD value, WETH, and ETH amount. And the reason this should work is because in our engine, we pass the token and the amount, and internally it uses the price feed associated with that token, calls the price to get the amount. And now we should be able to just do assert equals expected USD and actual USD. All right. I know there's a lot of setup just to write this one test, but like I said, I like making sure my deploy scripts are part of my test suite right from the beginning, but it might be a good idea to just do them as integration tests. So forge test -m test get USD value, and it works. Now, I will point out, the first couple of times that I ran this test, I actually failed miserably. I got a number of things wrong, and that's okay, because you will, and that's why you write tests. So I also, while I'm here, let's also write at least one deposit collateral test. So let me copy this, paste it here, because we're going to write a lot of deposit collateral. Deposit collateral tests. Make it look a little bit pretty, at least. Like that. We can do some more simple tests like function test revert, reverts if collateral 0, public. We'll prank a user. So up at the top, we'll do an address public user equals make ADR user like this. Make user capital user. Let's say vm.start prank. our user. Now we'll at least approve the token can go to the protocol. So we'll do ERC20 mock weth. Do we have that imported? Nope. We're gonna have to import that. Import ERC20 mock from at open zeppelin / contracts / what is it? Mocks / or contracts mocks ERC20 mock. Okay. ERC20 mock.sol. ERC20 mock weth dot approve. Address DSCE, some amount. Let's do at the top. Let's make another UN256 public constant amount collateral equals, let's say 10 ether worth of collateral. Down here, we'll approve that 10 collateral, and then we'll do vm.expect revert with DSC engine dot. We're going to need to use that needs more than 0 in here. Needs more than 0 dot selector. And now you guys know what this selector bit means. DSCE dot deposit collateral. Say weth 0 like this, and then vm dot stop prank. And actually this might fail for a different reason, but let's go ahead and try a forge test -m. Oops. Okay, cool. And this actually did pass. Now, if we want to make this a little bit better of a test, we should also mint our user some weth. And we probably should do that right in the setup so we don't have to do that for every single test. So what I'm going to do is I'm going to do ERC20 mock weth dot mint user. We're going to do a UN256 constant starting ERC20 balance equals, and let's say this is 10 ether as well. 10 ether. Starting ERC20 balance. Boom. All right, cool. So now, forge test. All of our tests are passing. Cool. And like I said, I'll do this kind of as a sanity check to make sure that my architecture is even making sense, right? So what we probably also want to do next then is have a test for collateral is being deposited in these data structures. But for now, I'm content with these tests. So I'm just going to go back to writing my contracts. Like I said, there's no one single process, and I don't think I've ever written a smart contract completely in one go. I'm pretty much always writing tests as I'm writing the code. So it is a really good idea to do this. Yes, you do not have to write the deploy script as you're writing your code, but it's something that I like to do. And then, you know what, while we're writing these tests, let's also do -- fork URL, Sepolia, RPC URL. Let's also do this, because this probably will fail actually, because we can't just mint weth out of thin air, and we do indeed fail. Test get USD value. Oh, interesting. That's the one that fails. Test get USD value. This one fails because we're hard coding the expected USD right here. And of course, the price on Sepolia is the actual price, as opposed to kind of this fake price that we're making up. So we should probably update this test to make it more agnostic, right? We probably should update this test so that instead of just hard coding 3000 in here, update this test to use the price of the actual price feed. For now, I'm going to leave it as is, and then I can fix it later for running those fork tests. So where are we now? Okay, so we have a way to deposit collateral. We have a way to mint. We don't really have too many tests here. We're just assuming that this kind of works for now, which is okay, but this is good, right? We're getting somewhere. So we can mint our debt or our DSC. We can actually, now we can get a whole lot of information as well, which is awesome. Let's now combine these two into kind of this main function that we're thinking a lot of people are going to call this deposit collateral in mint USD, right? The purpose of this protocol is to mint this stablecoin, right? Deposit collateral and mint DSC, which is just going to be the combination of deposit collateral and mint DSC. So in here, what this is going to take, it's going to take similar stuff to deposit collateral and address, token collateral address, a UN256 amount collateral, and then also a UN256 amount DSC to mint, right? Like that. And here we're just going to call. So deposit collateral is external right now. We'll make this a public function. So we'll change this to deposit collateral, where we give it the token collateral address and the amount collateral. And then we'll call mint DSC, amount DSC to mint. Boom. So that's all this function does, is just combines the two of them. Oh, and mint DSC is not defined because it's external. We'll make this public as well so that our contract can also call it. Toggle word wrap, put that back on. Okay. And cool. So this is going to be one of our main functions we're thinking. So let's add some nat spec to it. We'll say at param. And this is where GitHub Copilot is really helpful. Token collateral address, the address of the token to deposit as collateral. At param, amount collateral. Yep. At param, that looks good too. And then we'll notice this function will deposit your collateral and mint DSC in one transaction, right? Because otherwise we're going to have to have people call deposit collateral and then mint. But some people, they're probably just going to want to do both at the same time, because that's kind of the purpose of this protocol. Okay, great. So we have a way for people to get money in. How do they get their money out? So we're going to need to write this redeem collateral, right? So in order for them to redeem collateral, let's talk about this. In order to redeem collateral, they need what? One, their health factor must be over 1 after collateral pulled. So we're going to want to put some checks in here to make sure that they have enough money in here. And that's kind of the main thing, right? That's all we really need to worry about. So let's go ahead and start writing this. So first we should let them choose which collateral they want. So address, token collateral address, and then obviously the amount collateral. And we're going to want to add this more than 0 modifier in here for the amount collateral. We don't want them to be sending accidental 0 transactions. And because we're going to be moving tokens around, we'll just do non-reentrant. Better safe than sorry. We can figure out later in kind of like a gas audit if this is even needed. Now I'm going to write this function as if somebody redeeming collateral is the only time they actually redeem collateral. However, we're going to refactor this in the future to make our code much more modular. There's this concept in computer science called dry. Don't repeat yourself. If you find yourself coding the same thing, that should send off a light bulb in your head going, oh, maybe what I'm doing isn't the best practice. So we're going to code this one way, and then I'm telling you right now, we're going to go back and we're going to refactor this in the future. But I want to code it this one way first, just to show you the process that you'll probably go through and how you'll probably refactor it when you come across this yourself. So we're going to code this one way now. Let's do it. We're going to need to pull the collateral out, and we're going to update our internal accounting. So we have this s underscore collateral deposited of message.sender of the token collateral address, right? This is our internal accounting, how much collateral they've added. We're going to do minus equals amount collateral. So this is assuming we're going to pull it out. If they try to pull out more than what they have, we're relying on the Solidity compiler a little bit to throw an error, right? If in their balance they have 100 and they try to pull out 1,000, right, it'll revert, because as of newer versions of Solidity, they don't let you do this unsafe math stuff, which is awesome. It saves us a lot of hassle. So, and then since we're updating state, we're going to emit an event. Let's call it collateral redeemed. We'll say it's message.sender. So from message.sender, the amount collateral, the token collateral address, like this. So we're going to go to the top. We're also going to refactor this event, but you'll understand why later. Event collateral redeemed, address indexed, user address indexed, token uint 256 indexed, amount, like this. Okay. Control minus, go right back down to where we were. Okay, amount collateral. Oh, what's wrong with this? Oh, these are backwards. Okay, cool. So now all we have to do is return the money. Well, how do we do this? So we want to follow CEI, right? Checks, effects, interactions. Checks, effects, interactions. But we also want to make sure the health factor is good after collateral is pulled. And this is where sometimes you'll see CEI be violated. When I need to check something after a token transfer has happened, sometimes you'll see this CEI be violated a little bit. And what you could do is you could do like calculate health factor after and then like simulate it. But a lot of people choose to not do this because this is really gas inefficient. So what a lot of people do is they just go ahead with doing the token transfer first and then checking this and reverting if this happens. And that's usually fine though, because we're going to revert the transaction if it's bad, right? So what we'll do is we'll do this token transfer and then we'll make sure the health factor is okay. So you know how to move tokens around. So we'll say bool success equals IER 20 token collateral address dot. We can just do transfer instead of transfer from, since transfer is when you transfer from yourself. Transfer from is when you transfer from somebody else. So dot transfer, and we're going to be sending it to message.sender, and we're going to send amount collateral. And then if not success, if not success, we're just going to go ahead and revert DSC engine. We'll just do transfer failed like this. And then we want to make sure that the health factor isn't broken. And we have written a function that does that already called revert if health factor is broken. So we can just grab this, go back up to our redeem and just do revert if health factor is broken for the message.sender. Okay, cool. Like I said, we're going to refactor this very soon. Okay. But it looks like this is actually pretty good for redeeming collateral. Now, this revert if health factor is broken is a little bit troublesome with just this raw redeem collateral. Let's say I put $100 in and then I mint, let's say $20 worth of DSC. Put $100 worth of ETH in and I mint $20 worth of DSC. Let's say I'm done. Like I want to burn all my DSC and I want to withdraw all of my ETH. Well, if I try to redeem all my ETH, it'll break, right? It'll break my health factor. So what I need to do first is I need to first burn back my DSC, and then I need to redeem ETH. So it's a kind of this 2 transaction process here. This kind of stinks. So let's turn it into a 1 transaction process. So we're going to combine redeeming your collateral with also burning your DSC, which means we're going to need to create a burn DSC function. And we're also going to refactor this in a little bit, but I'm just going to write it as if this is the only burn DSC function for now. So let's have people burn their DSC, right? This is when they say, hey, I'm done with these tokens. And this will reduce that. If we scroll up to the top, we have this mapping here, SDSC minted, it'll reduce this SDSC minted. So essentially it'll reduce their debt in the system. So burn DSC, we're going to add some modifiers here. There should be more than 0. Amount. So we want to do a U256 amount so they can burn as much as they want. And then what we're going to want to do is we're going to say S_DSC minted of the message.sender is going to minus equal amount. So we're going to remove that debt, remove that DSC minted. And then we're going to do a little bool success equals I_DSC dot transfer from DS message.sender to address this amount. And we could also send this to the 0 address, but we're going to just send it to our address for now because the decentralized stablecoin ERC20 burnable has its own burn function. And we're just going to call the burn function directly on the token itself. But first, we're going to take it from them, bring it into our contract, and then we're going to burn it. So if not success, then we'll revert DSCE transfer failed like this. And this conditional is kind of hypothetically unreachable because if the transfer fails up here, we're going to throw the transfer from fail error. But let's say this DSC token is implemented wrong. Great. We kind of have this backup. But so they're going to send their DSC token here. Then we're going to call IDSC.burn amount. Now, since we're burning DSC, question is, do we need to check if this breaks health factor? Well, probably not, right? Because we're burning DSC, we're burning debt. It's highly unlikely that burning your debt, removing your debt is going to break the health factor, right? We probably don't ever need this, but I'm just going to add this in here for now, just as a backup. In a gas audit, we can figure out if we actually need it. I don't think this would ever hit. And this is where, when I do go to an audit, when I do go to a security professional, I can make sure to point this line out. Say, hey, I don't think this line will ever hit, and I'm thinking of pulling it out. What do you think? Right? It's good to call these out in your comments so that when you do go to a professional who knows, they can help you out, figure this out. So for now, we're going to put it in here, although it's highly likely we don't even need this. And we're going to refactor this function pretty soon anyways. So we have this burn DSC function. We're going to make it public because we're going to be burning DSC and redeeming collateral at the same time. So now we have redeem collateral. We have burn DSC. Now we can write this redeem collateral for DSC, where we send DSC and redeem collateral at the same time. And so in here, we're going to say address token collateral address uint 256 amount collateral uint 256 amount DSC to burn. We'll have this be external. So then we're going to call burn DSC with the amount of DSC to burn. We're also going to call redeem collateral. So we're going to burn the DSC first, and then we're going to redeem their collateral with the token collateral address and the amount collateral. Redeem collateral. Oh, this is external. Let's make this public. Let's go back. And then, of course, we should revert if health factor is broken. But if we look, our redeem collateral function currently does this already. So we don't need to do that here. So I'm just going to put this comment. Redeem collateral already checks health factor right here. And then we'll add a little bit of nat spec here. So at param, boom. That's not even the right param. Token collateral address, the collateral address to redeem at param, amount collateral, the amount collateral to redeem at param, amount DSC to burn, the amount of DSC to burn. This function burns DSC and redeems underlying collateral in one transaction. Okay, cool. Are we going to refactor these two functions soon? Yes, absolutely. But I want you to understand why we're going to refactor them. So we're going to leave them in as they are for now. Okay, cool. So this is looking pretty good. So we have a lot of stuff in here. We have deposit collateral and mint DSC. So people can mint our stablecoin by depositing collateral. People can just straight up deposit collateral. People can then redeem their collateral for the DSC that they minted. They can just straight up redeem collateral. They can just straight up mint DSC so long as they didn't break the health factor. They can burn DSC to go help their health factor. I don't think this line will ever hit. We've got to do a couple of more things here. Most importantly, we got to do this liquidate function. So this liquidate function is kind of the key thing that holds this whole system together. If we do start nearing under collateralization, we need someone to start liquidating positions, removing those positions. We need somebody to basically call redeem and burn for you if your health factor becomes too poor, right? Because the worst thing that would happen is, let's say there's $100 worth of ETH backing $50 worth of DSC, and then the price of ETH tanks to $20, right? $20 of ETH backing $50 of DSC. Well, now the DSC isn't worth $1, right? The DSC then is going to be worth, whatever 20 over 50 is. So we can't let this happen, right? We need to make sure we liquidate people's positions. We remove people's positions in the system if the price of the collateral tanks, okay? And this is where liquidation comes in. So we say if someone is almost under collateralized, we will pay you to liquidate them. We have kind of this gamified incentive system here where people can get basically free money for removing other people's positions in the protocol. So in this situation up here, as the price is going down, let's say the price goes down to $75, backing $50 of DSC, this is way lower than our 50% threshold. So what we're going to do is we're going to let liquidator take this $75 backing, takes the $75 backing and pays off the $50 DSC and burns off the 50 DSC. So we're going to have somebody able to take their money in exchange for them making sure our protocol stays collateralized. So that's what this liquidate function is going to do. So first off, they're going to be able to choose the collateral, the user that they want to liquidate, and the UN256 debt to cover. And they'll be able to track the users and their positions by listening to these events that we've been emitting, which is exciting. We're going to definitely want a lot of NAT spec for this. So at param, collateral is going to be the collateral to liquidate, or better yet, the ERC20 address, collateral address to liquidate from the user. At param, user, the user who has broken the health factor. Their health factor should be below min health factor. At param, debt to cover is going to be the amount of DSC you want to burn to improve the user's health factor. Okay, we're going to add a lot of at notices here. At notice, you can partially liquidate a user. Just so long as you improve their health factor, that's all we care about. At notice, you will get a liquidation bonus for taking the user's funds, right? We want to incentivize them to actually do this, right? If we say, okay, cool, you'll get the $50 back for paying off the $50 debt, it's going to be hard to incentivize people to do that. But if we say you get all $75 and all you have to do is pay back $50, then that's going to be a bonus that they should be able to take to incentivize them to do this. At notice, this function working assumes the protocol will be roughly 200% over collateralized in order for this to work. Why? Well, because in this scenario, if this drops down to $20 backing $50 of DSC, and if I pay back the 50 DSC and I get $20, well, then I'm not going to do that. I'm not going to pay $50 to get back 20. So this whole system only works if the system is always over collateralized. The only way we can give liquidation bonuses is if we're over collateralized. So the only way we can incentivize people to liquidate poor users is if we are over collateralized. So we could say at notice, a known bug would be if the protocol were 100% or less collateralized, then we wouldn't be able to incentivize the liquidators. And then we would just say, like, for example, if the price of the collateral plummeted before anyone could be liquidated. So hopefully this makes a lot of sense. If this doesn't make sense, you know what to do. Ask ChatGPT, ask in the discussions forum, Google it, use the resources that you have to your advantage. Yes? Yes. Okay, good. So debt to cover. We probably want to do more than 0. Very lame if they did just 0. So we're going to do more than 0 here. We're going to be moving tokens around. So we're going to do non-reentrant as well. Maybe we'll do some more modifiers, but that looks pretty good to me right now. So now, what do we need to do? Well, we need to do a bunch of stuff here. Well, we first need to check health factor of the user, right? Is this user even liquidatable, right? Remember, we want to do follows CEI, checks, effects, interactions, right? We always want to follow CEI. So we should do some more checks here because we should only liquidate people who are liquidatable. So first thing we should do, UN256, starting user health factor equals _ health factor of the user, right? Because we have this health factor function, which gets that health factor. And what we can say, and let's put this above. Now we'll say if the starting user health factor is greater than or equal to the min health factor, which what's our min health factor again? 1. Actually, it should be 1E18. And we're definitely going to write some tests to make sure this is correct. So 1E18, because we're using our precision here. What else are we doing health factor? Why don't we write tests elsewhere? Revert if health factor is broken. Oh, I guess we haven't tested this yet. Well, I guess we're going to be testing it very soon. Make sure that that health factor bit is right. So if the starting user health factor is greater than or equal to the health factor, then we revert, right? Revert DSC engine __ health factor, okay, right? Health factor is fine. Got a new error. Let's go to the top, scroll down. Error. Health factor, okay. Back. Go back down here. Remember, I'm doing control minus to go back. It might be something else depending on your setup. So let's do some thinking. So now we have their starting health factor. What do we want to do? We want to burn their DSC debt, right? We want to reduce the amount of DSC they have and take their collateral. We want to remove them from the system, basically, right? So how do we do that? Let's say they have $140 of ETH deposited and $100 of DSC. With a setup like this, their health factor should be below what it currently is. What we could do is we can say, okay, we're going to cover. So this is what bad user has. That means we could say, okay, we're going to cover debt to cover. It's going to equal that $100. And we need to pay back $100. So we're going to have to get a UNT256 collateral or token amount from debt covered. So we need to figure out, okay, if we're covering $100 of debt, $100 of DSC equals how much ETH? So we're going to pay back $100 of debt, and how much ETH is that? Okay, how much ETH is that? So we're going to get the token amount of debt colored, the ETH basically, equals, and we're going to have to do some pricing stuff. We're going to have to say it equals get token amount from USD. So we're going to add the collateral and the debt to cover. So we're going to figure out, okay, how much of this token are we going to get, right? We're going to cover $100 worth of debt. How much in ETH or whatever collateral token is $100 worth of debt? So we're going to have to create a new function, get token amount from USD. This is going to be a public view function. So we're going to scroll all the way down here, public and external view functions. Function, get token amount from USD. And we're going to pass an address token or collateral, UNT256 USD amount in way. This will be a public view returns UNT256. And we're going to have to do some price feed stuff. So we're going to need, what are we going to need to do? We're going to need to get the price of ETH or the token. And then we're going to have to say, okay, so if the pricing is dollar per ETH and we have ETH, how do we get the dollar? Well, if we do some math here, let's say it's $2,000 of ETH and we have $1,000, right? How much ETH is that? We're going to do the 1,000 divided by 2,000, which is going to equal 0.5 ETH, right? So we're going to do this number divided by this number. The amount, the USD amount in way divided by the price. And that's how we're going to get this token or collateral amount from the USD amount. So we'll say aggregator v3 interface price feed equals aggregator v3 interface of S price feed of token. Oh, wow. It even filled in a lot of this for me. That's great. Yes, this looks right. So we're going to get the price feed of the token and get call the latest round data on it to get the price here. And then we're just going to do this right here. So we're going to say the amount USD in way divided by the price, or UNT256 price. Is this the full story? No, absolutely not, because we should always multiply first. So we're going to do this times our precision. Then we can divide by the price. But is that the whole story? No, because the price has 8 decimal places and we need it to have 18. So we're going to do additional feed precision like this. Does that look right? So if we have, let's say we have 10 E18 for amount in way, we're timesing that by 1 E18 like this. We're saying divide that by the price. Let's say the price is $2,000, $2,000 E8 times the 1 E10, the additional piece here. This looks pretty correct. Do we need anything else? Let's even just pull out the calculator, right? So 10, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by 2, 1, 2, 3, 2,000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8 equals this number, which is probably a half, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. 0 point. Is that right? Oh, because it's $10, duh. Yes, this is right. I was like, I thought we did $1,000, but this is $10. Yes. Okay, cool. That looks good to me. Great. And then obviously we're going to test this soon to make sure that it is right. So we have this function where we get the token amount from the USD. So we're saying, hey, we're going to cover $100 of your debt or something like that. How much ETH is $100 worth of your debt? Maybe it's, if the price is $2,000, we would do 100 divided by 2,000, 0.05 right there, right? So this is going to be something like 0.05 ETH or whatever it is, right? Cool. So we have how much ETH we need to take away from their collateral as a reward for paying back this DSC. But additionally, we also want to and give them a 10% bonus, right? Because we want to incentivize them. If it's just a 1-for-1, they're not going to want to do this. So let's say we're going to give them a 10% bonus. So we are giving the liquidator $110 of WETH for 100 DSC, whatever $110 of WETH is going to be. We should implement a feature to liquidate in the event the protocol is insolvent. We're not going to add that in yet though, but we should probably add something like that. And then add sweep extra amounts into a treasury, but we're not going to add either one of those. So don't worry if that's confusing. Don't worry about that. We're not even going to implement that anyways. So we'll say UN256 bonus collateral equals this token amount debt covered times some liquidation bonus that we haven't defined yet, although we're going to do 10%, divided by 100, but I hate these floating numbers, so we're going to do something better than 100. We're going to do liquidator precision, which is 100, and we'll do UN256 private constant liquidator bonus equals shun bonus. It's going to be 10. Be like, this means a 10% bonus. And since it's going to be 10 divided by 100, that's going to be 10%. Let's go back down. Liquidation bonus divided by liquidation precision. So the bonus collateral is going to be 10%. So let's say it was 0.05 ETH. We're going to multiply that by 0.1, right? Because we're going to multiply first and then divide to get 0.005 ETH. So as a total, or that's not quite right. It's going to be 0.005. 0.05 times 0.1 equals yes. So that means they're going to get 0.055. Is that right? I think that's right. Why am I being bad at math? Time 0.1. Yes. Okay, cool. Great. So that's what they're going to get, this bonus collateral. We got to add the bonus collateral to the actual collateral. So we're going to say like UN256 total collateral to redeem equals token amount from debt covered plus bonus collateral, like that. And now we need to redeem this amount of collateral for whoever's calling the liquidate function, right? We need to redeem that collateral. And then we also need to burn the DSC from this user as well. So we need to give them the collateral and burn the DSC that they're covering with their debt to cover. Now, though, if we look at our redeem collateral function, which is public right now, we can see as inputs it takes token collateral address and amount collateral, right? And it is hard coded to message.sender. Our third-party user isn't the one with the bad debt, right? We need to redeem a random person's collateral. So what we can do is we can refactor this code so that there's an internal redeem collateral function that can redeem collateral from anybody, right? And only very permissioned functions can call redeem collateral. So what we're going to do is actually we're going to take all of this code and we're going to change it and we're going to delete it and we're going to put it into a different function all the way down in private and internal functions here. We're going to make a function underscore redeem collateral. And this is going to be an internal function where we can actually redeem collateral from anybody. And as input, this is going to take address token collateral address, same as the regular redeem collateral, also the UNT56 amount collateral, but we're going to add address from and address to. So this way, and this is going to be private. So this way, somebody can liquidate an address from and then get the rewards too. And this is where I'm going to paste all that code we got from above. And I think this looks good. Yeah, we're just going to paste that code exactly like this. Instead of doing message.sender, this is just going to be from and emit collateral redeemed. We're going to update our collateral redeemed to redeemed from. We'll do address redeemed from, address redeemed to. We'll do the token, and then we'll have amount not be indexed. So from, to, token, and amount. So now we got to refactor some of these collaterals. So from, when we do just the regular redeem collateral, we'll update this in a minute, actually. Yeah, we'll update that in a minute. So in this internal function, it's going to be from to address collateral. And then we're going to transfer the tokens to whoever the to is. So this is going to be like the liquidator, amount collateral, and do that. And now we're going to use this internal function up in our regular redeem collateral function that we just created, right? Up here, oh no, up this one. Up here, we're going to dump all this and just use this underscore redeem collateral. And for here, we're just going to say message.sender. So from message.sender to message.sender, token collateral address, amount collateral. And now that we have this internal function, we can use this redeem collateral bit down in our liquidate, which is down here. We can now just say redeem collateral from the user that's being liquidated. So from user to whoever's calling liquidate here. So it's going to be message.sender, the collateral token that we're liquidating, and then finally the total collateral to redeem. So this is why I said we were going to do a little bit of refactoring soon, right? We generally only want to redeem collateral from and to the same person. However, when we're doing a liquidate, we're going to redeem to whoever's calling the liquidate. So they're going to get that reward. The total collateral to redeem is that total amount debt to cover plus some bonus here. And now we actually need to, we need to burn the DSC now. So right now, if we look up burn DSC, we have this public function, which just does the same thing. It just burns from message.sender. We're gonna have to do the same here. We're gonna wanna make an internal burn DSC function that allows us to burn from anybody, right? So if we scroll down to where we're doing those private functions, or scroll up, so we have this internal redeem collateral. We also are gonna need an internal burn DSC. So function underscore burn DSC, uint 256 amount DSC to burn, address on behalf of, like, whose DSC are we burning for, whose debt are we paying down, and then address DSC from, where are we getting the DSC from? We have private, and we can go back to the burn DSC, this burn DSC function, right? And same thing, we can just copy all of this, go back to our internal burn DSC function, paste this in here. We're going to want to update this, right? Instead of message.sender, this is going to be on behalf of. We're going to take away their debt. We're still going to do this, but instead of message.sender, it's going to be DSC from, and it's going to be amount DSC to burn. This is still fine. This just needs to be amount DSC to burn. And we don't need to check health factor yet because this is going to be our internal function. So we might even say, like in the comments here, low level internal function, or at dev, low level internal function, do not call unless the function calling it is checking for health factors being broken. So now we have this burn DSC. We can go back up to our burn DSC function. We can just swap, delete all of this, call burn DSC, and this is going to be message.sender amount, right? If somebody calls burn DSC themselves, great. We'll just have them call this burn DSC amount to burn on behalf of themselves, from themselves. Oh, it looks like I got this backwards. Amount should be the first one. Okay. And now we have this burn DSC function. We can go down to liquidate and we can call burn DSC. What are the amount on behalf of from? So the amount is going to be this debt to cover. Amount on behalf of is going to be the user, and the one who's going to be paying this is going to be message.sender, right? Because it's whoever's the liquidator, whoever's calling liquidate is going to be the one who's paying down the debt to cover, right? Paying back that minted DSC. And now, since we're doing these internal calls that don't have checks, we absolutely need to make sure we're checking this health factor is okay, right? So we're going to do uint256 ending user health factor equals underscore health factor of the user. And if the ending health factor is less than or equal to the starting health factor, right? If we didn't improve the health factor, we should revert DSC engine underscore health factor not improved. Copy this, go to the top. We'll do error, DSC engine health factor not improved, go back down. So if we don't improve the health factor, we should 100% revert. And then also, if calling this liquidate function, if paying down some debt and doing all this stuff actually hurts the liquidator's health factor, we should also revert, right? So we should also call revert if health factor is broken for the message.sender, right? If this process ruined their health factor, we shouldn't let them do this, okay? So we're following checks effects interactions here. For the most part, these two functions are making external calls to external contracts, right? And then we're doing kind of like a check afterwards. Again, this is a bit of a trade-off. We could calculate before and then run this, but that's kind of gas inefficient. We're just going to check after we do all this. Hey, just make sure that the health factor is okay. Make sure that we didn't break anyone's health factor. So now we have this liquidation function, which is incredibly powerful and kind of what ties this whole thing together, right? There's an incentive here for people to call liquidate so that our protocol is never insolvent, right? And I know I've been kind of throwing around a lot of these financial terms, but our protocol always has more collateral than it has minted DSC. The value of the collateral should always be more than the minted DSC, always. Incredibly powerful function. We're obviously going to be testing the living hell out of this, right? Because we want to make sure it actually works. Woo! Okay, what do we need now? Oh, well, it looks like we broke some stuff. Oh, this needs a semicolon. What else do we break? There's a little red thing down here. Let's go fix it. Amount. This should be amount DSC to burn. Got a couple more red things. Redeem collateral. User message to sender. Redeem collateral. Oops, we did these backwards. I'm going to copy these. Put these at the front. Okay. Oh, looks like that fixed pretty much most of this. I don't see any more red stuff on the side here. So we're going to go ahead and run forge build. Make sure everything's at least compiling. Awesome. Maybe we'll even run forge test. I don't think this would have broken any tests. Looks like those are working fine. But all right, we're doing some fantastic work. And like I said, at this point, I probably would be running tests with this, but we're almost done with all of our code here. So we're just going to keep going, right? And this code's starting to look pretty darn good, right? We've got these amazing nat spec comments in here. We've got comments all over the place. Maybe these probably should be cleaned up a little bit, but that's fine. We've got this little dev thing, a shout out saying, hey, don't let anybody call burn DSC without checking the health factor, right? This is really good to tell auditors and security professionals about this, right? It's really good to call this out. We've now have this internal redeem collateral function, so it can be used for the liquidate or the redeem collateral. Health factor, it looks like pretty much all the functions that we originally wrote are working in here, right? And the reason, again, that this all works is because when we mint DSC, we can only mint as much as we have collateral in the system. We're setting this exchange rate essentially for our protocol. Hey, cool, you have $100, you have $150 worth of ETH deposited. Great, you can mint $100 worth of DSC. So it's this exchange rate that we're setting, which is maintaining the price. Let's just double check that we have kind of most of the functions that we want here. And let's also check that they're in the right place. So we go to the top here. Got a whole bunch of errors. That's great. Got a whole bunch of constants because we hate magic numbers. We have a mapping of price feeds, a mapping of collateral deposited from user to token to the amount they have deposited. We have their debt or their DSC minted, collateral tokens, the IDSC token. We've got some events in here, a couple modifiers, some functions. We've got a way to deposit collateral and mint DSC in one transaction. We've got a way to calculate health factor. I'm going to tell you right now, there's actually a bug in here. I'm not going to tell you what that bug is yet, though. Maybe you can figure it out. We've got some view functions down below. We're probably going to add more as we write tests, but this is looking pretty darn good. Now, like I said, there's at least one big bug, and there might even be, and there's likely more, but there's at least one big bug in here. So now would be a good time to take a break, because after this, we're going to go deep into writing tests for this protocol. We're going to write some new tests, and we're going to show you some really advanced testing methodologies. So take that break, go for a walk, and I'll see you in a few. All right, so let's pull up our terminal here. Forge, coverage. Ooh, we got some work to do. All right, well, no time like the present. Let's get into it. So we have some price feed tests over here. We probably also want to set up some constructor tests, right? We want to make sure that stuff is being initialized correctly. So let's copy that. We'll do constructor tests like that. We'll fix this so our ADHD doesn't go crazy. And we'll do function test something. What are we testing? Let's go down to the constructor here. And what should we be testing? Okay, well, we're doing this revert here. So we should make sure we actually are reverting correctly when the lengths aren't the same. So function test reverts if token length doesn't match price feeds. Public, zoom in. We're going to be in here a while. So function this. Now we're going to create some address arrays. Address array, public token addresses, address array, public price feed addresses. We're going to say token addresses dot push. We're going to push weth into here. Feed addresses add dot push eth_usd price feed, and we're going to push 2 in here. Oh, cool. BTC. What do we have? I guess we should pull BTC USD price feed. Let's get this too. So eth_usd, BTC USD price feed. Okay. Oops. Price feed addresses. So we'll push the 2 of those in there. Now we'll do vm.expect revert DSC engine dot, what's the name of the error? I'm going to copy this. Boom, dot selector like that. Doing some toggle word wrap now. Expect revert. Now we call a new DSC engine with the token addresses and the price feed addresses. Oh, what else goes in the DSC? Oh, we also need the address DSC, right? Address DSC. So this should revert. Let's see. Forge test-m. Nice. Okay, that's passing. All right, cool. Price feed tests. We're testing getting the USD value. I think we had another one down here, right? We had something like get token amount from USD. We sure did. This is a public view. So let's test this one as well. Do function tests. And I usually just like to paste the function names, especially when they're like this. Public. So we're going to do basically the opposite of this. This got the USD value of some ETH amount. We're going to do UNT256 USD amount, right? Equals, let's say 100 ETH, 100 Ether. And then UNT256 expected WETH. Do a little bit of math here. If it's $2,000 per ETH and we have $100, we're going to do 100 divided by 2,000. So 100 divided by 2,000, 0.05. So we can say expected WETH is 0.05 Ether. Now we'll do UNT256 actual WETH equals DSCE dot this function with the lowercase, pass in WETH, and then the USD amount, assert equal expected WETH and the actual WETH. The two of them should be the same. Let's test it out. Forge test -m. Nice, that passed. All right, let's keep going. Deposit collateral tests. Test revert if collateral is 0. That's good. What else? Let's go to this deposit collateral function. Okay, we should also revert here. We're basically just going to go through this whole function and kind of test each line. We just tested this one. Let's test this one. So this will be something like function test reverts with unapproved collateral public. We'll make an ERC20 mock, some RAN token, right? We'll just make some silly token. New ERC20 mock. RAN will be the name. RAN will be the token. Do we have a user in here? I think we do have a user, right? Okay, yeah, we do have a user. Let's give this money to a user, and then we'll give them some starting amount. I think we have starting ERC20 balance or amount collateral. Yeah, we'll do amount collateral. Give them the amount collateral. We'll do vm.start prank this user who has this token, and they're going to try to deposit this collateral, and we're going to expect it to revert. So vm.expect revert, and this error here is allowed token right now doesn't take any parameters. So that's easy enough for us. Let's just copy this. We'll do dsc engine dot this dot selector, and then we'll call the deposit collateral. So dsce dot deposit collateral, address of that RAN token, right? RAN token or random token. We'll do amount collateral as well. So it'll just be that whole amount. And then we can do vm.stop prank, and that should work. Forge test -m. See if that's correct. Yep, looking good. All right, let's keep going. What else? What's next? Deposit collateral. Not that one. Okay, did this. Non-reentrant. We could go ahead and test reentrant. I'm going to skip doing that for now, but we probably do want to do some reentrancy tests at some point. But yeah, I'm going to skip them for now. And all right, cool. So then we can start testing some of this. So if they deposit collateral, we should see that they actually do this. We should see that they emit an event. Let's go ahead and do that. So let's do function test can deposit collateral and get account info. Because once they deposit, we have this get account info. Oh, it's private right now. So let's actually go to the bottom. Let's create a public version of that. So we'll do function get account information. This will be external view. Return this account address user, returns these two. I'm going to copy this, go back down. External view returns these two things. And we're going to say total DSC minted, comma, collateral value in USDC equals this internal function. And that should be good, right? Oh, we're going to do, instead of message.sender, we'll do address user. This, paste the user in here. So now we can get the total DSC minted and their collateral value in USD from an external view function. We should be able to get that information. So let's have them actually deposit collateral in here. And since we're going to be doing a lot of deposited collaterals, we know we can actually make a modifier called deposited collateral. This bm.start prank user ERC20 mock WETH. In order to deposit WETH, we need to approve address DSCE, comma, amount collateral. And we're going to do DSCE.deposit collateral, WETH, amount collateral, bm.stop prank, bm.stop prank, underscore like this, modifier, right? And we'll have this can deposit collateral and get account info. We'll have them deposit collateral. And we'll now get that account information. So we'll say UNT256, total DSC minted, UNT256, collateral value in USD equals DSCE dot get account information from the user. From the user. And now what we're going to say, we're going to make sure these two numbers are correct. The total DSC minted and the collateral value in USD. They should have minted no DSC. So UN256 expected total DSC minted. Yep, equals 0. UN256 expected collateral value in USD equals, this is going to be that DSCE dot get token amount from USD with collateral value in USD. So expected collateral value should just be this function. Then we can say assert equal total DSC minted should be this expected total DSC minted. And then we can do assert equal collateral value in USD. It's going to be this expected collateral value in USD. All right, clear. Forge test-m. All right, we have a fail. You know what to do. We're going to run it again. -vvvv. Let's see what we messed up here. It says the assertion failed. Left is this number and right is a much smaller number. This is why it's not cool to do two types of asserts, but I know it's the second one. So we're saying the collateral value in USD is this, but the right side is expected collateral value is going to be this. So let's see what's wrong here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So it's saying collateral value in USD is 20 grand. Does that make sense? Well, it's 10 Ether times $2,000 equals 20 grand, right? So that is, so the collateral value in USD is right. It looks like my right is wrong. Collateral, expected collateral value in USD, DSC.from token amount, WETH. Oh, what the heck? Why am I doing that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So it's saying that $20,000 is equal to 10 ETH. So I don't know why I'm calling this. Oh, this is actually expected deposit amount. And we shouldn't be comparing these two. This should be compared to the amount collateral, right? So 10 is how much collateral we're putting in here. And then collateral value in USD. Yeah, that's correct. So we're using this collateral value in USD to get the expected deposit amount. That looks more correct. Okay, cool. Forge test-m. And this is one of the kind of weird parts about writing tests, right? Okay, cool. We fixed it. Sometimes your test is wrong, like what we just showed here. I wrote my test wrong, but sometimes your code is wrong. And that's what these tests really should be testing. Hey, when is the code actually wrong? We're making some progress. Forge coverage. Not a whole lot of great coverage here. Let's keep going. So instead of me just kind of walking you through the rest of these tests, you know how to write these tests. In this file, I'm not really going to show you any more unique tests, right? But like I said, there is at least one glaring issue in our DSC engine.sol. There's a big issue in here, right? We definitely need some more getter functions as well. So write getter functions as you test, but there's at least one giant issue. So what I'm going to do now is, instead of me literally walking you through the rest of these tests, I mean, you can see all the tests in here, is I'm going to challenge you to write these tests yourself to get this forge coverage up. Remember, you can do forge coverage to obviously see what's going on. We're focusing on this one right now. You can also do forge coverage -- report to see -- report debug to actually see the exact lines that are missing, right? And all these things are just kind of line items, whatever. IC doesn't matter. Scroll. Okay, these are the ones that are actually issues, right? Which one's this? Oh, that's essential. That is the decentralized stablecoin. We want to write tests for that as well, but let's just focus on this massive list up here. DSC engine, focus on this list and write some tests for this. Because yeah, the rest of these unit tests or staging tests, we're not going to learn anything new. This is just one of these things that you got to do, that you got to get good at, that you got to write. Now, you don't have to get it to 100%. If you get it to like 85, 90, that's pretty good. Some of these tests are actually very difficult to write, but writing these tests should find a glaring bug in at least one of these functions. And maybe if you find more than one glaring bug, that's great. Make a PR, make an issue to the repo. But I want you to pause the video and take some time, right? It might be an hour, it might be 2 hours, it might be 30 minutes, right? Depends on how quick your AI buddy is, how quick you are, and write some more tests. And sometimes, actually, you can even come to your contracts and you could do something like grab this, go over to your chat GPT and say, hey, this is one of my Solidity functions. Can you write some tests for it in Foundry? And because it doesn't know what Foundry is, it's going to totally bunk it up. But you could use ChatGPT to help you write some tests as well, help you get your coverage up. But there's definitely one major issue in here. You might even need to go back and refactor some code, right? I'm going to say keep that to a minimum though, but there are some spots where maybe you need to refactor your code to make writing tests easier. Maybe you need to write some more helper functions, right? Take this time to experiment and tinker and think, what should I do? How can I make sure my code is safe? And importantly, how can I write enough tests to find this bug that Patrick is talking about, right? Maybe you do some refactoring. Now, don't write any fuzz tests yet. We are going to go over fuzz tests in a little bit, but yeah, just try to write the rest of these unit tests, rest of these pseudo integration tests, and I'll see you when you come out the other side. But when you finish writing the tests, take a break, take a minute. I want this to sink in. This is the most advanced lesson that you're going to take in this course. And to be honest, probably it's going to be one of the most advanced courses you'll ever take in Solidity. Okay. So I want you to take your time with this. I want you to understand what's going on. Sometimes it might even make sense for you to go, oh, well, what does MakerDAO do? How can I learn more about stablecoins? Where else can I go? Maybe I can ask ChatGPT for questions, right? For those of you who are going, I really don't want to do that, you can 100% just copy paste mine, but I recommend you go through this exercise. Okay, block off some time and I'll see you soon. All right, welcome back. Did you find the bug? How are your tests looking? If you run forge coverage, do they look something at least like this? Do they look better? Do they look worse? So I copy pasted a whole bunch of my tests and we're looking pretty good here. We definitely should be increasing the test coverage of our branches and we can definitely get these a little bit higher. But for at least the DSC engine, we have a much better code coverage going on here. And I hope your code coverage looks like this too. Now, additionally, I did a little bit of refactoring writing these codes. One of the main things that I added was I added this calculate health factor function. The reason I added this calculate health factor internal function was so that I could have this public calculate health factor function. And then in my tests, what I could do is have an expected health factor. And that way, when a function breaks health factor, I can pass that into the expected health factor error revert here in one of my tests, right? When we're testing to expect an event, I added this new function to do that. And having a public function like calculate health factor might make it easier for people to see what their health factor might be if they make some change, right? So that was one of the big ones I made. And the bug was in the health factor as well, or at least the bug that I planned to be in there. So in my calculate health factor, which instead of in our underscore health factor function, I'm just calling this calculate health factor function, right? I'm getting the account information and then just passing it to this calculate health factor. And in this, we needed to add a checker for if the total DSC minted was 0. And if it's 0, then we said, okay, cool, your health factor is going to be the max UNT56 or something like that, right? And the reason that we need this is if someone deposits a ton of collateral but has no DSC minted, well, their health factor is going to divide by 0, which we can't have. So calculating someone's health factor after they deposit collateral would result in an issue. We'd break stuff. We don't want to break stuff. And then the final piece that I did was I added a ton of external view functions just to make it easier to read and interact with this protocol. So those are some of the refactors that I did. And then obviously we added a ton of tests. There's nothing really new in here. It's just, you got to write the tests, right? Everything in here you've learned you can do. And if you wrote some tests and you got this to a high level of coverage, around 90%, you should be incredibly proud of yourself. This is hard to write tests for. This is a very difficult project. So you should be incredibly proud of yourself for just getting this far. But guess what? We're not even done, because we want to make this code so freaking amazing. We need to think a little bit about security, and we're not going to go too deep into security. However, we should ask ourselves some questions, right? When we're working with a code base, we want to say, we should always ask, what are our invariants / properties? What are the invariants / properties of the system? And that way we can write some stateful and stateless fuzz tests. Now, I know we briefly went over one form of fuzz testing, but now we're going to go a little bit deeper. And I made a video on stateless and stateful fuzz testing recently, and we're going to go ahead and watch that so you can have a better understanding of what stateless and stateful fuzz testing is and why it's so important, especially for a project like this that has potentially a lot of money moving around. So let's understand what fuzz testing is. Let's watch this video. All right, contracts are written and tested. Can I ship my code? No, I can easily break this with a flash loan attack. Ah, crap, I didn't think about that. Let me fix. All right, how about now? If I make a flash loan on Aave, I can use that loan to lock up a CDB on FakerDAO, and I can exploit the Oracle by re-entering your dinner reservation at Chili's, causing a bridge malfunction on the flux capacitor, bypassing the possibility media. I can exploit your contract. I exploit your contract. Most of the time, hacks will come from a scenario that you didn't think about or write a test for. But what if I told you that you could write a test that can not check for just one scenario, but every scenario? Let's get froggy. Fuzz testing or fuzzing is when you supply random data to your system in an attempt to break it. So if this balloon is our system / code, it's us doing random stuff in an attempt to break it. This is Chainlink. Now, why would we want to do all that? Let's say we have this function called doStuff. It takes an integer as an input parameter, and we know that no matter what we give it as an input, our variable should always be 0, should always be 0. The fact that this variable should always be 0 is known as our invariant, or our property of the system that should always hold. In our balloon example, if we market our balloon as indestructible or unbreakable or unpoppable, the invariant that would hold would, this balloon cannot be broken. And unlike this balloon in real life, we can write a test that will call the doStuff function many times with random data and check to see that our should always be 0 variable is always 0. Now, a normal unit test for our code might look like this. We pass a single data point, we call the function, and then we do our assertion to make sure that should always be 0 is in fact 0. And with this, we might think our code is covered. But if we look back at our doStuff function a little bit closer, we can clearly see that if our data input is 2, should always be 0 will end up being 1. This would break our invariant. Should always be 0 will not be 0. Now, this may seem obvious for this function, but sometimes you'll have a function that looks like this. It would be insane to write a test case for every single possible integer or scenario, so we need a programmatic way to find this scenario. Now, in our code, we also see a second exploit, but we'll get to that in a minute. Now, there are two popular methodologies to find these edge cases: fuzz tests / invariant tests, and symbolic execution / form of verification. We'll save the latter for another video. If we were writing our code in Foundry, this would be our unit test. Writing a fuzz test in Foundry, where we do all this random inputting, is going to be really similar. Instead of us manually selecting our data, right in our test parameter, we'll add our variable, comment out this line, and that's it. Now, when we run a Foundry test here, Foundry will automatically randomize data, run through our code with a ton of different examples. This is as if they run with data equals 0, data equals 1, data equals this number, that's a t, but whatever, you get the picture. Now, if I run my unit test, you'll see that the unit test actually passes. However, if we run this fuzz test, you'll see it actually gives us an output where it says assertion violated, counterexample, gives us the call data and the arguments. It was able to find out by randomly throwing data at our function call that 2 breaks our invariant, aka it makes it such that should always be 0 is not 0. Now, it's really doing semi-random data instead of purely random data. And the way your fuzzer picks the random data matters. It won't be able to go over every single possible uint 256. So understanding how your fuzzers pick the random data is an advanced thing that you should learn later on. At the moment, I think the Trailbits Echidna / Optic integration is probably the best fuzzer out there, and it easily has the best logo of all time, but Ripped Jesus is a solid second. So now that we have our counterexample here, we can use this to go back into our contract, find out, okay, so we are doing this wrong, delete this line, and then run our test again and see that it does indeed pass. What's important is this number down here, the number of runs. So this did 256 different random inputs to make our test run. In Foundry, you can change the number of runs in your foundry.toml file by just adding a section like this, rerunning your tests, and now you'll see it did 1,000 different examples. The number of runs is really important, obviously, because more runs is more random inputs, more use cases, more chance that you'll actually catch the issue. And now, congrats, that's the basic of fuzz testing. Let's just do a little recap here before going further. The first thing you need to do is understand our invariant, or property of the system that must always hold. In our example, should always be 0 was our invariant. Understand your invariant, and then write a test that would input random data to try to break that invariant. Now, if we go back to our example contract though, you'll see with our fuzz test, we were able to find this first use case. However, it didn't find this second scenario where should always be 0 was set to 1 if hidden value was 7. In order for this to revert, hidden value would need to be 7. And the only way to set hidden value to 7 would be to first call do stuff with 7, which would set hidden value down here, and then call do stuff again with anything. Our fuzz test, as written, would never be able to find this. That's because this fuzz test is known as a stateless fuzz test, which is where the state of the previous run is discarded for the next run. If we go back to our balloon example, stateless fuzzy would be doing something to the balloon for one fuzz run, then discarding that balloon and blowing up a new balloon for each fuzz run. However, instead of doing stateless fuzzing, we could do stateful fuzzing. Stateful fuzzing is where the ending state of our previous fuzz run is the starting state of the next fuzz run. For example, instead of blowing up a new balloon for each one of these runs, we just use the same balloon to do multiple random things to it. Combined is considered one fuzz run. So a single fuzz run on a stateless fuzz run would be having data be 7, calling do stuff, just using the same contract that we just called do stuff on, and then call another function on it. If this was a unit test we had, we would of course see this get violated. But as you can see, with sufficiently complicated code, coming with these very specific scenarios are going to be missed. To write a stateful fuzz test in Foundry, you need to use the invariant keyword, and it requires a little bit of setup. And don't get too confused by the invariant keyword here. Yes, it's being a little overloaded. To write an invariant test in Foundry, we first need to import this std invariant contract and inherit it in our test contract. Then we need to tell Foundry which contract to call random functions on. Since we only have one contract with one function, we're going to tell Foundry that my contract should be called and it's allowed to call any of the functions in my contract. So we'd say, hey, the target contract for you is going to be the address of example contract. Foundry is smart enough to know, okay, it's going to grab any and all of the functions from my contract and call them in random orders with random data. So it's going to call do stuff with random data, and then it's going to call do stuff with random data, and then it's going to call do stuff with random data since do stuff is the only function. Now we can write our invariant by saying function invariant test always is 0 public, and we can just add our assert. Assert our example contract that should always be 0 is 0. So it'll run do stuff with some random data. If it happens across 7, it'll set hidden value to 7, and then it'll call do stuff again with hidden value starting at 7, which will trigger this conditional. So now if we run this test, we can see it does indeed find a sequence where our invariant or our assertion or our property is broken. We can see first on my contract, it's going to call do stuff with an argument of 7, and then it's going to call my contract with an argument of some random number, because it doesn't matter what the input is after it sets it to 7. So now that we have that, we can go back to our code, remove this, come back to our test, rerun our test, and we'll find that our code is now safe and sound because our invariants hold up. Now, an important aside on the term invariant, Foundry uses the term invariant to describe this stateful fuzzing. Stateless fuzzing is when you give random data to an input to a function to see if it breaks some invariant. Stateful fuzzing is when you give random data and random function calls to a system to see if it breaks some invariant. In Foundry, fuzzing is stateless fuzzing, and invariants are stateful fuzzing. So when people are talking about invariants in Foundry, they're usually talking about stateful fuzzing. If they talk about fuzzing in Foundry, they're talking about stateless fuzzing, even though they're both technically fuzzing. There's an issue on the repo to potentially change the name, but I digress. So in a real smart contract, your invariant won't be that a balloon shouldn't pop or some function should always be 0. It might be something like new tokens minted is less than the inflation rate. There should only be one winner in a random lottery. Someone shouldn't be able to take more money out of the protocol than they put in. And let me tell you what, at this point, congratulations, you've learned the basics of fuzzing. This is something that even some of the top protocols in this space don't use. And this is something that we in Cyphren use to find high severity vulnerabilities in smart contracts.
Hey, I'm Alex Rowan, co-founder at Cyphren. We use invariant tests during our audits to identify vulnerabilities that are often difficult to catch purely with manual reviews. That's not to say they're a silver bullet. They are in no way a replacement for experts' manual review, but they certainly can aid in the audit process.
This needs to be the new floor for security in Web3. If you're working with a protocol that isn't doing stateful fuzzing or invariant or fuzz tests, red flag. Get them to use it. Make a PR. Number 1, understand what the invariants are. Number 2, write functions that can execute them. Do not go to audit without these. Don't let your auditors let you get away with not having them. So this video was just to give you the basics. And if you want to learn the advanced fuzzing strategies and how to fuzz like pro, be sure to watch our next video on the topic, as that'll give you the keys to write professional fuzz and professional invariant tests. Come on, gang. Let's make Web3 better, and I'll see you next time. All right, so now we've learned a little bit about invariant tests or fuzzing tests and why they are so absolutely crucial, especially for a project like this. So we're going to write some stateful fuzz tests or invariant tests in Foundry so we can have some more confidence that our code actually does what we want it to do. And the method that we saw in that video that we just watched is kind of the most basic methodology out there. And if we go to the Foundry docs, we can go on the left side, go all the way down to fuzz testing, or go all the way down to this invariant testing, which invariant testing, like I said, is stateful fuzz testing. And we can read more about some of the more advanced ways to do these fuzz tests or these invariant tests. We're still going to do the target contracts, but what we saw in the video was a type of open testing, right? Where we just have function invariant A and then the assert. And what this does is it just calls all the functions on this contract to try to break that invariant. Now, this is good. This is great for an initial run of the code. However, we want to do for more advanced systems like ours, handler-based testing. Sufficiently complex protocols are going to have so many different random intricacies that we want to narrow down the random call so that we can have a higher likelihood of getting and catching actual errors. So we're going to do this handler-based type of testing. In this example here, in this open testing, it just calls any of the functions in the contract in any order. And handler-based testing, if we scroll down, we can kind of see this example here, where we create a contract called handler, where we only call functions in specific ways. For example, when depositing tokens, we need to make sure an approve happens beforehand. If you just call deposit without approving that token, that's kind of a wasted fuzz run. And if we only have 200 fuzz runs and we're wasting them on failed fuzz runs, well, the chance of us actually finding a bug becomes smaller. So if you think of the open fuzz testing like this, where you have Foundry, you call a whole bunch of functions on the protocol with the asserts, handler is going to call functions in specific ways to the function so that we have a higher likelihood of calling functions in orders that we want. So we're going to learn about this handler-based methodology, and we're going to build an incredibly verbose fuzz testing or invariant testing setup. Now, in our foundry.toml, to work with these fuzz or these invariant tests, we can do this in variant section here. We can say the number of runs, we'll say is 128. We can also say the depth, which is the number of calls in a single run, which we might do 128. And then one of the most important keywords you're going to run into is this fail on revert. So let's talk about this fail on revert keyword and setting. So to create some invariant tests, let's create a new folder or fuzz test called fuzz or invariant or whatever you want to call it. And in here, we're going to need to actually create two different files. We're going to do invariance test.t.sol, and then handler.t.sol. This invariance file is going to have our invariance, aka our properties of the system that should always hold, right? That we just learned from that video. And this handler is going to narrow down the way that we call functions. This way, we don't waste runs, like I was saying. Again, if we call deposit collateral in our stablecoin without approving that stablecoin, that's kind of a wasted run, and we don't want to waste runs. So this handler is going to set our code up, set our contracts up so that we don't waste these runs. And we're going to come back to this fail and revert in a second. For now, let's actually set this to false, and we'll set it to true soon. But so the first thing we always want to do when writing invariant tests, when working with this, is want to ask the question, what are our invariants? What are the properties of the system that should always hold? Well, we can think of some, right? Well, one, the total supply of DSC should be less than the total value of collateral. Follow the word wrap. The total supply of DSC, which is essentially the debt, should always be less than the total value of collateral. Great, we have an invariant that we can test, and we should throw a ton of random function calls to try to break this one. Okay, what else? What other invariants should we have? Maybe our getter functions, our getter view functions, should never revert. And this is actually sort of an evergreen invariant. Most protocols can and should probably just have an invariant that looks like this. Getter view function should never revert. Now, we can probably think of more, but because doing these invariant tests can be a little bit time intensive, we're just going to focus on these two for now. These are going to be the two invariants that we focus on and we try to work with. So let's begin working and writing our invariant tests. And then we're also going to write our handler to help make sure all the function calls that we're working with actually do what we want them to do. Okay, let's do it. So this is going to be another test file. So spdx, license, identifier MIT, pragma. So, oh, well, that's nice. That kind of just automatically added it for me. Let's put this to the top. 0.8.18, a little caret here. Contract, invariance, test, like this. And to do this, we're going to say, we're going to have to import some stuff. We're going to import test from forge td/test.sol and import std in variant from forge std in variant dot sol. This contract invariant test. And then we're going to say this is std invariant and its test. So this std invariant contract, if we click into it, it has all this stuff that we're going to need to work with the invariants. One of the most important functions that it gives us is this target contract, where it says, hey, this is the contract I want you to call all these random functions on. Okay, great. Now, just like our normal tests, we're going to have a function setup, external, like this, and we're going to set up some stuff, right? A lot of this is going to look similar to our unit tests. So we're going to have to import deploy DSC from // script/deploy dsc.s.sol, import dsce engine from // src/dsc engine.sol, like this. and we'll say deploy DSC, deployer equals new, deploy DSC. And then of course, DSC engine, DSCE equals deployer.run. And this actually returns a whole bunch of stuff. Decentralized stablecoin, DSCE, and helper config. So this is going to be, we also need a DSC. So we're going to import that. Import the centralized stablecoin from //src/decentralized stablecoin.sol. So we're going to do decentralized stablecoin, DSC. And let's get the helper config as well. Import helper config from //script/helperconfig.s.sol. Helper config. Great. And so this returns the DSC, DSCE, and config equals deployer.run. Great. And now, if we were doing this open testing methodology, right? If we go back to the docs here, we're doing this open testing methodology, we could kind of finish this right now. So what we would do is we would say target contract address DSCE, like this, paste this in here. And then just by adding this, we're telling Foundry, hey, go ahead, go wild on this, right? Go absolutely wild on this. And actually, let's even rename this. Call this open invariant test.t.sol. Open invariant test.t.sol. So we'll say absolutely go buck wild on this. And now we can add our invariant, right? We'll say function variant underscore protocol must have more value than total supply. And this will be a view function. And what we can just say is we want to get the value of all the collateral in the protocol, compare it to all the debt or the DSC. So we can do that pretty easily by using the collaterals itself, right? Using our helper config, we'll say helper config.active network config. We can get the, what does this one do again? Let's open up the helper config. We can get these two tokens and just say, okay, well, what's the balance of these two tokens in our DSC engine? And then what's their value, right? So we'll just get those two tokens. So we're going to do nothing, WETH, Bitcoin, nothing. So we'll do blank, WETH, BTC, nothing. And then those are ERC20s. So we'll import IERC20 from, all right, cool. That looks good. So we'll say ERC20 WETH, IERC20 BTC. This is wrapped BTC. Oops, sorry, this is config.active network config. We need to wrap this IERC20 like this. What am I messing up? Oh, let's just do address WETH then. Address WETH, address BTC, like this. All right, cool. So we're getting WETH in Bitcoin. There's going to be wrapped ETH and wrapped Bitcoin. And now what we can do is first we'll say uint 256 total supply equals DSC dot total supply. So this is the total supply of all DSC in the entire world, right? And we know the only way to mint DSC is through the DSC engine. So through people depositing and withdrawing collateral. Now what we can do is we can say, okay, let's get the uint 256 total WETH deposited equals, and this is where we can do IERC20 WETH dot balance of address DSC. So this is going to be the total amount of WETH deposited into that contract, or just the total amount of WETH sent to that contract. Then we're going to say uint 256 total BTC deposited equals IERC20 wrapped BTC dot balance of address DSC. So we have the total WETH, total Bitcoin. Now we can get those values. We can say uint 256 WETH value equals, we have a function here called get USD value, where we can get the USD value of any token of any amount. So we're just going to use that. WETH value is going to be DSCE dot get USD value, WETH, and the total WETH deposited, uint 256 wrapped BTC value. Same thing. Get USD value, wrap BTC, total BTC deposited. And now what we can do is we can do assert the WETH value plus the wrapped Bitcoin value is greater than the total supply. And this is all we would need to do for this open testing, this open invariance. That's it. We're done. Boom. And this is why this is the easiest type of invariant test. But you'll see, running this, we won't get great results. So let's do forge test.m. And now what this is going to do is it's going to call all types of functions on our DSCE and try to break this invariant. So it looks like it was able to break this really easily. So let's clear this and we'll add our dash VV. We'll see what's up. Yep, assertion violated. We're having a hard time actually seeing the numbers. So we're going to import console in here. Test console. And we're just going to say console.log WETH value, semicolon, WETH value, or that's wrap BTC, WETH, wrapped BTC value, console.log, total supply. Let's run this again. Now what do we get? Well, we get our first issue is that these are all zeros, right? And if they're all zeros, then this doesn't hold. So we can do greater than or equal to. This is kind of a bit of a cop-out, right? Because if they're equal, that makes us nervous, but it's fine, right? We should always at least have more collateral in the system than total supply. So now let's try again. Run this test again. Compiler run successful. And we get, hey, you pass. There's no way for us to make it such that the total supply is lower. So this is awesome, right? Well, it's not that awesome. We didn't find any issues. We're looking to find issues. So maybe we need to bump up the number of runs. Maybe we need to bump it up to 1,000. And let's run this again. Now you're going to see this is going to take a lot longer. Because before it was doing 100 runs at 128 depth. Now it's doing 1,000 runs. And each one of these runs has 128. So it took a lot longer. And you can see that it took 14 seconds as opposed to what did it do before with 128. We run that. It did it in 1.5 seconds. But if we look up here on this line is incredibly important. We have calls and we have reverts. So this made 16,384 calls and reverted 16,384 times. So basically, it wasn't even able to do anything, right? So what if we bump this up to 1,000? Clear, run this. We're gonna have to wait a few more seconds again. Ugh. So it did this many calls and it also reverted this many times. And the reason that this is still saying pass though, is because we have this fail on revert equals false. And this fail on revert equals false has some pros and it has some cons. The pro of fail on reverse equals false is that we can very quickly write open testing functions like this. And we can very quickly write minimal handler functions that aren't perfect. But the downside is it's hard for us to make sure that all the calls we're making actually make sense, right? Because this could be calling on our engine. Maybe it's just trying to deposit collateral, but it keeps using random collateral addresses that don't make any sense. So maybe it's calling this 128,000 times with 128 different collateral addresses, but only 2 work, right? So doing like this is cool for kind of some sanity check and maybe it'll catch something, but it seems like it's not actually catching anything, right? And that's not a very good use of this. So revert on false is fantastic for quick tests. And often if I'm doing a competitive audit, which you can learn more about in the security course coming out soon, hopefully. If I'm doing competitive audit, a lot of times I will have revert on false be false, just so I can write up invariant tests quickly. I will also write handlers as well, like mini handlers, just so I don't have to get every nook and cranny, but I still will write a handler so I can narrow down some of the functions. But this open invariant seems to have this major flaw where it's probably making a bunch of silly calls. So this is great for very small contracts, but the more complex you get, like our system here, this open invariant system, it probably doesn't make sense for us to do because it's not going to catch anything. It's just going to keep breaking. Now, if we set this to true, we open this back up, we run this again, you'll see exactly one of the calls it makes that breaks. So it looks like it called redeem collateral for DSC. This is the first function call it made, which obviously doesn't make any sense because you can't redeem any collateral unless you have deposited collateral. And you can see the args it put in. It put in some random address, some random amount, a random amount, and then another random number, right? And you'll see we can call this many times and it'll keep giving us different places that it ran into issues. When we say revert on false is true, this can give us some peace of mind knowing that if this test passes, that means all of the transactions that went through actually went through and it didn't make a bunch of really dumb calls here, right? So here, fail on revert was false. We called liquidate first, which obviously doesn't make any sense with some horrible random address, some random amount, right? None of these make any sense. We call it again. We failed again. It called deposit collateral mint DSC, which is good. All right, so we're trying to deposit collateral, but it used some random address that isn't approved, some horrible amounts here, and it just keeps failing, right? So we want to try to prevent, and you can see here in the call summary, it made one run, one call, and that call reverted, right? So we want to narrow this down to try to point our fuzz, our random runs in a direction that makes a lot more sense, right? So this is cool, not great. Open invariants. I'm just now going to comment out this whole page because we're not going to use this anymore. Okay. I'm going to leave the file in here though. We're going to create a new file though. We're going to call this invariants t.sol. I am going to copy this whole invariance thing, paste it in here and uncomment it. And we're going to level this up so that this invariance file, actually, let's just call this invariance, so that this new one is using this handler method. It's using this handler method to narrow down the function calls. And we'll do a mix of setting this to true and false, and you'll see where some of the advantages and disadvantages are. So we have our invariance file. We have our target contract here, but we want to make sure we call this in a sensical order. For example, hey, don't call redeem collateral unless there is collateral to redeem, right? Maybe we want to set this up. So we're going to create a handler, which is going to handle the way we actually make calls to the DSCE. So it's basically going to, instead of us just randomly calling redeem collateral, we're only going to be able to call redeem collateral if there is collateral to redeem, right? Because otherwise the transaction is just going to revert and that's a waste of a function call. So now we're going to create this handler. And instead of our target contract being the DSCE, our target contract is going to be this handler, which handles the way we make those calls, okay? So we're going to do SPDX license identifier MIT, as you already know, pragma, solidity, 0.8.18, a little caret, contract, handler, like this. And then we're going to say this contract handler is going to be test as well. And this is definitely some advanced code here. So don't get too discouraged if it doesn't make sense or if it's hard the first time, okay? So we're going to import test from forge std/test.sol. Remember to ask questions and use the forums. So what's one of the first things we want to do? Hey, don't call redeem collateral unless there is even collateral to redeem, right? We want to make sure that this is a valid run. Hey, only call redeem collateral when there is collateral in there. So this function, this contract is going to do that for us. We do need to make a constructor though, so that this handler contract knows what the DSC engine even is, right? Because it's going to be the one making the calls to it. So we do need to import the DSC engine from //src/DSC engine.sol. We also need to import the decentralized stablecoin from the decentralized stablecoin.sol constructor. And these are going to be the main functions. These are going to be the main contracts that our handler is going to call. So we're going to say DSC engine DSCE, and then we're going to say decentralized stablecoin DSC. And in the constructor here, we're going to say DSC engine _ DSC engine. a decentralized stablecoin underscore DSC. And then we're just going to say, oh, cool. It already added DSCE, DSC engine, and DSC is underscore DSC. So because these are the contracts that we want the handler to handle making the calls to. Great. Makes sense. So let's talk about this redeem collateral, right? Let's just focus on making this not revert. So we're going to say, okay, call this when you have collateral. So the first thing we probably need to do is what? Probably deposit collateral, right? So we'll create a function called deposit collateral. And this function is going to look a little different than the deposit collateral in the DSC engine, right? If we look in here, this is what it does. But we're going to set this deposit collateral function up in our handler so that this transaction always goes through, right? It doesn't revert. But we do want to keep the randomization, right? We want it to deposit random collaterals that are valid collaterals. So what we can do is we can create a uint256 collateral seed and a uint256 amount collateral. And this is actually really similar to the fuzz tests. So in your handlers, whatever parameters you have are going to be randomized. So we're going to pick a random one of the valid collaterals to deposit, and we're going to pick a random amount of collateral. Now I'm going to write this function without any guardrails, and it's going to break, and that's okay. We're going to fix it as we go along. But if we were to just not have any guardrails on this at all, we would just say dsce.deposit collateral, and we would do collateral and an amount collateral. We could actually just have this be address collateral and amount collateral, and we'd say deposit this collateral and amount collateral. And this, of course, is probably going to break a lot, right? Because the collateral we're going to pass is going to be wrong. This is a random address. There are so many addresses. And the amount of collateral could also break because deposit collateral reverts on 0, right? But I do want to show you what we're actually going to do in our actual contract here. Instead of having our target contract be the DSCE, what we're going to do is we're going to say handler. So we're going to import this handler. So we're going to do import handler from /handler.t.sol, handler. We're going to say handler equals new handler, DSCE and DSC. And now we're going to say our target contract is just the handler. Okay. Excuse me, the address handler. Now with this, the handler only has this one function. So we're going to call deposit collateral through the handler, which is going to call our engine. And since this is the only function for it to call, this is all we're going to see if we see our invariance break. So if I do forge test-m, paste this in, we're going to see it break almost instantly with an issue, but it's only going to be deposit collateral because it's the only function that we have, right? We run it again. It's still going to be deposit collateral because it's the only function the handler has. Yes, makes sense? Okay, cool. Hopefully it makes sense. In our foundry.toml, we could say fail on revert is false. We could run this again. Let's make this a little bit lower, 128. And let's see if we get any valid runs, right? Let's see if we pick miraculously a valid address and we get success, but oh, it looks like we did do some valid ones, but we've got a ton of reverts here. We've got so many reverts here that almost half of these runs, almost half of these calls were bad. That's not a great use of our, and this isn't really super helpful because of course our invariant here is going to hold because the only thing we've allowed our system to do is deposit collateral, right? Ridiculous. So if we turn this back to true, we run this again, we're of course going to break now because some of these deposits are going to fail, right? So it looks like if we call deposit collateral with some horrible address, it fails, right? So that's one of the first things we want to have our handler do. We want to say, hey, you're only allowed to deposit valid collateral. So what we can do in our handler is we can set that up. Hey, you're only allowed to deposit valid collateral. Instead of passing any address as collateral, we'll say uint256 collateral seed, okay? And what we're going to do with this seed is we're going to have it pick from our two collaterals. We're going to have it randomly pick either WETH or BTC. So we're actually going to create a function, helper functions. We're going to say function underscore get collateral from seed, UN256 collateral seed. And we're going to make this a private view function that's going to return an IERC20. Actually, we're going to do an ERC20 mock, and I'll explain why in a bit. We got to import that. Import ERC20 mock from at Open Zeppelin contracts mocks slash, what is it? Mock ERC? No. ERC20 mock.sol. Cool. And so what we're going to do instead of this line is we're going to use this line, this function to do it. We're going to say if collateral seed modulo 2, because we only have 2 collaterals, equals 0, then return weth. We can get weth by sticking at the top. We'll say ERC20 mock weth, ERC20 mock wrapped Bitcoin. And right in our constructor, we can get all of our collateral tokens. Because I made a function way down at the bottom here called get collateral tokens, which returns the full array of collateral tokens. If you don't have this, feel free to pause and implement this. But what we can do, we can say address array memory collateral tokens equals dsce.get collateral tokens like this. And we can say weth is 0 and wrap BTC is 1. So that's how we can get those collateral tokens. So weth, wrap BTC. If collateral seed divided by 2 is 0, return weth. Otherwise, return wrapped BTC. So now we have a function where we can only get a valid collateral type. So instead of just depositing any collateral type, we can say ERC20 mock collateral equals get collateral from seed, collateral seed. And now we're still depositing a random collateral, but this is, it's going to be address. But this is a valid collateral address. So we're probably more likely to actually pass a transaction that will actually go through, making us have more solid, more good random calls. So let's try to run this function now. Great. Successful, but we ran into an error, right? Let's see what the error is. So deposited collateral, UN256 with this huge collateral seed and nothing. So it looks like we failed here. Let's clear. Let's rerun it with -vvvv so we can see a little bit of output of why we actually failed. Okay, the only function we're calling is deposit collateral. Looks like this failed again. We called deposit collateral with some weird args. We can scroll up and see exactly why we failed. Oh, we ran into this. DSC engine needs more than 0. So it looks like we tried to deposit 0 collateral. Amount collateral was 0. Yep. Okay. So we tried to call with 0. So amount collateral was 0. So we know that this is going to fail. So how can we make it so that this doesn't fail? Or maybe you're like, hey, like sometimes it will be 0, like whatever. I just want a sanity check. You can make fail and revert false, right? And we can run this again. And now we'll see how often this actually fails. Hopefully we cut down on the amount of times it failed. Oops. Let's remove those V's. Great. It does look like we cut down on the amount of reverts we got. Not a lot, but we did cut down on the amount of reverts, at least by adding this bounding of the collateral types. But let's keep cutting down on these reverts and potentially even have revert on false be true, right? You're not always going to have revert on false be able to be true. And sometimes it's quicker just to have it false and write all your invariants and stuff. But if you want but it is good to aim for this. Now, the downside of always aiming for this is that if you make your handler too specific, maybe you'll actually narrow it down and remove edge cases that would break the system that are valid, right? So it's kind of this balancing game you have to play with these fuzzing tests and whether fail and revert to be true or false. There's definitely a little bit of an art to this. So the more you do it, the better you'll get. But in any case, collateral seed, amount collateral, we need to now change it so that this amount collateral is bounded between 1 and some max number, right? So we don't want this to be able to be 0. So what we can do then instead is we actually can bound this so that in the same way we got a valid collateral, let's get a valid amount collateral. So we can say amount collateral equals bound. This is a function that actually comes with std utils, and it bounds the result to an amount. So we want to say, okay, this amount collateral, we're going to bound our amount collateral to being between 1, we don't want it to be 0, and then some like really, really big number. What I like to do is up here in the state variables, I'll do uint256 max deposit size equals, and I'll do type uint96 dot max. And this allows us to get the max uint96 value. Why are we not doing the max uint256? Well, if we do the max uint256 and we try to deposit more collateral later, if you do the max uint256 plus 1, you'll get a revert. So this is going to give us a really, really, really big number, but we're at least not going to hit the absolute top of amount of deposits we can deposit. So we're going to say we're going to bound this amount collateral between 1 and max deposit size. Okay, cool. So let's put this back to false. Let's run this test again, and let's see if we cut down on the reverts some more. Aha, a couple more, right? Only a few hundred, but we did cut down on the amount of reverts. Why? Because we're passing valid, well, okay, that one didn't go so well, but we are cutting down on the amount of reverts piece by piece. We're able to bound the collateral, but there's more. If we do fail on revert back to true, we can see exactly why it's failing, right? We'll do dash VV. We can see an example that is indeed failing. And whoa, these are getting more intricate, right? Before it was just a single call was breaking it. Oh, okay, so a single call still is breaking it, but they are getting a little bit more intricate. So it looks like this one failed because what? We called deposit collateral. We scroll up, we're getting this insufficient allowance. Oh, okay, so that's why we actually weren't cutting down on the reverts at all, because we're getting insufficient allowance. Of course, we need to approve the protocol to deposit this collateral. So of course this is breaking. This is always gonna break. So let's do a little prankage. So we'll do vm.startPrank. We'll just do message.sender, and we'll allow this message sender to mint some of this collateral so that they can actually deposit it, right? So we can set this up so that whoever's calling deposit collateral actually has the collateral and actually will approve to deposit the collateral. So, and this is why I'm using this ERC20 mock, so that we can actually mint some of this collateral. So we'll do collateral.mint, message.sender, amount collateral. We'll do collateral.approve, address DSCE for the amount collateral. Then we can deposit it, and then we'll do vm.stopPrank. Okay, now let's clear this. Let's have revert on false to be false. And let's see now if we cut down on the amount of reverts that we get. Oh, and I added too many V's. Let's get rid of those. Let's run this again. And yep, there will be some brief delays in here, of course. Whoa, we cut the amount of reverts down to 0. Now, all of our function calls are passing, which means every single run was a valid run, meaning we're using our runs much more wisely. We're not wasting runs on failed reverts. So now I can even set this to true, run this again, and we'll see this passes and none of our runs failed, right? So this means, what does this mean from a security standpoint? It means that no matter how often we call deposit collateral, no matter how much we deposit our collateral, we will never make this invariant false, which isn't saying too much because, of course, we're not even, the total supply is always 0. Of course this holds. So this makes a lot of sense. So let's actually keep writing more functions to do more with the system, but set them up so that whenever we call them, they're always going to be valid calls, okay? So now we were talking about redeem collateral, right? Okay, cool. So now we actually have a function, a valid function to deposit collateral. Now let's actually have a valid function to redeem collateral. So we're going to do the same thing. Function redeem collateral. We're We're going to do the same thing. It's going to take a UNT256 collateral seed for which collateral to redeem. UNT256 amount collateral. So be a public. And we're going to do something very similar here. We're going to say we're only going to choose a valid collateral by saying ERC20 mock collateral equals underscore get collateral from seed, collateral seed. And now we should only allow people to redeem the maximum amount they have in the system, right? So we're going to say UNT256 max collateral to redeem equals DSC engine dot get collateral balance of user. Do we have this function? DSC engine. So this is one that I added in. It's going to get the collateral balance of a user if you pass in the user and the token. So if you want to pause and add this in, feel free to do so. Get collateral balance of user, where we add the address of the collateral and the message.sender. So it's going to get the total balance of a user. Oh, and this should be DSCE. And then we're going to bound the amount collateral to this max amount that they have. To make these always valid, they should only be redeeming as much as they put in the system. Amount collateral equals bound amount collateral. We're going to say redeem between 1 and the max collateral to redeem, because we don't want them to redeem 0, of course. And then we're going to say, oh, this is going to be public. Then we're going to say DSCE dot redeem collateral, address collateral, and amount collateral, right? So now we have two functions to randomly call. So we're going to be depositing collateral and redeeming collateral. Let's run this invariant. It only has two functions it could call. We go to the foundry.toml, fail and revert is true. Oh, and it looks like we found an edge case. So now we can read this and see what it's doing. So it's depositing some collateral, 1381 and 82, and then it's redeeming the collateral. I'm actually sure what's going on. So let's add this dash VVVV to see more into the actual transaction that's failing. Oh, my goodness. We got an even bigger one here. So what do we say? Oh, max is less than the min. Oh, looks like I'm messing up with my bounding. So it's not even really an issue. So if we go back to the handler, bound amount collateral, 1 max collateral to redeem. Ah, okay. So if max collateral to redeem is 0, this will break. So we actually do need to keep 0 in here. And then we can just say if, amount collateral equals 0. We could say if it's 0, return. Or what we could do is we could use this keyword called assume, like vm.assume, which will say, if the Boolean expression value is to false, the fuzzler will discard the current fuzz inputs and start a new fuzz run. So we're going to do if the amount collateral is 0, just return. Don't call this function, right? Because this is going to fail. So let's go ahead and run this again now. Compiler run successful. Well, would you look at that? We are now passing again. So people can, if we go back to the handler, people can now redeem collateral, and all of these redeemings are going to be valid, and all of these deposits are going to be valid, right? They can only redeem valid redemption amounts. Now, here's where this fail and revert equals true can be a little bit deceptive. Let's say right now, we're only letting you redeem the max collateral to redeem. Let's say there was a bug where a user can redeem more than they have. This fuzz test wouldn't catch this. It's because we have this fail and revert is true. If this fail and revert was false and we didn't have this line, right? And we just said this is the max deposit size, this is a test where we might actually catch that bug, right? And if we run this now, and with fail and revert is false, we are going to get a whole bunch of reverts. We are going to get bad transactions. However, and you can see, we can see the number of reverts over here, and it actually is way less than it was before, which is awesome. And if we run it again, still way less than 8,000, which is what it was before. But if we have fail and revert false, we can actually catch this. So the Foundry team is actually working on allowing some tests to be fail and revert and some tests to be not fail and revert. So you can kind of pick which one for which functions instead of kind of having to blanket everything. So just keep in mind the dangers here, okay? Of always defaulting to fail and revert equals true, okay? They have their trade-offs. And if you do fail and revert equals false, you can sometimes write these handlers a lot quicker. But okay, so we have some stuff here. We can deposit collateral. We can redeem collateral. What else? So we probably should figure out a way to get some total supply, right? So what we're going to do is now we're going to finally make our mint function. So function mint DSC, public like this. And what do we want to put in here? Well, if we go to the DSC engine, go to mint DSC, go to this mint DSC function, it takes an amount of DSC to mint. So we'll do the same thing. We'll say uint 256 amount, and that's it. We'll mint a random amount. So in here, of course, we can't have amount be a number of things, right? We can't have it be 0, and they would need to not have their health factor be broken. So we're going to say amount equals bound amount 1, and let's say max deposit size, and then additionally, this amount better be more than the value of the system, right? Because we have this revert if health factor is broken. But maybe I don't even want to do that narrowing down. Maybe I just say, screw it. I'm going to make revert on false, revert on fail and revert false. And I'm just going to leave it like that because I'm nervous that I'm going to narrow it down too much. So then maybe I just go, screw it, bm.startPrank, message.sender, and we call in the DSC engine mint DSC, dsce.mint DSC, and the amount, and then vm.stop.prank. And this is where actually you'll see sometimes some people will have continue on revert and a fail on revert. Fail on revert. See, some people can have two types of folders. Continue on revert is going to be the quicker, looser tests where it might look like this. The fail on revert is going to make sure that every single transaction that you run your invariant test suite on is going to pass. I personally think it's good to have both. When I'm writing invariant tests, I actually start with the continue on revert because they're faster. Oftentimes you can find bugs as long as you narrow down them enough. So for now, let's go ahead. Let's have this be false. See if we can find any issues like this. So we'll go up. So we'll run forge test-m. We're just going to run this invariant test. Boom. Let's see if we get any issues here. We'll see how many reverts we get as well. So we got a similar amount of reverts, which is good. Similar amount of calls, which is all right. And then actually, if we do -vv, we can even see the console.logs at the end. It looks like it hasn't found a way to mint more tokens than collateral in the system. Oh, and it looks like the last run, it ended with a total supply of 0, right? But maybe I'm paranoid. Let's actually go back to true, and let's just stay true for the rest of this. But like I said, I think it's good to have both types of tests. Anyways, handler. So this mint DSC, we should only be able to mint DSC if the amount is less than the collateral. So what we can do is we can call this get account information, which gets the total collateral value in USD and total DSC minted, and make sure that we're always going to mint less than the collateral value that we have. So we can say, we can actually just copy these two, paste it in here, equals DSCE dot, copy this function, paste, message.sender. So we're going to get the total DSC minted, collateral value in USD. And what we can do is we can say, we'll just have them always mint the max DSC they can mint. So we'll say uint 256, max DSC to mint equals collateral value in USD. We could say the collateral value in USD divided by 2 minus the total DSC minted better be greater than 0, right? Better not be a negative number. So we can even do like an int 256. And then if this is negative, then we're just going to return. Otherwise, we're going to say amount. We're going to equals bound this again. Say amount 0, comma, max DSC to mint. And then we're also going to say if amount equals 0, we're going to return. Oops. And then actually we need to grab this start prank, put this down here. That's all we need to do. And we should probably just grab these, put them down here. We don't need both of these. So we just need this, I think. And we don't need both of these. We only need one of these. So we'll do UNT250. We'll convert this back to a UNT256. And if amount is 0, return. This looks pretty good to me. Let's see if we made this actually work. Let's run this. And now we can mint DSC. Successful. And bada boom. So we have some calls. We have no reverts. This is great. But I keep getting total supply is 0 down here. So we have plenty of WETH, plenty of wrap Bitcoin. Are we ever calling this function? We keep getting a total supply of 0 down here. Why is that? How can we figure out if our mint DSC is actually getting called? Let's first off see if this mint DSC is even being called. We can use something called a ghost variable to track this. So in here, up at the top, we'll make a function called uint256 times mint is called. We'll make this a public variable. And at the bottom of mint DSC, we'll do times mint is called plus. Now, back in our invariants, we do a console.log times mint called, comma, handler.times mint called. And then we'll run our test again. Oops, with -vv. And we can see, oh, mint is actually never called. How is that possible? Well, it must be because one of these returns is hitting and it's not finishing this call. So we could keep moving this up to figure out where it's actually being called and to continue to debug this. But I already know how to debug this, of course, because I've done this a while. If you want, take this as a challenge for you to answer the question, why is this never being called? Why is times mint being called, never being called? Why is it never finishing? So feel free to pause the video, try to debug this yourself and find out. And then I'll tell you the technique that I used to debug this and figure out why this mint DSC was never being finished. All right, welcome back. Did you actually pause the video? Did you actually try to figure it out? If you didn't, I'm giving you a second chance. Pause the video, go find out. Pause the video and take this as your opportunity to try to debug, okay, why is this not getting hit? Why is this line not hitting? All right, welcome back. Now, there's a couple different ways that I used to actually debug this. One of them was having this times mint called plus equals 1 and then moving it up so I found the line that it was breaking on. Once I found the line that it was breaking on, I console.logged all the values of the different variables around. One of the most important variables that I dumped was going to be the message.sender. So when you're working with invariants, remember, it's going to call this contract with a ton of different functions and a ton of different calls. However, it's also going to call them with random addresses as well. So in order for us to mint DSC, we need to only mint DSC with an address that has actually deposited collateral, because it's impossible for someone to mint DSC without them depositing collateral. Now, again, if we restrict this function like this, maybe there is a case where you can mint DSC without depositing any collateral that we don't know about. This is again why it's important to have some open invariant tests, some continue on revert, and some fail on revert as well. So if we want to have this be fail on revert, we would need to only pick a message.sender that has some deposited collateral. So what we can do is actually keep track of people who have deposited collateral. And then when we go to mint, we just choose an address from somebody who already has deposited. So how can we do that? Well, we can just keep track of an array of addresses that have collateral deposited. So up at the top, well, let's actually keep this times mint is called, and we'll put it at the bottom, times mint is called plus plus. And this way, we know how to test this, right? If times mint is called increases, we've known we will know that we fixed the actual issue. So times width is called plus plus. Up at the top, we'll do a address array, public users with collateral deposited. We'll copy this address. And now in deposit collateral, users with collateral deposited dot push message dot sender. Now there's some caveats here. This will double push, obviously, some people. So this will double push if the same address is pushed twice. But for now, let's just keep it simple and let's go ahead and just leave it like this. We probably should check to see if someone has already deposited collateral, but whatever. We're going to go with this for now because it's simple. And then now in our Mint DSC, we can do something similar to what we did with collateral. So we'll do a underscore uint256 address seed. And instead of bounding to message.sender, what we can do is we can say address sender equals users with collateral deposited. It's going to be the index of the users with collateral deposited of address seed mod users with collateral deposited dot length. And now instead of message.sender, we're going to use sender in here. Same thing with down here. We're going to use sender. Now let's run this and see if Mint is ever actually called. Aha, so this was very helpful. Redo it. Let's do dash -vv. Okay, so at least we're getting something different here, right? We're getting an error, division of module by 0. Okay, of course we're getting module by 0. Because if the collateral length is 0, then obviously sender is going to be 0. So we can do if users with collateral dot length equals 0, then we're going to return. We're going to skip this one. So let's run this again. Okay. So we're getting some stuff passing. Let's actually just do it 2 Vs so that it's easier to read than all those events. Aha! Total times Mint was called is now 31, and we're getting a total supply. So our Mint DSC function in our handler is now actually working. We're now successfully calling Mint DSC, and it looks like our protocol is holding up. All right, it's fantastic. So we're getting closer to building this handler to actually have a solid recreation of all the possible functions we can actually do in this system. Something I didn't show you was we should pretty much always use a given invariant called function invariant getters should not revert, like this. And then we just put in here all of our invariants, like dsce dot get liquidation bonus, dsce dot get precision, etc. Put all of our getters in here, and this could be public view. And if any of these revert, then this will fail. This invariant test will call a ton of different functions on the handler. And if any of the function combinations break any of our getters, we know we broke an invariant. This is a layup invariant that everyone should always 100% include. A way to make sure that you're including everything is you can run something called forge inspect DSC engine methods, and it'll print out all the different methods that this function has in addition to its function selectors. So you can kind of use this as your checklist of all the different functions you can call on a contract, and you can look for all the view functions in here. This is additionally why it's great to have get in front of these words, because it becomes very easy to figure out which ones are getters. But it doesn't reflect the whole world, right? One of the other really fantastic things we can do with the handler is we can both handle our DSC engine, but any other contract that we want to simulate for as well. And there's a lot of things we want to take in mind when writing these, especially the other contracts that we interact with. What are some of the other contracts that we interact with? Well, one of them is going to be the price feed. One of them is going to be the WETH token, the wrapped Bitcoin token. So our handler should probably also show people doing random weird things with WETH and wrapped Bitcoin, right? Because people are going to do random weird things with both of these tokens, and we want to make sure our system can work with them appropriately. Now, I'm actually going to skip them for now, but I am 100% going to do one with price feeds, because price feeds are definitely a system that can change, and definitely a system that greatly affects our protocol. So we're going to include price feed updates in our handler. So what we're going to do is we're going to go ahead and do import a mock v3 aggregator from //mocks/mock v3 aggregator.sol. Or where is this located? Oh, just one like this. Okay. And this mock v3 aggregator has some functions that allow us to just easily update an answer, right? Which is something that we want to do. We want our protocol to be able to easily update answers. So we'll take this mock v3 aggregator and let's at least get the WETH price from our system. So I have a view function, dsce.get collateral token price feed, and I'll pass the address WETH. Oops. And I'll say ETH, and I'll make another variable, mock v3 aggregator, public ETH USD price feed. I'll say ETH USD price feed equals this, and we just got to wrap this up as a mock v3 aggregator like this. And great, now we have an ETH USD price feed. And now we can add a new function in here. So we have mint DSC, deposit collateral, redeem collateral. We can add a new one called function update collateral price. We'll do a uint 96 just so that the number isn't too big, new price. And then we could also randomize the collateral, but for now, we'll just have it be the ETH USD. So we need to convert a uint 96 to an int 256, new price, int equals int 256 new price, because price feeds take int 256s. Oops, sorry, this should be in. And to convert a uint 96 to an int 256, we actually have to wrap it as uint 256 first, and then to an int 96. Dot update answer, or set price, or whatever we want to do to this new price, like this. Boom. And now, simple as that, we have an update collateral price, well, an update ETH price anyways. So now we can do three things in our system. We can update the price, redeem collateral, deposit collateral, and mint DSC. So before we actually run this, what do you think? Do you think we'll get an error? What do you think will go on? Let's run this. Whoa, it looks like it found a sequence. It found an issue. The reason, assertion violated, which means that our invariant here was broken. The WETH value plus Bitcoin value now is no longer the total supply. So let's scroll up. Let's see what the issue is here, all the way past everything. And if we read the sequence, we can figure out why this broke. We can see exactly what happened. Okay, so first it called deposit collateral. Okay, cool. So it deposited some collateral. And then we minted some DSC. Okay, cool. We minted some DSC with some stuff here. And then we updated the collateral price to 471. So as we know, our handler update collateral price, if we scroll all the way to the bottom, update collateral price 471 updates the ETH collateral from $2,000, which is 2000 E8, to 471. So this, remember, is 2000, 1, 2, 3, 4, 5, 6, 7, 8. It went from this to 471. So of course it reverted, right? Because people minted a ton of collateral. They deposited collateral. They minted a ton of DSC, right? Look at this input. It's massive. And the system broke. And if we run this again with fewer Vs, right, VV, we'll be able to see that total supply. If we scroll up, we'll be able to see the WETH value, wrap Bitcoin value, and the total supply here. So actually it looks like in this one, it's set the new price to 3. So obviously the WETH value is probably 0 or just about 0. It let them mint DSC because originally the collateral was worth something, and now it's worth almost nothing, right? So this is an important thing for us to take in mind in our system. Hey, if the price drops or spikes quickly, our system is screwed. Our system is busted. And this is something we would want to know about and potentially go back in our code and fix. Hey, what do we do when the price plummets in a single block? Right now, we have kind of this assumption in here where we have this liquidation 10% bonus, and the collateral always needs to be 200% over collateralized. With this, we're saying, okay, between 200% over collateralization and 110% over collateralization, as long as our system is within this, it's still safe. I mean, obviously it's better if it's above this, but as long as our system is within this, it's still safe. But if the price plummets of some collateral, and let's say that's the only collateral, maybe we get to 50% collateralization rate, and that would break our entire system, right? That would break our invariant, and our system will be screwed. So we can go back to the drawing board, figure out how to smooth this out, or we could say this is a known bug. If the price fluctuates or explodes too quickly or too slowly, this protocol becomes worthless. And that's kind of not a great solution, right? So these are things we absolutely want to keep in mind. And these are things that we can find with invariant tests. And this is why they're so important. So for now, in our handler, I'm actually just going to even comment this out because it does break our test suite. But I'm going to put a little comment here. This breaks our invariant test suite. And this would 100% be something that shows up in a smart contract audit saying, hey, if the price of an asset plummets too quickly, the system's breaking because it breaks the invariant. All right, great. Now there's a few more things I want to teach. Only a few, and then we're done with this section. We're going to teach one, some proper Oracle use. And then two, we would need to write more tests, which we're not going to do. I'm going to leave that to you. But we have a whole bunch of other contracts in here, like the decentralized stablecoin. And then three, some smart contract audit preparedness, some smart contract audit preparation. So let's start with some Oracle proper use. So in our DSC engine, we're of course using an Oracle, right? We're using Chainlink price feeds. Now, this is kind of an assumption that we have in our protocol right now. Price feeds are just going to work. But price feeds are a system just like anything else. And we should add some checks in our code here just to make sure that if this breaks or if something in here breaks, our system isn't broken. So what we're going to do is we're actually use that library methodology we made years ago to write some checks on this price feed. So I'm going to make a libraries folder, and we're going to make a new contract in here called oraclelib.sol. And what we want to do is we want to check to make sure that these prices aren't stale. If we click on any one of these prices like ETH, USD, and let's scroll up to show more details. You can see they have this heartbeat where a new price should show up at least every 3,600 seconds. I believe what this is, right? Yes, on the Spolia testnet. We want to write some checks to make sure that this is actually updating every 3,600 seconds. And if it's not, we should probably pause the functionality of our contract. So we're going to make a SPDX license identifier MIT, pragma solidity like this. We're going to do a library, Oracle lib, and let's put a little nat spec to explain what this is going to do. Say at title, Patrick Collins, title, Oracle lib, at author, Patrick Collins, at notice, this library is used to check the Chainlink Oracle for stale. If a price is stale, the function will revert and render the DSCE engine unusable. This is by design. So we're going to say, hey, if a Chainlink price feed is stale, just stop. Don't let anything happen. Because if a price is wrong, if a price is bad, our whole protocol is kind of bunked, right? So we want to just freeze everything. So we want the DSC engine to freeze if prices become stale. So if the Chainlink network explodes and you have a lot of money locked in the protocol, too bad. this is something that's going to be a known issue, right? If the Chainlink network blows up and all the prices become stale, you're kind of screwed, right? And maybe this is something we want to account for. But for now, I'm just going to say that's a known issue and we're going to move on. And this is where you'll see me start to get more and more particular about stuff. This is where, as we get more and more advanced, this is where the details start to matter more and more, right? All those little things that I kind of gloss over, they start to become more and more important as this becomes closer and closer to a real production product that should go to audit, right? So let's create a stale price check function. So we'll create a function, stale price check. And we'll have this stale price check be on an aggregator v3 interface.sol. So I'm actually going to copy this, paste it in here, toggle the word wrap. And so as an input parameter, it's going to take aggregator v3 interface, price feed. This will be a public view, which will returns a uint 80, int 256, uint 256, uint 256, and a uint 80. The same return value of the latest round data function in an aggregator v3 interface. Function like this, uint 80. Okay, cool. And in here, what we're going to do is we're going to call price feed dot latest round data. And I'm even just going to cheat a little bit. We're going to control click into this. We're going to copy this line, paste it here, equals, boom, just so I don't have to type as much. Cool, we have all those. And what we're going to say in here, and we're probably not even going to use all these, we're going to have some stale check, right? So each one of these price feeds has their own heartbeat. So we probably should ask them what their heartbeat is, but I'm just going to hard code it for this one. I'm going to say uint 256 private constant timeout equals 3 hours. And this is a constant in Solidity. It stands for 3 times 60 minutes times 60 seconds equals this many seconds. So looks like this heartbeat is actually much longer than the one that Chainlink should allow. So 360 seconds is 3,600 seconds is just 1 hour, right? We're going to give it 3 hours. So what we're going to say in here is we're going to say, first we're going to do a uint 56 seconds since equals block.timestamp. And then we'll have, minus updated app. And then we'll say, so this will get the current block timestamp minus this updated app. So this should basically get us the seconds since this price feed was updated. Then we'll say if seconds since is greater than our timeout, then we're going to revert with a new error, Oracle lib underscore stale price, like this, revert with stale price. And then we're just going to return all of this stuff. So return round ID, answer, started at, updated at, answered around. And I'm going to change this name to stale check latest round data. Now, what we can do, since this is a library on our price feed, we can use this stale check latest round data to automatically check to see if the price is stale. So now in our DSC engine, anytime we call latest round data, we just swap it out for stale check latest round data. So long as at the top we go after our errors, we're going to put our types. So after the errors, we're going to put types. So this is where we would do using Oracle lib or aggregator v3 interface. We need to import Oracle lib. Let's import Oracle lib from, /libraries /oracle lib.sol, like this. And now, yep, any place we use latest round data, we can now use stale check latest round data where we have this stale check baked in. And cool. Now we did a ton of refactoring. Let's run forge test just to run this whole test suite, including the invariant test suite. Okay, and stuff's looking good here. And you can see that it even took a lot of extra time to run this last bit. So cool. So we've We got a little check here. Great. We're not going to write some more tests. This is something that you should 100% do. If we pull up our terminal here, we run forge coverage. What do you think we get? We get this, which you can see there's a whole bunch of contracts that we need to test. This Oracle lib could probably use its own test suite, even though it's looking like a lot of it's tested. We probably should definitely test this ourselves. We need to write tests for this. We probably want to test our DSC some more for sure. So we should definitely write some more tests. I'm going to leave that to you. This little finger here. And then finally, some smart contract audit preparation. So we talked a little bit about what a smart contract audit is. And we haven't covered a whole lot of security stuff yet. We're going to do that later in the course. But a solid place you can look is this audit readiness checklist from the nascent XYZ GitHub repo, which has a lot of different things that you should and keep in mind when running your tests. For those of you looking to be really serious about actually launching a protocol and really having the security mindset that you need as well, be sure to get to this last section in the course about intro to security, because this is where we're going to give you a lot of that lower level security stuff, at least from a smart contract developer perspective. We're going to give you all the basics that you need to be aware of in order to stay secure. So we're not going to talk about it too much in this one, but it is something that if we were to actually launch this, we would need to keep in mind. So I'll put a little soon emoji here for coming very soon. All right. So with that all being said, we've done an absolute ton here. This is 1000% a project you should push up to your GitHub repo. And this is 1000% a project that if you made it this far, you should be incredibly proud of yourself. This is the hardest, most complicated, most advanced project in this course. And to be honest, probably the most advanced project you'll work on in almost all of Web3. There's so much going on here. We learned about DeFi. We learned about advanced state-of-the-art modern fuzzing techniques. We learned a tiny bit about security. We used oracles in a safer way. We wrote this crazy, amazing test suite. We wrote deploy scripts for this. We interacted with a couple different libraries. We learned about this fail on revert, runs, depths, and variance. The only thing we didn't do was write a proper README, which you 100% should write a proper README. And if you want, you can check out the Foundry DeFi Stablecoin README to see how it actually works, of course. Even for me, this was a long, difficult project for me to build because there's just so much to think about. Like I said, this is a project that I am planning on getting audited. So what you're going to see in this repo is you're going to see kind of this main branch, which is what you're going to be working on. But I'm additionally going to make a new branch called like audited or post audit or something like that. And if you want to follow and watch this GitHub repo, you can see the progress and you can see the audit reports that come out on here so that you can be intimately familiar with this code base already because you wrote some of the code, and then also see as it progresses through its security journey. And for those of you who are looking to actually release production code, you definitely need to be at least aware of how security works and the security paths that your code should take. But all right, with all of this being said, you know what time it is. It's time for you to get a break. You deserve it. You should 100% go take a lap, push this code base up to GitHub, and actually clean it up a little bit. I'm going to be cleaning this up a little bit before I push the rest of it to this GitHub repo. So you should clean it up a little bit. Make it yours. Make it the way that you want to make it. Maybe even improve on it, right? We saw with the invariant test that there is at least one other glaring issue with this protocol. If the price of the assets collapse too quickly, our protocol becomes insolvent. So maybe you come up with a method to fix it. And then maybe you launch your own stablecoin. Why not, right? In any case, good luck to you. Take that break. We're getting so close. We only have 1, 2, 3 more lessons. And these ones are actually easier than the one we just did. We're going to learn about upgrades and proxies. We're going to learn about governance. And then we're going to do an introduction to smart contract security. These are much easier than everything you've done so far. So take the break, give yourself a pat on the back, be incredibly excited, celebrate this win. This is a huge achievement getting this far, and I'll see you very soon. 3 more left. And as a bonus piece of content here, another one of the reasons that I absolutely love the Aave protocol and the Aave team is that they're just shipping protocols and shipping amazing products and features and services for the Web3 community. One of those protocols is something called Lens Protocol, which is a decentralized social layer or a decentralized social platform for building social medias. So to give us some information about this, we have the head of DevRel for Lens Protocol on the Aave team, Nader Dabit, to talk a little bit more about Lens.
Hi, my name is Nader Dabit. I wanted to give you a quick introduction to Lens Protocol and why it might be interesting to you as a smart contract or Solidity engineer. Lens is the social layer of Web3. It allows developers to build social applications or to implement social features into their existing applications. There are 4.9 billion people in the world today already using social applications, so these types of apps provide a use case that people already know, understand, and value. They also present a wide variety of value propositions and opportunities for developers to take advantage of and build on. And with Web3 features like native payments, ownership, and composability also provide a lot of primitives to build on that were not available with traditional social applications or infrastructure. Lens allows developers to extend the core smart contracts by building out their own custom modules. This would be similar to as if Twitter, Instagram, or other social applications allowed developers to send pull requests into their backends and APIs. This opens the door to a lot of interesting and powerful functionality that we're seeing developers integrate into their applications, build out new, different ideas, but also integrate into other parts of Web3 like DeFi. In addition to that, you can call Lens smart contracts from other smart contracts. So if you'd like to build out something that is composable with the Web3 social graph, Lens is a great place to integrate. If you want to get started building on Lens, check out the docs at docs.lens.xyz and be sure to check out how to deploy the protocol on your own so you can check out the smart contract code and play around with it, and also look at how to build out and create your own custom modules. Thanks for checking this out.
All right, and welcome to Lesson 13, Boundary Upgrades, where we're going to learn about upgradable smart contracts, the pros and their cons. Now, I've actually done a couple different versions of this type of video in the past, so we're going to go through an old video explaining the concepts of this, then we're going to move over to Remix, and we're going to explain an important sub-lesson, and then we're going to go to our VS Code, and we're actually going to do all of this in Foundry. Upgradable smart contracts are something that I'm going to go ahead and just say right out loud, we should deploy as little as possible. We should not be defaulting to upgradable smart contracts. It sounds like a good idea in theory, but we've seen time and time again, whenever a protocol has a centralized control over contracts, issues happen, full stop. So when going through this course and when learning about this, keep this in mind. What are the downsides of upgradable smart contracts? And then you can begin to ask questions, have we seen examples in real life where these downsides have come to a fruition? And I'll say right now, 100% the answer is yes. So keep that in mind when watching this and use this knowledge to make yourself be an even better smart contract dev. So let's learn. Now I'm editing this video much later after I filmed it, hence why I have a beard. So I'll be jumping in from time to time, updating some of the sections.
When deploying your smart contracts on chain, we all know that those smart contracts are immutable or unchangeable. But what if I told you that they were mutable? Well, technically that wouldn't be correct. However, smart contracts actually can change all the time. When people transfer tokens, when people stake in a contract, or really do any type of functionality, those smart contracts have to update their balances and update their mappings and update their variables to reflect this. The reason that they're immutable is that the logic itself never changes and will be on chain like that forever. So technically, yes, once they are deployed, they are immutable. And this is actually one of the major benefits of smart contracts in the first place, that nobody can tamper with or screw with our smart contracts once we deploy them. However, this can be an issue if, for example, we want to upgrade our smart contract or protocol to do more things, or we want to fix some glaring bug or issue that we have. Now, even though we can't change the specific code that's been deployed to an address, we can actually do a lot more than you think. And in this video, we're going to explain the different methodologies behind upgrading your smart contracts, and then we're going to show you how to do it with Hardhat and OpenZeppelin. Huge shout out to a lot of OpenZeppelin and TrailBits articles that helped me put this video together, and a number of other sources as well, links in the description. So let's get to it. Now, at first glance, you might be thinking, if you can upgrade your smart contracts, then they're not really immutable then. And in a way, you'd be right. So when explaining kind of the different philosophies and patterns that we can use here, we do need to keep in mind the philosophies and decentralization implications that each one of these patterns have, as they do all have different advantages and disadvantages. And yes, some of the disadvantages here are going to affect decentrality. So we need to keep that in mind. And this is why it's so important that before you go ahead and jump in and start deploying upgradable smart contracts, you understand the trade-offs.
So we're going to talk about 3 different ways to upgrade your smart contracts. The first one being the not really / parameterized way to upgrade your smart contracts, the social migration method, and then the method that you probably have heard about, which is proxies, which have a ton of subcategories like metamorphic contracts, transparent upgradable proxies, and universal upgradable proxies.
So let's talk about the not really upgrading method, or the parameterization method, or whatever you want to call it. This is the simplest way to think about upgrading your smart contracts. And it really isn't upgrading our smart contracts because we can't really change the logic of the smart contract. Whatever logic that we've written is there. We also can't add new storage or state variables, so this is really not really upgrading, but it is something to think about. Upgrades is just parameterizing everything. Whatever logic that we've deployed is there, and that's what we're interacting with. This function means we just have a whole bunch of setter functions and we can update certain parameters. Like maybe we have a reward parameter that gives out a token at 1% every year or something like that. Maybe we have a setter function that says, hey, update that to 2% or update that to 4%. It's just a setter function that changes some variable. Now, the advantages here are obviously this is really simple to implement. The disadvantage is that if you didn't think of some logic or some functionality the first time you deployed their smart contract, that's too bad. You're stuck with it. You can't update the logic or really update anything with the parameterization, aka not really method. And the other thing you have to think about is who the admins are. Who has access to these setter functions, to these updating functions? If it's a single person, guess what? You have a centralized smart contract. Now, of course, you can add a governance contract to be the admin contract of your protocol, and that would be a decentralized way of doing this. So just keep that in mind. You can do this method, just need a governance protocol to do so. Another example of this might be a contract registry, and this is something actually that early versions of Aave used. Before you call a function, you actually check some contract registry that is updated as a parameter by somebody, and you get routed to that contract and you do your call there. Again, this really doesn't allow us to have the full functionality of upgrades here. You can argue that this registry is a mix of one of the later versions, but for all intents and purposes, this doesn't really give us that flexibility that we want for our upgrades. But some people might even think that upgrading your smart contract is ruining the decentrality. And one of the things that makes smart contracts so potent is that they are immutable, and that this is one of the benefits that they have. So there are some people who think that you shouldn't add any customization or any upgradability. You should deploy your contract and then that's it. TrailBits has actually argued that if you deploy your contract knowing that it can't be changed later, you take a little bit extra time making sure you get everything right, and there are often less security vulnerabilities because you're just setting it, forgetting it, and not looking at it again.
Now, if I wanted to upgrade a smart contract with this philosophy in mind, the philosophy that I do want to keep my smart contracts immutable, we can instead use the social migration method, which I previously called the yeet method, and now I think it's less funny, so we're just going to stick with social migration.
The social yeet method, or the migration method, is just when you deploy your new contract not connected to the old contract in any way, and by social convention, you tell everybody, hey, this new contract, this new one that we just deployed, yeah, this is the real one now. And it's just by convention of people migrating and over into using this new one that the upgrade is done. Hence my slang name of social yeet, because you yeet the first one out of the way and you move to the second one. I think I'm funny. This has the advantage of truly always saying, hey, this is our immutable smart contract, and this is our new one. This is really the truest definition of immutable, because since you give it no way of being upgraded in place, then if somebody calls that contract in 50,000 years in the future, it'll respond exactly the same. Another huge disadvantage here is that you have to have a totally new contract address. So if you're an ERC20 token, for example, you have to go convince all the exchanges to list your new contract address as the actual address. Keep in mind that when we do this, we do have to move the state of the first one over to the second one. So for example, if you're an ERC token moving to a new version of that ERC token, you do have to have a way to take all those mappings from the first contract and move it to the second one. Obviously, there are ways to do this since everything is on chain, but if you have a million transfer calls, I don't want to have to write the script that updates everyone's balance and figures out what everyone's balance is just so I can migrate to my new version of the contract. So there is a ton of social convention work here to do. Trail of Bits has actually written a fantastic blog on upgrading from a V1 to a V2 or etc. with this Yeet methodology. And they give a lot of steps for moving your storage and your state variables over to the new contract. So link in the description if you want to read that. Now let's get to our big ticket item. So in order to have a really robust upgrading mentality or philosophy, we need to have some type of methodology or framework that can update our state, keep our contract address, and allow us to update any type of logic in our smart contracts in an easy way. Which leads us to our big ticket item, the proxies.
What's our big ticket item?
Proxies.
It's people.
Proxies.
Proxies are the truest form of upgrades, since a user can keep interacting with the protocols through these proxies and not even notice that anything changed or even got updated. Now, these are also the places where you can screw up the easiest. Proxies use a lot of low-level functionality, and the main one being the delegate call functionality. Delegate call is a low-level function where the code in the target contract is executed in the context of the calling contract, and message.sender and message.value also don't change. So you understand what delegate call means now, right? Great. And in English, this means if I delegate call a function in contract B from contract A, I will do contract B's logic in contract A. So if contract B has a function that says, hey, store this value in a variable up top, I'm going to store that variable in contract A. This is the powerhouse, and this combined with the fallback function allows us to delegate all calls through a proxy contract address to some other contract. This means that I can have one proxy contract that will have the same address forever, and I can just point and route people to the correct implementation contract that has the logic. Whenever I want to upgrade, I just deploy a new implementation contract and point my proxy to that new implementation. Now, whenever a user calls a function on the proxy contract, I'm going to delegate call it to the new contract. I can just call an admin-only function on my proxy contract. Let's call it upgrade or something, and I make all the contract calls go to this new contract. When we're talking about proxies, there are 4 pieces of terminology that we want to keep in mind. First is the implementation contract. The implementation contract has all of our logic and all the pieces of our protocol. Whenever we upgrade, we actually launch a brand new implementation contract, the proxy contract. Proxy points to which implementation is the correct one and routes everyone's calls to the correct implementation contract. You can think the proxy contract sits on top of the implementations. The user is going to be making contract and function calls through the proxy contract, and then some type of admin. The admin is the one who's going to decide when to upgrade and which contract to point to. In this scenario, the other cool thing about the proxy and delegate call is that all my storage variables are going to be stored in the proxy contract and not in the implementation contract. This way, when I upgrade to a new logic contract, all of my data will stay on the proxy contract. So whenever I want to update my logic, just point to a new implementation contract. If I want to add a new storage variable or a new type of storage, I just add it in my logic contract and the proxy contract will pick it up. Now, using proxies has a couple of gotchas, and we're going to talk about the gotchas, and then we're going to talk about the different proxy contract methodologies, because yes, there are many proxy contract methodologies as well. And this is why Trail of Bits doesn't really recommend using upgradable proxies for your smart contracts, because they're fraught with a lot of these potential issues. Not to mention, again, you do still have some type of admin who's going to be upgrading your smart contracts. Now, if this is a governance protocol, then great, you're decentralized. But if this is a single group or entity, then we have a problem. The 2 biggest gotchas are storage clashes and function selector clashes. Now, what does this mean? When we use delegate call, remember, we do the logic of contract B inside contract A. So if contract B says we need to set value to 2, we go ahead and set value to 2. But these smart contracts are actually kind of dumb. we actually set the value of whatever is in the same storage location on contract A as contract B. So if our contract looks like this, and we have two variables in contract A, we're still going to set the first storage spot on contract A to the new value. This is really important to know because this means we can only append new storage variables in new implementation contracts, and we can't reorder or change old ones. This is called storage clashing, and in the implementations we're going to talk about, they all address this issue. The next one is called function selector clashes. When we tell our proxies to delegate call to one of these implementations, it uses what's called a function selector to find a function. The function selector is a 4-byte hash of the function name and the function signature. Don't worry about the function signature for now. Now, it's possible that a function in the implementation contract has the same function selector as an admin function in the proxy contract, which may cause you to do accidentally a whole bunch of weird stuff. For example, in this sample code in front of you, even though these functions are totally different, they actually have the same function selector. So yes, we can run into an issue where some harmless function like getPrice has the same function selector as upgrade proxy or destroy proxy or something like that. This leads to our first out of the 3 implementations of the proxy contracts. This is called the transparent proxy pattern. In this methodology, admins are only allowed to call admin functions, and they can't call any functions in the implementation contract. And users can only call functions in the implementation contract and not any admin contracts. This way, you can't ever accidentally have one of the two swapping and having a function selector clash and you running into a big issue where you call a function you probably shouldn't have. If you're an admin, you're calling admin functions. If you're a user, you're calling implementation functions. So if you're an admin and you build some crazy awesome DeFi protocol, you better come up with a new wallet address because you can't participate. The second type of proxy we're going to talk about is the universal upgradable proxy, or the UPS. This version of upgradable contracts actually puts all the logic of upgrading in the implementation itself. This way, the Solidity compiler will actually kick out and say, hey, we got 2 functions in here that have the same function selector. This is also advantageous because we have one less read that we have to do. We no longer have to check in the proxy contract if someone is an admin or not. This saves on gas, of course. And the proxy is also a little bit smaller because of this. The issue is that if you deploy an implementation contract without any upgradable functionality, you're stuck, and it's back to the yeet method with you. And the last pattern or methodology that we're going to talk about is the diamond pattern, which does a number of things. But one of the biggest things that it does, it actually allows for multiple implementation contracts. This addresses a couple different issues. For example, if your contract is so big and it doesn't fit into the one contract maximum size, you can just have multiple contracts through this multi-implementation method. It also allows you to make more granular upgrades. Like, you don't have to always deploy and upgrade your entire smart contract. You can just upgrade little pieces of it if you've chunked them out. All the proxies mentioned here have some type of Ethereum improvement proposal, and most of them are in the draft phase.
And at the end of this explainer, we will do a demo of showing you how the delegate call function works. And the end of the demo is right now. So let's look at delegate call. Now we're going to learn about how to actually build these proxies, how to build these upgradable smart contracts. And to do this, we first need to learn about this delegate call function. And it's going to be really similar to the call function, which we learned much earlier. If you haven't seen that, be sure to go back to our hard hat NFTs. We have a sub lesson in there about EVM opcodes, encoding, and calling, and we'll give you all the context for delegate call. Like I said in the explainer, it's very similar to call. However, the way that I think about it is one contract says, oh, I really like your function. I'm going to borrow it myself. And we're going to be looking at Solidity by example. I'll leave a description in the GitHub, and all of the code for this will be in the GitHub associated with this lesson as well. Now we have 2 contracts. We have this contract B that we're going to be deploying on Remix, and it looks like a real minimalistic, real simple contract. We have a couple of storage variables here, and then we have a function that updates our values. We have a function called setVars, and it updates our uint public num. Now, as we learned before, whenever we have some type of contract with storage variables, they get stored in this storage data structure that's indexed starting from 0. Right now, our uint public num is at index 0, our senders at index 1, our values at index 2, etc. Now we're going to deploy a contract A. And now this contract is actually going to use the delegate call function. Now in contract A, this is going to look a little bit different, but it's still going to have this setVars functions, except it's going to make a delegate call function call to our contract B. The difference here is we're doing contract.delegateCall. What this call does is something very similar to call. Normally, if we did contract.call on this contract, we would just call this, we would just be calling this function setVars, which would update contract B's storage. But instead, we're saying, hey, call that setVars function and then pass this as an input parameter, but call it in our contract. Call it on contract A. We're kind of borrowing a function for our contract. And so instead, what we're going to do is we're going to borrow this setVars and run this setVars function over here. Now, the difference is instead of num equals num, the variables could be named different than the variables on contract A. So instead of num equals num, our contract is going to say, hey, whatever's at storage of 0, have that equal to whatever we pass as an input parameter. And if that's a little bit confusing, just stay with me. Let's go ahead and let's see this in Remix. So I'm going to copy paste this code into Remix here so we can kind of test and see what this looks like. Again, there's a link to this in the GitHub repo associated with this course. Feel free to pause the video to grab this link. It's solidity-by-example.org/delegatecall. Or you can just grab the code directly from lesson 16, hard hat upgrades. So let's compile this code and let me show you what I mean. So I'm going to compile it and we'll go to the run tab. And first, let's deploy this contract B. We'll hit deploy. We now have a contract. Num, sender, and value are all blank. We'll update the number to something like 777. We'll hit set vars. Set vars will change the storage variable num to 777. And then we're changing the sender and the value. Sender and value is 0. Now let's deploy contract A. So we'll scroll back up. Contract A, deploy. Of course, we're on the JavaScript VM. Now we have this contract A with num, value, and sender are also all blank. But when we call setVars, it's going to borrow this setVars function from contract B and run it in contract A. You can almost think of it as if we're copying setVars and pasting it into our contract A just for one run and then immediately deleting it again. That's what this delegate call function does. So when I call setVars, I'm going to pass it this contract address as an input parameter so it knows to call this contract's setVars function. When I pass it the address and I pass 987, since we're borrowing the function, we're not going to update this num on contract B. We're going to update the num on contract A. So when I hit setVars, we see num now has 987, we see sender, and we see value still being 0 here. Because again, we're borrowing this function and running it here. Now, the way that this works is it actually doesn't look at the names of our storage variables. It looks at the storage slots. So when we borrow this function using delegate call, so we could have these variables be named anything. Instead of num, we could call this first value. Sender, we could call something else. And then value, we could call woo or whatever you want here. And when we borrow this function using delegate call, instead of us grabbing the actual names of the variables, our contract will swap out these variable names with the storage slot. So it says, oh, okay, well, in contract B, you're accessing the num variable, which is at storage slot 0. So when we borrow setVars in contract A with delegate call, we'll say storage slot 0 is going to equal that underscore num, which for this contract, storage slot 0 is first value. So we'll say first value equals underscore num. Something else is going to be storage slot 2. So it's going to say, okay, storage slot 2. We're going to update storage slot 2 to message.sender. Okay, value here is storage slot 3. So whatever's in storage slot 3 will update with message.value like this. So that's essentially what's going on behind the scenes. So let's go ahead, let's delete those and redeploy them. So we'll deploy contract B, we'll deploy contract A. Right now in B, once again, if we do 1, 2, 3 for setVars, we have 1, 2, 3. And in contract A, now even though these variables have different names, we could grab contract B's address, paste it in, do 654, hit setVars, and first value is now 654. So delegate call allows us to borrow functions and then just transposes whatever is in here to the storage location equivalents. And the other thing that's interesting is that even if you don't have variables, it'll still save to storage slots. So in contract A, if we didn't have any of those variable names, storage slots 0, 1, and 2 would still get updated.
Now, here's where things can get really interesting. Let's delete our contract A again, and let's change the type of our contract A's first value from a uint to a Boolean. Let's save that. And now let's deploy contract A. Now, when we call setVars on our contract A, it's still going to use the setVars function of contract B, which takes a uint and assigns the first storage slot that number we pass it. But our first storage slot is now a Boolean. So what do you think is going to happen now? Well, let's try it out. Let's copy contract B's address, paste it in here. We'll do 222 as our input parameter. We'll hit setVars. Our transaction actually does go through. And now when we look at first value, it says true. Huh, that's really weird. Well, what if we change setVars to 0 and hit setVars? And now first value is false. In storage here, when we add a number with setVars, it's going through because it's just setting the storage slot of the Boolean to a number. And when Solidity reads it, it goes, oh, well, first value is a Boolean. So if it's anything other than 0, it's going to be true. So this is how you can actually get some really weird results if your typings are different or if your storage variables are different. What if we made this an address? So this is where working with delegate call can get really weird and really tricky really fast. All right, now with all this being said, let's turn up the heat and let me show you a small proxy, a minimal proxy example that shows how a contract can be used as a singular address, but the underlying code can actually change. And all the code we're going to be working with once again in the Hard Hat Upgrades FCC sublesson smallproxy.sol. And you can go ahead, copy paste this code if you want to follow along. So you don't have to code along with me here, but you absolutely can if we want. Now, I will say this is going to be one of the most, if not the most advanced section of the entire course. So feel free to go ahead and skip over this sub lesson if you want to just move on to learning how to actually build these proxies without really understanding what's going on behind the scenes. However, it is still really powerful if you do understand what's going on behind the scenes. So I have this minimalistic starting position right here. I have small proxy is proxy, and I'm importing this proxy.sol thing from OpenZeppelin. OpenZeppelin has this minimalistic proxy contract that we can use to actually start working with this delegate call. Now, this contract uses a lot of assembly, or what's something called YUL, and it's an intermediate language that can be compiled to bytecode for different backends. It's a sort of inline assembly inside Solidity and allows you to write really, really low-level code close to the opcodes. Now, we're not going to go over YUL, but I'll leave some links to the YUL documentation if you want to learn more. Even if you're a really advanced user, you really want to try to use as little YUL as possible because since it is so much lower level, it is much easier to screw things up. However, like I said, for this example, we are going to be using a little bit of YUL. Now, in this proxy that we're going to be doing, we have this delegate function, which inside this inline assembly, which is YUL, it does a whole lot of really low-level stuff, but the main thing that it does is it goes ahead and it does this delegate call functionality. If we look here, we can see it's using a fallback function and a receive function. So whatever it receives a function it doesn't recognize, it'll call fallback, and fallback calls our delegate function. So anytime a proxy contract receives data for a function it doesn't recognize, it sends it over to some implementation contract where it will call it with delegate call. In our minimalistic example here, we have a function called setImplementation, which will change where those delegate calls are going to be sending. This could be equivalent to like upgrading your smart contract. And then we have implementation here to read where that implementation contract is. Now, to work with proxies, we really don't want to have anything in storage, because if we do delegate call and that delegate call changes some storage, we're going to screw up our contract's storage. The one caveat though to this, we do still need to store that implementation's address somewhere so we can call it. So EIP 1976 is called the standard proxy storage slot, which is an Ethereum improvement proposal for having certain storage slots specifically used for proxies. And in our minimalistic example here, we set byte32 private constant implementation slot to that location in storage. And we'll say, okay, whatever is at this storage slot is going to be
the location of the implementation address. So the way our proxy is going to work is any contract that calls this proxy contract, if it's not this set implementation function, it's going to pass it over to whatever is inside the implementation slot address. That's what we're going to build here. So we have this small proxy is proxy, and we'll create a real minimalistic contract. So we'll say contract implementation A, and we'll just give it a uint256 public value, and then function set value, uint256 new value, public. We'll say value equals new value. And so this is going to be our implementation. So now, anytime somebody calls small proxy or small proxy contract, it's going to delegate call it over to our implementation A, and then save the storage in our small proxy address. So we're going to call our small proxy with the data to use this set value function selector. So let's make it a little easier just to figure out how to get that data by creating a new helper function. We'll do function get data to transact. And we can get the data using the ABI.encode with signature that we learned in an earlier lesson. So function get data to transact. We'll pass it a uint256 number to update. So we'll give this the number we want to call a new value. We'll have this be a public pure that's going to return a bytes memory. And we'll just say return ABI.encode with signature set value uint256, comma, number to update. So you'll remember this from our call anything section. And if you don't remember how to do that, remember to refer back to our NFT section to learn how to call anything and use ABI.encode with a signature, and call anything with its raw bytes. We're going to get the data to transact. And we know that when we call implementation A from our small proxy, we're going to update our small proxy's storage. So we'll create a little function in Solidity just to read our storage in small proxy. So we're going to say function read storage, and this will just be a public view. And we'll do returns uint256 value at storage slot 0. And we are going to use a little bit of assembly here since we are doing all this low level stuff. And we're going to call the sload opcode to read the value at storage slot 0. We'll say value at storage slot 0, and we're going to set it. And then in assembly, this is how we set things. We're going to set it equal to sload of storage slot 0, and then it will return this value here. So we're reading directly from storage. Oops, and then we need a little parenthesis here, sorry. So let's go ahead and deploy our small proxy, and let's deploy our implementation A. Now, our small proxy has a function called set implementation. So we're saying, okay, anytime we call this proxy contract, we're going to delegate call the functions over to here. So we're going to grab implementations A's address, paste it into set implementation 777. So this is the data of set value uint256 with that number to update encoded in it. So if we call our small proxy with this data, our proxy contract is going to go, oh, okay, this is a function. I don't see that function here. We're going to call our fallback, right? Which again is coming from OpenZeppelin, and our fallback is going to do this delegate, which is this low level stuff, but it's basically just doing a delegate call. We're going to call our fallback function, and then we're going to get the function in the implementation A. We're going to borrow this function, and we're going to use it on ourself. So if I copy this, the implementation has been set to being this address down here. So all the logic is going to be down here. So when I go ahead and I grab this, I paste it into call data, and I hit transact, looks like it successfully went through. If I read storage now, we see that it is indeed 777, which is incredibly exciting. Now, this is incredibly beneficial because now let's say we want to go and update our code, right? We don't like contract implementation anymore. So let's go ahead, copy contract implementation A, and we'll make a new one called implementation B. Now let's say whenever somebody calls set value, we do value equals new value plus 1 or plus 2. Let's go ahead. Let's save this. Let's compile this. And let's deploy implementation B. We'll grab implementation B's contract address. We'll call it on set implementation in our proxy. And essentially, we have now upgraded from implementation A to implementation B. Now, if we use this same data here, we're still going to call set value with 777, but instead, we're now delegate calling to implementation B instead of implementation A. So if I put this data into the low-level call data and I hit transact, it looks like it went through. Now I read storage, and now is 779 since doing value equals new value plus 2. So this is a minimalistic example of how upgrading actually works. Now this is incredibly beneficial because we can always just tell people, hey, make all your function calls to small proxy and you'll be good to go. But like I said before, this also means that the developers of this protocol can essentially change the underlying logic at any time. This is why it is so important to be sure to read contracts and check to see who has the developer keys and if a contract can be updated. If a contract can be updated and a single person can update it, well, guess what? You have a single centralized point of failure, and technically the contract isn't even decentralized. Now, something else I was talking about in the video is function clashes, function selector clashes. Right now, whenever we call set implementation, the proxy function set implementation gets called because we don't trigger the fallback because we can see the function is here. However, if I have a function called set implementation in our implementation, this one can never be called. Whenever we send a function signature of set implementation, it's always going to call the one on the proxy. This is where the transparent proxy that we're going to be working with can help us out here, and the universal upgradable proxy can help us too. And I'm not going to go too much deeper into these now, but we've left some links in the GitHub repository to teach you more about these selector clashes and how those two proxy patterns that I just mentioned, the transparent and universal upgradable, can get around these. If you're confused by anything in here, go into this discussions thread and make a new discussion about proxies. Make a new discussion about the assembly, about the UL set implementation. This is a great time to connect with other people taking the course and ask questions here, because I know that this is a really advanced section and requires you having gone through a lot of those sub lessons that we've gone before. And if it takes you a couple times of playing around with Solidity and playing around with Remix, I definitely recommend you do so. This is a section where seeing really is believing. And I want you to jump into Remix, and I want you to test this, and I want you to play around with this and see what you can break and fiddle with. All right, so now that we've learned all about this delegate call function and what it can do and the power of it, let's actually put it to use. Let's actually build an upgradable contract example so we can really see this power. So let's go ahead and let's start doing this. Of course, all the code that we're going to be going over with is available in the GitHub repo associated with this course if you want to follow along. So let's go ahead, make a new directory, Foundry upgrades -F23. Let's code Foundry upgrades F23 or file open folder. You know the drill. Now, I know in that video, we talked a lot about this transparent proxy pattern versus the UUPFs. We're actually going to be teaching the UUPS proxy. In the UUPS proxy, the upgrade is handled by the implementation and can eventually be removed. And this is incredibly important, especially if we want to heed my warning I made at the beginning, where we want to really do this as little as possible. And this is kind of a crutch to get started. And we've seen issues where if you have upgradability and you have a centralized entity that can upgrade and change your contracts, those are often exploited. So the UUPS proxy allows us to eventually remove the upgradability so that the code is truly immutable. And also, UUPS proxies are technically a little bit cheaper to deploy. You can read more about the differences between the two proxy types in the documentation for OpenZeppelin. And additionally, if you go to the contract wizard in OpenZeppelin, most of these types in here have a upgradability option with UUPFs that we could even open in Remix and see exactly what some of these might look like. So we're going to be going through that with our own example here. So we're going to go ahead, we're in our folder, we're going to do forge init, of course, and we're going to go and delete these once again. Goodbye, goodbye, goodbye. delete, move the trash. I held down Command so I could select all three. And let's create a very minimal contract that we're going to actually upgrade. So we're going to say a box v1.sol, and this is going to be what we're going to upgrade. So in this box v1, we're going to do SPDX, license, identifier MIT, you know the drill, MIT, pragma solidity 0.818 with a little caret here, contract box v1 like this. Cool. Now, so since we're using the UUPS proxy, we're actually going to need to add all of the proxy upgradability into this contract as well. So we can actually borrow from OpenZeppelin, kind of like what we were seeing here, because they have all of these contracts already created for us. But let's actually just write out what we'd want our box to do first, and then we'll go ahead and do that. So we'll say a uint256 internal value or number, a little bit less confusing. We'll have a function get number, public view, or better yet, external view returns uint256, return number. All of this is something you all get because you did the Stablecoin video, which was a monster of a project. Version external here returns uint256 return 1, and that's it. This is all our box is going to do. Now let's copy this box. Let's go to our source. We'll create a box v2.sol, paste all that in here, and let's change this a little bit. Let's have the version return 2. Get number will still return number, but let's add a function set number uint256 underscore number. This will be external, null, like this. But so here's, oh, and this, rename this to box v2. Okay, cool. So now we have our box v1. We're going to deploy box v1, and then at the contract address of box v1, we're going to upgrade it to box v2. Now remember though, if we upgraded it, changed some storage variables, we would mess it up, right? So if you go to the OpenZeppelin documentation, let's actually reopen this back up in Remix here. We can see kind of what's going on here. So this token example that they have, they say it's initializable, upgradable, ownable, and UUPS upgradable. They say it's all this stuff. So for us, we're going to go ahead and we're going to install this OpenZeppelin contracts upgradable package. And this is actually at a different OpenZeppelin repo. If we look up OpenZeppelin contracts upgrade, GitHub. There's this OpenZeppelin/OpenZeppelin contracts upgradable repository that we can use. And this is the one that we're going to want to install. So we're going to copy this like that, forge, install this --no -commit. All right, great. We've installed it. Now we can start using these contracts upgradable code in here. Let's just go in here, do a remappings equals. We'll say at OpenZeppelin/contracts upgradable equals lib/OpenZeppelin. And let's do a toggle word wrap. Zeppelin contracts upgradable/contracts. Hopefully that looks right. Let's go to lib. OpenZeppelin contracts upgradable. Yep, that looks right. Okay, cool. So now we can start using this. So in this remix example, it can be a little bit confusing because there's a lot of imports going on, right? So let's kind of break this down. So the first thing that we're going to need is going to be this UUPS upgradable contract. And I'm just going to copy this line. Feel free to copy this line as well, or write it out yourself. And I'm going to toggle the word wrap here. And of course, we're going to do named imports because we're good engineers. What did I mess up? Oh, I don't need this versioning. Okay, cool. And if we control click into this, or we command click in this, or we just open this, we can see exactly what is in this upgradable code here. So we have this UUPS upgradable contract. It's initializable. It's some proxy stuff, yada, yada, yada. We scroll down, it's got some modifiers, it has this function upgrade to, address new implementation, upgrade to and call, and it has this gap at the bottom. So let's talk about these. So this upgrade to function, this is the function that gets called when we want to upgrade our box. So we're going to say our box is UUPS upgradable. And then it's going to say, hey, it should be marked abstract because we don't have all of the functions defined in here. And this contract is actually known as an abstract contract. Abstract contracts have some functions defined and some functions undefined, and they expect their child classes to implement those functions. So for example, at the bottom here, we have this authorize upgrade function, which isn't defined. So an abstract contract basically says, hey, you better define this authorize upgrade function because I'm not going to do it. You need to do this. And this can be helpful for a lot of reasons, right? For example, let's say you want to make sure to not forget to add some function. So this is something that we're going to need to define. These are how we're going to actually do the upgrades. We see that this is, obviously the function that we're going to have to define. So we can add authorization parameters in here, such as who can actually do the authorization. So if I toggle the word wrap, we can see function that should revert when message.sender is not authorized to upgrade the contract. So for example, if you wanted your proxy to be owned by a DAO, you would update this to be ownable or only owner or something like that. But then they call this upgrade to and call UUPS, which if we control click into, or we just go to where it's defined, we toggle the word wrap here. We can see this performs the implementation upgrade with security checks for UUPS proxies and additional setup. So if we scroll into here, this is the code that's actually doing the upgrade, and it's really low level, right? So we call this function set implementation, which now routes all contract calls via delegate call to this new implementation address that we set. And then it does a couple of checks in here, and then it calls upgrade to and call, which calls upgrade to, which calls set implementation, which mainly just sets the implementation slot, which basically, like I was saying before, it says, okay, all contracts are going to be routed to this address now, right? But if we go all the way back, that's kind of the long of what this upgrade to is going to do, right? So it's going to change where we route all of our delegate calls. And then if we have any data we want to send, it'll call this as well. The data is obviously going to be none if you just call upgrade to. Anyways, I'm getting kind of in the weeds here, right? This is the function that it has set up to do the proxy stuff we showed before, right? This changes the implementation address. So we obviously need this. We also need to implement our own authorize upgrade function. So we can just go ahead and copy this. And in here, we'll paste it in here. And for us, we need to make this override instead of virtual. I'm just going to leave it blank because I don't really care. I don't want any authorization stuff in here, right? But this is where I'd put require, or excuse me, if, message.sender does not equal owner, revert, right? Right. But for us, I don't really care. So I'm just going to leave it blank, right? And so this is going to say anybody can upgrade this. So this is why this is going to be the most important one, right? This UUPS upgradable is doing all that proxy upgrade stuff. All right, cool. So what else? Now, you'll also notice here at the bottom, there's this gap thing. Now you can read the docs here. This empty reserve space is put in place to allow future versions to add new variables without shifting down storage in the inheritance chain. What the heck? What are you talking about? Storage gaps. The reason these proxies work is that they point to the slot number instead of the name of variables. So if I were to upgrade from box v1 to box v2 and I put in other number here, guess what? If I did this upgrade, whatever number was in box v1 is now set to other number instead of number. This is because proxies point to storage slots. They don't point to variable names. They point to storage slots. If we upgrade to v2, other number is now in storage slot 0, whereas number was in storage slot 0 over here, right? So what is the best practice to do is to have this gap at the bottom. So a uint 256, you can put really whatever number you want here, which basically just says, hey, we're going to save 50 storage slots in storage for adding new variables in the future. You could have this be, 100, whatever amount you want, right? And this is just so that in the future, if you need to add more storage slots, you don't collide with other places that storage is already being reserved. So it's really important that they have this gap, especially for UUPS. If this doesn't make sense, definitely 100% be asking questions about it. And you'll see a lot of people will even manually add their own gaps sometimes. So sometimes you'll even see somebody go, like gap 2 or whatever they want, right? So that they have additional gaps, whatever they want to do. Cool. So this is why we need this. Now, right like this, we could ship this code and this would be upgradable. Now, of course, Box v2 is not upgradable, but Box v1 would be upgradable. So why is Remix adding all this other stuff? What is initializable? Well, let's copy this and let's paste it in. And you can also see all this weird initialized stuff. What is going on with that? Well, let's add this in. And of course, we're going to do a named proxy. If you want to write this out yourself, feel free. Excuse me, we're going to remove this because we did not add the version in here. Initializable. So what is this? Why is OpenZeppelin telling me I got to do this initializable thing and it's doing all this weird initialized stuff? So let's go into initializable. Oh, and if it doesn't let you do that, let's open up our file explorer. We'll look for initializable.so and let's see, let's read this. So if you want to pause and you want to read this, I'm even going to toggle the word wrap. If you want to pause and you want to read this, feel free to do that. But the main thing we know is this piece here. Since Proxies contracts do not make use of a constructor, it's common to move constructor logic to an external initializer function. You might be thinking, wait, what? They don't use a constructor? Remember, storage is stored in the proxy, not the implementation. So we have proxy, which will direct all calls to the implementation, but it's like borrowing the implementation functions, right? So all the storage is happening over here. If the implementation has a constructor and it sets number to 1, right? The proxy will have number still set to 0. Because when you deploy a contract, the constructor gets called from the implementation. So proxy contracts or contracts that are meant to be used via proxy don't use the constructor. So what you need to do is then with a proxy, you need to deploy implementation. Then you need to call some initializer function. Now the initializer function is going to be essentially your constructor, except for it's going to be called on the proxy. So that's kind of the difference. If that doesn't make sense, please ask questions about it because it's really important. So constructors are not used in proxy contracts. So what a lot of upgradable contracts do is they call this disable initializers function in constructors, like you see here. And I'm actually going to copy this, paste it into my box v1 like this. And then often you'll see this comment. I'm going to paste this over here because sometimes different linters will say, hey, you're using a constructor in a upgradable contract. You shouldn't do that. So we just say, hey, let it happen, right? What this disable initializers function does is it says, hey, don't let any initialization happen. So if we go see this, we say require that you're not initializing, right? You can't call any initializer functions. So you could just as easily just do this, right? They're kind of the same, but this is much more verbose, right? This is making sure, hey, don't do any initializers. Constructor, don't do anything. So this and this are almost the same, but this is more verbose. As you know, verbose is better. But let's say we do want a constructor. What we would do is we would add an initializer. So we do something like function initialize public initializer. Initializer. And of course, we'd say our box v1 is initializable, public initializer, like this. And we would add whatever we want to initialize. And then what we're going to do is we're going to deploy the contract. And then we're going to have the proxy immediately call our initialize function. Instead of doing this constructor, instead of the implementation having the storage, we want the proxy to have the storage. Typically, you'll see initializer functions have 2 underscores like this. So if we want our box v1 to have an owner, right, we can't set storage. We can't do like owner equals message.sender in the constructor like we normally do with a ownable contract. Instead, we need to put that in the initializer function. So what a lot of people will do is they'll add double underscore like ownable underscore init. Like let's say we did want this to be ownable, and actually let's go ahead and add that right now. We're going to add this ownable upgradable. I'm going to paste it in. I'm going to remove that. Ownable from like this, comma. I know I kind of was quick, but I know you all are advanced enough to kind of know what I just did here. I refactored this a little bit, so that's a named import, remove the version, and now we're doing this ownable upgradable instead of ownable. I'll explain what that means in a second. Oh, and this actually goes here. A note, if you see this linearization of inheritance graph impossible, this means that we're trying to inherit stuff in the wrong order. So we'll just do this. Oh, is that the right order? No, that's still the wrong order. Is that the right order? Cool, that's the right order. Okay. So what you'll see is these upgradable initializable functions will be prepended with double underscores, right? And so what this is doing is it's setting the owner to message.sender. And if I command click into this, or I command click into this, we look up ownable init. We see it does this ownable init unchained. All it's doing is calling transfer ownership, right? That's it. This is essentially the same as setting owner equals message.sender, right? But we're just prepending it with the double underscore to say, hey, this is an initializer function, treated as such, right? It should only be called in this initialize section. Additionally, most of the time you'll see this initializer function, which doesn't do anything, but it's best practice to have this in here to say, hey, this is a UUPS upgradable contract. We're going to treat it as such. Okay. So you'll see this in here a lot too. But I know I kind of went through this a little bit quickly, but let's just do a quick recap of what we learned. We can't use constructors with our proxies. A constructor adds storage to the implementation. And if we have a proxy pointing to an implementation, the implementation would have the storage of where the owner is, and we need the proxy to have the storage of where the owner is. So we need to call initialize through the proxy, not through the implementation. The initializer function is essentially a constructor for proxies. You can almost think of it like that. We want to prepend them with this double underscore to know that they're initializers, and we don't want any initializers to run in the constructor, and we only want them to run once. You'll also see this initializer modifier, which basically just says, hey, you can only initialize one time, right? A contract can only be initialized once, otherwise it'll error. Great. And that's pretty much going to be our box. So now we made this ownable. So since this is ownable, down here in our authorized upgrade, we could add an only owner modifier in here so that only the owner could upgrade it if we wanted to. But we're not going to add that, but I wanted to add this ownable init here just to show you, hey, like, so this is what you do instead of working with constructors. So that's our box v1. Let's fix our box v2. So our box v2, we're going to do pretty much the same thing. So we're going to grab all these, paste it in here. I'm going to toggle the word wrap. We're going to make this initializable, ownable upgradable, and UUPS upgradable is like this. We're going to need to add authorize upgrade, which we're going to keep blank. But if you want to play with this, you can obviously implement this. We're going to want to add a constructor and an initializer. So we're going to copy both of these and just paste it right in here. A constructor which disables constructors, and then an initializer, which is going to be really what we want. And that's pretty much it. That's the only changes that we need to make. Now we can make this even smaller, right? We could say, okay, cool. We don't care about upgrades. We don't care about initializing. And we just say, goodbye. This doesn't need an initializer. This doesn't need any of that stuff. And we could even delete all of this if we wanted. And now it's just UUPS upgradable, right? Without any initializer and without any constructors. And we could do the same thing with box v1, but I just wanted to demo what it would look like if you did want a constructor. But now that we've done all this work, let's actually show you this in action. So we're going to deploy box v1. We're going to get an address. We're going to use that proxy address to make sure that these functions work. We're going to then deploy box v2. We're going to point our proxy to box v2, which will essentially mean we upgraded our contract, and it's all going to be from the same address. So let's do this. We're going to make a little 2 scripts. We're going to make one called deploybox.s.sol and a new one called upgradebox.s.sol. So we're going to deploy the box, and then we're going to upgrade it. So let's deploy it. SPDX, you know the drill. License. Pragma, Solidity, 0.8.18. Contract, deploy, box is script. Import, script from forge, std/script.sol. We're going to need to import box v1 from ./src/box v1.sol. Function run external returns. I'm gonna return address, and you'll see why in a bit. Returns address proxy equals deploy box turn proxy, and I'm gonna create a deploy box function deploy box. So this is a little bit different. This will be a public returns address, and what we're gonna do is say box v1 box equals new box v1. This is going to be our what? Our implementation. This is going to be our logic, right? This is where our proxy is going to point to delegate call, right? To borrow those functions. Now, we're going to need to get a proxy on top of this. The proxy that we're going to use is the ERC 1967 proxy. And we can learn more about this proxy in the Open Zeppelin documentation. We can learn more about this at the EIP for ERC 1976, whatever you want to do. But it's going to be this proxy that we're going to use to point to our implementation, right? To point to our box v1, which has all this upgradable logic in it. So we're going to import that. We're going to import ERC 1967 proxy from, and this is actually just a regular Open Zeppelin contract. So we're going to do forge install Open Zeppelin /Open Zeppelin contracts. This is just a regular one, contracts. Oops. --no-commit. We're going to go to our foundry.toml, and this is a remapping, comma, at Open Zeppelin /contracts equals lib /Open Zeppelin Open Zeppelin -contracts. I think that's what it is, right? Lib, Open Zeppelin contracts, and Open Zeppelin contracts are upgradable. Okay, Open Zeppelin contracts /contracts, like this. And port this from at Open Zeppelin /contracts /proxy /ERC 1967, like this. So this is the proxy type we're using. Now we're going to say ERC 1967 proxy equals new ERC 1967 proxy. And if we command click onto this or control click or just look at this, this does have a constructor. We can pass in the logic and the data. So we basically say, hey, proxy, this address is going to be the implementation, the logic that you're going to use. And then any data you want to pass to the initializer, right? If we could look at upgrade to and call, we call upgrade to, and then if there's any initializers, call that afterwards, right? We're not going to have any initializer stuff, so we're not going to do that, but we're just going to say address box, because we just deployed this box, no data. This is where, like I said, this is where we'd put the initializer stuff we wanted, but then we're just going to say return address proxy. So cool. And let's just make sure stuff is working. Forge build, or at least we're going to make sure code is compiling and source file does not specify required compiler version. That's because we haven't implemented that. That's fine. Cool. This looks good. And we're going to write some tests to show you this actually working in a little bit. But cool. So we have a deploy box. Let's actually write an upgrade box script now, and then we'll write a test to show both of them. SPDX license identifier MIT pragma Solidity 0.8.18 contract upgrade box is script. Import script from forge std/script.sol. Script, cool. Function run external returns address. Oops. I'm going to have this external. Oops. I'm going to have this use the most recently deployed box. So to do that, we're going to actually install forge install chain excel org -foundry devops -no -commit. Like I said, there might be a better DevOps tool than this. You can find the recommended DevOps tool in the GitHub repo associated with this. Recommended tool is going to be Foundry DevOps. So great. So that's what we're going to use. I've worked with this one before. So we're going to say address most recently deployed equals DevOps tools.get most recently deployed. There's going to be deployment. And this is where we're going to get the ERC 1976 proxy. Let me toggle the word wrap here. Move this down. On block.chainid. Oh, let's import that as well. Imports from, and I got to go to the foundry.toml. Do a little bit from lib/foundry devops /src/devops tools.sol. Looks good. Get most recently, I spelled that wrong. Get most recent deployment. So we're going to get the most recently deployed proxy first, and you'll see why in a second. And first, we're going to actually deploy box v2. So we're going to import box v2 from /src/box v2.sol. .sol. So we're going to do a little vm.start broadcast. Oh, did we do that in box deploy box? Oh, we should do that here. Oh, back in the deploy box, we're going to do vm.start broadcast and then a stop broadcast. Like that. Okay. vm.start broadcast in the upgrade box. We're going to say box v2 new box equals new box v2 vm.stop broadcast. And then we're going to say address proxy equals upgrade box. And I'm modularizing this for our test cases, but we're going to say we're going to create a new function called upgrade box. Where we're going to pass in the proxy address, right? This is the proxy address, and then the address of our new box. And then we're going to say return proxy. So we're going to create this function upgrade box, which has our previous proxy and then the address of our new box for us to do. So we're going to say function upgrade box address proxy address address new box. This will be a public returns address. We do a little vm.start broadcast. So, okay, so we're going to call upgrade box. We have the proxy address and we want to call upgrade on this, right? Since this is just an address, we can't call upgrade on an address. We're going to need to call upgrade on using the ABI of box v1, right? So let's import that as well. Import box v1 from /src/box v1.sol. We're going to say box v1 proxy equals box v1 of the proxy address, like this. And what we're going to do is, now that we've given our proxy address box v1 ABI, we can now just call proxy.upgrade2. Since box v1 is UUPS upgradable, it means it has access to this function. Address new box, this, we're going to upgrade it. And we're just going to do vm.stop broadcast. Like this. We could also optionally wrap this in box v2, or we could, do a direct function call, whatever we want to do. Now we'll just return address proxy, and that's it, right? So what is this doing when we actually upgrade? Well, we deploy box 2 implementation. We are calling this upgrade box function, and what we're doing is, we're saying, hey, point the proxy to this new place. That's it. We're saying proxy contract now points to this new address. That's it. Don't believe me? All right, let's write a test. So, new file. And we're going to write some crappy tests here. We're just going to do the whole suite just to show you the power. Deploy and upgrade test.t.sol. You know the drill. SPDX, license, identifier, MIT, contract, deploy and upgrade test is test. Import test from forge std/test.sol. Pragma, Solidity 0.8.18. We got to do a whole bunch more imports. We're going to need to import deploy box from /script/deploybox.s.sol. Import upgrade box. You know, this is what we're actually testing from /script-upgradebox.s.sol. We're going to import box v1 from, thank you, GitHub Copilot, and box v2. We're probably going to need to import more stuff, but it's fine. Function setup. What do we want to set up here? Well, let's get a deploy box, public, deployer, upgrade box, public, upgrader. We'll do an address, public, owner equals, make ADDR, owner. And we're going to say deployer equals new deploy box, upgrader equals new upgrade box. Okay, cool. And we probably should write a whole bunch of tests, but for this video, I'm just going to write one. We'll say box v1, public box v1, and we'll say box v1 equals deployer.run. We're going to have to wrap box v1 like this. Cool. So we have our box v1. It gets deployed. Our deployer.run is a deploy box. Run returns the address of the proxy, not the address of the box v1, right? Returns the address of the proxy, not the box v1. So we can even call this, to make it more clear, box v1 public proxy, since this is actually a proxy address. Actually, let's do this even better. Address public proxy. And this is why before we were working with addresses, because it can be kind of confusing to know what it is. The proxy, right? The proxy, and it right now points to box v1. Cool. Hopefully that's more clear. So now we'll do a function, test upgrades, like this, and we'll just test the whole darn system. So we have the box. We have the proxy address pointing to box v1. Now in our upgrade box, in our run, we went ahead and did all this. But for now, let's just use this upgrade box functionality so I can show you a little bit more granularly what's actually happening, right? So test upgrade. Let's deploy our own box v2. We do it in run. We could 100% do it in run, but I want to do it myself. So I'm going to say box v2 equals box v2, or box 2 equals new box v2 vm.prank. I'll do that. Just box v2 box 2. Now I'm going to say address proxy equals upgrader.upgrade box proxy, which is just an address of box 2. So our upgrade box here, all it's doing is saying, okay, cool, get the proxy for box v1 and now point it to v2. So we're calling that in our test here. And now we could do unit 256 expected value equals 2. And we could say assert equal. Oh, actually, we shouldn't even set this. Let's not even set this, right? So this address is going to be the same. We're never resetting this address. We're being very clear about that. Boom, proxy deployed here. Boom, we're never changing the address. So it's always going to be this address. Now what we can do though is we can say assert equal expected value is box v2 on the proxy address dot version. If this works, this means that on the proxy address, which originally pointed to box v1, it's now pointing to box v2. We could also do box v2 proxy dot set value, or what do we call it? Box v2 set number. We'd say like 7 or something, right? Then we can say assert equal 7 box v2 proxy dot get number, like this. And we could even add another function, test proxy starts as box v1, right? Public, we could say vm.expect revert with calling this function, because set number doesn't exist on box v1. So if we try calling set number on the proxy, it should fail. So let's run these one at a time. Forge test-m. This should indeed revert. Great. And then let's test this, and this should indeed upgrade. Forge test-m, test upgrades. Oh, we failed. Let's get some granular detail here. -vv. Left is 7, right is 0. Set number, get number. Oops, we forgot to actually add set number in here. So let's do number equals underscore number. Whoops. Now let's run that test. And boom, it passes. We have successfully upgraded our box. This is very exciting. So to wrap this up, I know we went through this really quickly. I want you to ask a ton of questions about this process. Ton of questions about this. Ask them in the discussion. Ask them on Twitter. Ask them to your buddies. Whatever you want to do. We just learned about upgrades. Like I said, I highly recommend you do not default to this. And you do not let protocols that have upgradable smart contracts keep this centralization vector, because it is. If you have an upgradable smart contract, that means that a group could change the logic of that code at some point, or be coerced to change the logic, etc. But this is an incredibly powerful primitive to know about, especially delegate call. We're almost done. Push this up to GitHub, add this to your portfolio, take a break. Congratulations. I'm going to go ahead and deploy this to a testnet now, just to show you what it will look like on Etherscan. Feel free to just watch, sit back, relax. You've done a ton of amazing work to make my life easier. I'm going to borrow a make file and just kind of tweak it. Let's just delete all this stuff. Deploy. It's going to be deploy box, upgrade, port script, upgrade box, make, deploy, args, equal, -- network, Sepolia. All right, so I ran the deploy. We deployed 2 contracts. Let's grab this one first. Sepolia Etherscan. Let me show you what this looks like. Looks like this one didn't quite verify correctly. I could go ahead and manually verify it if I wanted, but let's look at the second one. Looks like neither one of these actually verified correctly, but that's fine. I can go to my broadcast, see which one's which. We can go to both these runs. Let's see the first one. Okay, we did create box. And so this is going to be the address of box v1. So I copy this, paste it in here. I could go ahead and verify this manually later, but I know that this is my box v1. We'll go back to broadcast, click this one, scroll down. This one doesn't have a contract name, but I know that this one is going to be my proxy address. So I go to your browser. Let's keep them both up, paste it in here. This one didn't get verified correctly either, but that's okay. So this one's our box. This one's our proxy. And this is the one that's more important, right? This proxy is pointing to this implementation. Okay. Now we're going to call our upgrade by just doing make deploy, make upgrade like this. Oh, and I need a toml. Since I'm using Foundry DevOps, I need FFI equals true. Remember, only do that if you are confident about what you're running. You do make upgrade. So this actually is a bit of a bug with this script that I just found out. I do need to update my run latest to ERC 1967 proxy. I either need to upgrade my script to look for null, or I need to upgrade Foundry to add this for the proxy name. So I'm just going to manually add this in. We're going to hit clear. We're going to rerun it. Looks like that is a bit of a bug. Sorry about that. But now that it knows that this is the ERC 1967 proxy, we're actually running this script now to upgrade the box. And the first thing that we're going to do is we're going to deploy our box v2, which for some reason is actually verifying. Looks like something was just wrong with the first time I did it, but all good. If I paste this in, we now have a box v2 being created, and it looks like it's trying to verify right now. Oh, and it looks like this one actually did verify. So if we refresh this one, so it looks like our box v2 is here. We place this in, it looks like this one did actually verify, which is great. Box v2. Now, if we go back to our proxy, we hit refresh, we can see we called an upgrade 2 on this contract. Now, whenever we call functions on this, it'll actually point to box v2, right? So we can even grab the contract address. We use a little cast send, paste this in here. We'll call get number like this, or actually, excuse me, cast call, and of course, dash RPC URL, Sepolia, RPC URL, like this. We'd see that it starts off as 0, that number starts off as 0. Then we can call, well, we can do send instead, set number, which takes a uint 256. We'll set the number to 77, RPC URL, dash private key. Remember, you're going to need to do source.env to do this. We'll send a transaction to actually update this, and we're calling the proxy, right? We're not calling this box v2 address. We're calling it right on the proxy. Then if I go up, and we do call again, we're now going to get 4D for the binary. And if we do cast -2 base, paste DEC for decimal, we convert this hex to decimal, and we see we get 77 back. So we have successfully deployed and worked with a proxy. This is so awesome. Take a break. We got 2 more. You're so close. You're almost done. We got 2 more. Scrolling all the way down. Foundry governance, another quick one. And then introduction to security. And then I'm going to send you on your way to make the future of finance, the future of smart contracts, a better place. You're so close. Take a break. Get ice cream. Post on Twitter. I will see you soon. All right, welcome back. We're almost there, everybody. Let's scroll on down to lesson 14. We are now on Foundry DAO/governance. And of course, all the code that we're going to be working with is in this GitHub repo. So if you want to follow along, feel free to go here. Now, there's a ton of conceptual stuff to go over before we get into this. But basically, we're going to learn everything about what a DAO is, what they're for, and how to use them. And as we're going along and as we're learning about DAOs, I want you to take some time to read these 2 articles. They're both from Vitalik, and they address a lot of the main concerns with DAOs. One of them are that DAOs are not corporations, where decentralization in an autonomous organization matters. And this article came out in response to a lot of people having really hard coordinating DAOs, because since they're decentralized autonomous organizations, and it can be difficult sometimes to coordinate with so many people and so many heads. So this article is really interesting, where DAOs work really well and sometimes where they don't. And this one is one of my favorite articles about plutocracy. Plutocracy is government by the wealthy. This is something that obviously sounds bad and something we want to avoid in this new system that we're creating. If we default to typical ERC20 based governance, we're going to run into a lot of issues outlined in this post. If that doesn't make sense to you right now, don't worry, it will. And we'll come back to this in a little bit. But first, let's learn about DAOs, what DAOs look like and how they actually work, especially as developers. So I made some videos about this in the past. Let's go ahead and watch those, and we'll come back. Now, before we learn how to code a DAO, we should learn what a DAO is. And again, I've already made a video that I put a lot of work into. So we're going to watch what a DAO is from a high level first. Then we're going to learn how to code a DAO. Now, DAOs, or decentralized autonomous organizations, is a bit of an overloaded term, but it typically describes any group that is governed by a transparent set of rules found on a blockchain or smart contract. And I say overloaded because some people say Bitcoin is DAO because the miners could choose whether or not to upgrade their software. Other people think that DAOs must use transparent smart contracts which have the rules ingrained right into them. And then other people think DAO is just a buzzword, so they just slap the name really onto any organization so that they can get some clout. And this makes for sad Patrick. And this is not to be confused with the DAO, which was an implementation of a DAO back in 2016, which set the record for the largest hack at that time.
So there's a lot of different ways to think about it, and the DAO term is used in a lot of different ways. But in essence, imagine if all of the users of Google were given voting power into what Google should do next. And the rules of the voting was immutable, transparent, and decentralized. This solves an age-old problem of trust, centrality, and transparency, and giving the power to the users of different protocols and applications instead of everything happening behind closed doors. And this voting piece is a cornerstone of how these operate. This decentralized governance, if you will. And it can be summarized by company or organization operated exclusively through code. And to really understand all this, we're going to look under the hood of the protocol that's setting the precedent for all other DAOs in Compound. Then, once we look at Compound, we'll understand what goes into building one of these and all the trade-offs, all the different architectural choices mean for your group. And then in my next video, I'm going to have a full code along tutorial for developers looking to build one of these themselves. But be absolutely sure to watch the rest of this video because it's going to give you all the architectural fundamentals so you can make intelligent decisions when you get to that section. And be sure that you and your DAO friends smash the like and subscribe button so we can keep giving you the best engineer first content on the planet when it comes to smart contracts. Let's get into it.
So here we have the Compound protocol. It's a borrowing and lending application that allows users to borrow and lend their assets. And everything about this application is built in smart contracts. Now, oftentimes they're going to want to do a lot of new things. Maybe they want to add a new token to allow borrowing and lending. Maybe they're going to want to change some of the APY parameters. Maybe they're going to want to block certain coins. There's a lot of different things that they might want to do. So that's where we're going to go ahead to governance. This is where you can find a user interface for a list of all the proposals and all the different ballots that came to be. So here's a list of some of the governance proposals that this protocol has actually been making to improve. And let's look at one of these proposals that's currently actually in process. So if we click on the proposal, we can actually see everything about this proposal, who voted for, who voted against, and the proposal history here. Now, the first thing to one of these proposals is somebody has to actually create the proposal in a proposed transaction. And we can actually see that proposed transaction right here. If we click on this and we scroll down, we can actually see the exact parameters they used to make this proposal. Let's go ahead and decode the input data, and we can see this is exactly what this proposal looks like. The way that they're typically divided is they have a list of addresses and a list of functions to call on those addresses, and then obviously the parameters to pass those addresses. So this proposal is saying, hey, I would like to call support market on this address, set reserve factor on this address. Here are the parameters we're going to pass. They're obviously encoded with bytes. And then here's the description string of what this is doing and why we're actually doing this. The reason we have to do this proposal governance process is that these contracts likely have access controls where only the owner of these contracts can actually call these two functions. And the owner of these two contracts is likely going to be this governance DAO. And values to 0 just means that we're not going to send any ETH along with these transactions. Once a proposal has been created, after a short delay, it becomes active. And this is when people can actually start voting on them. This delay between a proposal and an active vote can be changed or modified depending on your DAO. Then people have some time to start voting on them. And if it passes, which this one overwhelmingly did, it reaches succeeded. If we click on this transaction again, and we go to the Compound governance contract, and we scroll down to contract, write as proxy, we can actually see the exact function that the people called to vote, namely cast by vote, cast vote by signature, and cast vote with reason. We'll talk a little bit about the exact differences between these in our next video, but these are the functions that they're actually calling. And if you go to the Compound app and we go over to vote, this is a user interface you can actually vote through to make it easier if you're not as tech savvy. So you can vote right through this app.compound.finance, or you can just send the transaction yourself. Once all those votes happen, it reaches this queued stage. Now, what does queued mean? Well, before a proposal actually becomes active, there's a minimum delay between a proposal passing and a proposal being executed. So somebody has to call this queued function, and it only can be called if a vote passes, and it says, okay, that proposal ID has been queued, and we're going to execute it soon. Now, if we go to a different proposal, like this one, for example, we can see it has been executed. We can see somebody called this executed function, and they executed proposal 82. So this is going to be a full example of the life cycle of a proposal going through this process. Now, there are a couple that even failed. A whole bunch of people voted against this. And if you scroll down, you can see it was created, it was active, and the majority of people voted against. So that's where it stops. Now, oftentimes, just putting one of these proposals through isn't enough to really garner some votes for it. You generally want a forum or some type of discussion place to talk about these proposals and why you like them or don't like them. Oftentimes, a discourse is one of the main places that people are going to argue for why something is good or why something is bad, so people can vote on these changes. And again, Snapshot might be one of these tools that you use to figure out if your community even wants something before it even goes to vote. You could join one of these and with your tokens actually vote on things without them being executed just to get the sentiment. Or, like I said before, you could build your protocol in a way that Snapshot actually helps you with the voting process. All right, now you've seen the protocol that has been influencing all the other DAOs on how to vote. Now you know. Now that we know what a DAO looks like, let's talk about the architecture and tools that go into building one of these, and additionally, the trade-offs that they have. And the first thing to talk about here is going to be the voting mechanism. Now, voting in decentralized governance is critical to these DAOs because sometimes they do need to update and change to keep with the times. Not all protocols need to have a DAO, but those that do need to have a DAO need a way for participants to engage. This is one of the most important questions to ask and to tell your communities. How do I participate? How do I engage in this DAO? How do I help make decisions? And you'll find this is a bit of a tricky problem to solve. Now, an easy approach to this problem is going to be using an ERC20 or an NFT token as voting power, similar to what we saw with Compound. Use the comp token to vote for different proposals. Seems simple enough, right? Boom, problem solved, hooray! Now, this actually might be the right approach for certain DAOs, but it also runs the risk of actually being less fair. Because when you tokenize the voting power, you're essentially auctioning off this voting power to whoever's got the deepest pockets. Whoever has the most money gets to pick the changes. So if it's only the rich people who get to vote, then it's highly likely that all the changes in the protocol are going to benefit the rich, which doesn't really seem like that great of an improvement over our current world. NFTs are interesting because they have this non-fungible component, but yet even they still run into this issue. Additionally, if you buy a whole bunch of votes, you make a bad decision and then sell all your votes, you as an individual don't really get punished. You just punish the group as a whole. But you being malicious, you can get away with pretty scot-free. Now again, this voting mechanism is going to be correct for some groups, but for other groups, maybe not. It really just depends on what your DAO and community setup is going to look like. Now, the next one we're going to talk about is skin in the game. Now, Vitalik has actually written a lot about this, and I highly recommend you read his article, link in the description to see that. The skin in the game method means that whenever you make a decision, your vote is recorded. And if that decision leads to a bad outcome, your tokens are axed. So you get punished for making evil or bad decisions for your DAO and your protocol. I like this mentality because even if you buy a ton of tokens and decide to be evil with it, you can be held accountable for your bad decisions. Now, the hardest part about this though is going to be how do we decide as a community what is a bad outcome? How do we actually punish these people? And that's easy because the answer is, I'm not sure. Now, the third method of this voting mechanism is probably one of the most interesting ones, but also the hardest ones to implement. And this is proof of personhood or participation. Imagine that all users of the Compound protocol were given a single vote simply because they used the protocol. And even if they had 1,000 wallets that use the protocol, one human being means one vote. This would be amazing and a far more fair implementation where votes couldn't actually just be bought. The issue, however, comes in something known as Sybil resistance. How can we be sure that it's one vote equals one participant and not one participant pretending to be thousands of different people so they get more votes? This method hasn't really been solved yet, but I'm willing to bet some very clever engineer will do some amazing Chainlink integration because proof of personhood is basically just off-chain data that can be delivered on-chain, and that's exactly where Chainlink shines. Now, as you can see, all of these methods and even more that you probably think of aren't that far-fetched. And we actually see these exact same methods happening in the real world. Proof of personhood or proof of participation might just be the exact same as kind of the regular government voting that we see every day. In the United States, at least, one person gets to vote for one president. You can't go around making a whole bunch of fake people and voting for president. But in companies, the ERC20 voting standard kind of applies. The more shares of a company you have, maybe the more
voting power you have in that company. So we can draw parallels between the real world and how voting and governance is going to work in our smart contracts. And in fact, you should draw parallels and look for inspiration from the Web 2 space. Now, when it comes to implementation of the voting, I put them into two categories: on-chain voting and off-chain voting. On-chain voting is exactly what we saw with Compound. There's a smart contract, on-chain, you're a voter, you call some function called vote with your MetaMask, your Ledger, or whatever, send a transaction, and boom, you voted. Congrats, you can wear your little sticker now. You call that function and you send a transaction. You send a transaction. What do transactions use that are kind of annoying and kind of costly? Oh, that's right, gas. Imagine you have 10,000 people in your community and it costs $100 to vote per person. You're now costing your community $1 million anytime you want to change anything. This is obviously insane and not very sustainable for your community. The pro here is that the architecture is really easy. Everything's going to be transparent. Everything's going to be on chain, and that's really good. But yes, the con is that you're going to break the bank account for a lot of people, potentially. Now, there are a lot of variations of this to help solve some of these problems, especially the gas problem. One of the ones that I'm incredibly excited for is this one called Governor C, where they use some random sampling to do some quadratic voting to help reduce costs while increasing Sybil resistance. If you want to learn more about that one too, be sure to read about it in the description. So on-chain voting is the simplest one here, but let's talk about off-chain voting.
How could you possibly vote off-chain in a decentralized context?
Relax. You can vote off-chain and still have it be 100% decentralized. You can actually sign a transaction and sign a vote without actually sending to a blockchain, and therefore without actually spending any gas. Instead, what you can do is send that signed transaction to a decentralized database like IPFS, count up all the votes in IPFS, and then when time comes, deliver the result of that data through something like an oracle like Chainlink to the blockchain, all in a single transaction. Alternatively, what you could do is you could replay all these signed transactions in a single transaction to save gas. This can reduce the voting cost by up to 99%. Right now, this is an implementation, and one of the most popular ways to do this is through Snapshot. And I'm just dying for someone to make a Chainlink integration because it's going to be so much safer, more secure, and better, and blah, blah, blah. Dying for it. This is your call to action. Go build this thing. This off-chain voting mechanism obviously saves a ton of gas to the community and can be a more efficient way to store these transactions anyways. However, it needs to be implemented very carefully. If you run your entire DAO through a centralized oracle, you are essentially reintroducing a centralized intermediary and ruining the decentrality of your application. So don't do that. And if you've made it to this point of the video, give yourself a little pat on the back. You're doing fantastic. Learning is fantastic. Like I said, I have a video coming out after this one that's going to show you end-to-end how to build one of these from scratch. Let's learn about some of the tools that you can use help get you up to speed quicker. Now, there are a number of no-code solutions that can go into building one of these DAOs. DAOstack, Aragon. Just kidding, this is Aragon. Colony and DAO House are all alternatives that can actually help you with the ops side of running a DAO and building a DAO. However, if you want more granular control and you don't want to have to pay any of the fees associated with these protocols, you might want to do it from scratch. Now let's talk about some of the more codey solutions that you can use. Snapshot is one of the most popular tools out there for both getting the sentiment of a DAO and actually performing that execution. Users can vote through this protocol with their actual tokens. Those transactions get stored in IPFS, but none of it actually gets executed unless the DAO chooses to. So this can be a great way to get a feel for what your DAO wants to do. And optionally, you can send the transactions and execute the votes as well. I highly recommend checking out Zodiac, which is a suite of DAO-based tools for you to implement into your DAOs as well. Tally is another one of these UIs that allow people to see and actually vote and interact with these smart contracts through a user interface. For those of you who don't know about Gnosis Safe, you absolutely should. Gnosis Safe is a multi-sig wallet. And the reason that I put this on the list, even though it adds kind of this centrality component, is that most DAOs in the beginning are probably going to start with some type of centrality. It's much easier to be fast when you don't have thousands of people to wait for a vote. And in the beginning, any protocol is going to be centralized to some degree anyways. Using a multi-sig where voting happens through only a few key members can be good in the beginning for your DAOs, and often emergencies as well. But just keep in mind, when you add one of these, you are adding this level of centrality. And then, of course, Open Zeppelin contracts. We love Open Zeppelin contracts. These are the contracts that we're going to be basing our DAO code along on. All right, so that's all the tools. That's the architecture. One more thing before I let you go. Legality. The future of DAOs is interesting for all these reasons we just talked about, but especially on a legal front. Does it make sense for a DAO to live by the same regulation as another company? How could you even force a DAO to do something? You'd have to force them to all vote a certain way if the government tells you to. It's a little gray. It's hard to nail down who to even keep accountable for these DAOs. In the United States, at least, you can actually form your own DAO and have it legally recognized in the state of Wyoming. This is something I want to do, so we'll just have to see what happens there. Woo! At this point, you have been injected with all the DAO knowledge you need to succeed and thrive with this new amazing technology and these new amazing concepts. And it's time to build, baby!
Now, we are still going to build a DAO from scratch, but we do have our special guest, Juliet, from the Aragon team to go over a no-code solution that you can use as an alternative.
Hello, everyone. My name is Juliet Chevalier. I'm the developer advocate for Aragon, and today we'll be building a DAO without using a single line of code. Let's go. So to do that, I'll be using Aragon as my DAO framework. And to give you a bit of a better overview as to how Aragon's architecture is set up, DAOs are essentially composed of a smart contract, which is the one that contains all of the assets that the organization manages. So it acts as a treasury. And then all of the other functionality for DAOs is really enabled through plugins. And we'll see how this is represented itself throughout the process that we'll build. So we go into app.aragon.org, we go into creating a DAO. First, we'll see the process that we'll be taking in order to do that, and then we can get right into it. So firstly, we need to choose the blockchain which our DAO will be deployed in. I'll choose Goerli for the sake of simplicity and playing with testnet. Then we get to describe our DAO, so we can have a developer DAO, which can be something like this. We can set up our ENS, we can set up our logo, a description, a DAO for developers, and we can add in additional links as well that represent the organization. Then we'll go into defining the membership. This is what will define who is able to participate in the governance of these assets. And currently, our app supports two different types of membership definitions and governance mechanisms. One of them is token holders, which enables holders of specific tokens to vote in the organization. And then we have multi-sig members, which establishes a specific quorum that needs to be met in order for a proposal to go through. Now, to give you some context, both of these on the back are plugins, which essentially extend the functionality of what DAOs can do through enable them this specific decision-making process in order to manage the assets of the organization. However, keep in mind this can be anything, and plugins can also work to move funds. They can be treasury management mechanisms. They can be different types of coordination styles. And so really the possibilities are endless when we speak about customizing these types of on-chain organizations. Then we're going to create a token. This can be something like developer token. We can call it something like DVP. I can set up, say, 1,000 tokens for myself, or add any other address that I want to transfer some funds to. Then I establish what is the minimum amount of tokens that someone needs in order to create a proposal. I'll say 10. I could also just say, like, allow anyone out there to vote and create proposals, at which point there is a risk of proposal spam. So keeping that in mind, I'll just say that we need, say, 10 tokens in order to create a proposal. Then we'll go through our governance settings. So what is the minimum support threshold needed, the minimum participation needed for a proposal to be valid, how much time is the minimum duration the proposal needs to be out there in order for it to be counting the votes. And then we can say that we don't want early execution, which means that we wait for the entire time of the duration of the proposal, as well as not enable people to change their vote after they've voted. I can also vote yes to that. And then the last step is simply revising those parameters that I've set. So out of everything that we've defined, only the blockchain selection is the one thing that we cannot change later on, since that's the blockchain through which we're deploying our DAO. But really everything else, we can change it later on with a proposal vote. And so the idea here is to really enable these types of immutable organizations to mutate and evolve with time. So I'll sign in my proposal, I go back into my deployment, and so at this stage, what's happening on the back is that Aragon is deploying this DAO construct instance with the specific plugins defined, installed, as we determined through the DAO creation process. So once that's done, we can come into the dashboard of our DAO. We'll be able to see who is a member of our organization, how many tokens are held. I can create proposals, I can make deposits. And so this is where we'll be managing the organization. Keep in mind that this is a pretty default template that Aragon has set up as our initial drafts. We have a lot of iterations coming in terms of the type of plugins you'll be able to use, the different types of decision-making strategies you'll be able to implement. And so the customizability really is endless. Thank you very much.
All right, welcome back. You now know a ton about DAOs and how they work. And we are going to go over one of these plutocracy DAOs, right? One of these ERC20 based DAOs and how to build one yourself from scratch. However, I want to challenge you to not default to this. A lot of protocols default to, okay, I'm just going to launch a governance token. We're going to be good to go. And then a couple years down the line, they realize that that was a horrible decision and they have a hard time scaling their model. They run into issues where they can't separate speculation on the token from the utility of the token. And there's a ton of issues with that model. So anybody who's watching this, if I catch you launching a DAO in the future, and you do not have a foolproof white paper as to why you need a governance token, I will be very disappointed in you. I know that doesn't really matter to you, but I will be very disappointed in you and you will make me sad. So please don't make me sad. But we are going to learn this methodology and how to do it. So let's jump in because guess what? We only have 2 lessons left and then you're ready to go on your way. All right. You know where to begin. MKDIR, Foundry, DAO, F23, code, Foundry, DAO, F23, or file open. Let's pull up our VS Code. At this time, you should be pros at this port. Forge init. I don't want these 3 files. Boom, 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 goodbye. Boom. So let's do a little README and let's talk about what we're going to do. So 1, we're going to have a contract controlled by a DAO, 100% controlled by a DAO. Every transaction that the DAO wants to send has to be voted on, and we will use ERC20 tokens for voting, which, like I said, this is kind of the default model that the industry is currently using, but I'm telling you, it's not a great model. Please research better ones and make Web3 better. But all right, and this is the model used by pretty much every DAO at the moment. Compound, Uniswap, Aave, etc. So I'm showing you the most popular model, but yes, I'm telling you, please don't default to this. Please don't always use this. But let's start with this first one. We're going to have a contract controlled by the DAO. So let's create a minimal contract that we can vote on stuff for. And we're going to do something pretty similar to what we've already done. We're going to do src, new file. We're going to make a box.sol. Real similar to what we did before, right? SPDX. Places identifier MIT, Pragma, Solidity, 0.8.18, little caret, contract, box. Let's close this like this. Like we said, we're going to make this ownable. It's going to be controlled by the DAO. So we're going to do a little Open Zeppelin work. Forge, install, Open Zeppelin / Open Zeppelin contracts -- no - commit. And since we're doing this, we're going to need to open up our foundry.toml, paste this in here. I copied this from a previous project. Open Zeppelin / contracts, lib, Open Zeppelin, blah, blah, blah. Now, since we have that, we can do import ownable from at Open Zeppelin / contracts / access / ownable.sol. And our box is going to be ownable and the DAO is going to own it. Tracks. All right, cool. Going to be real minimal contract, UN256, private number. This obviously should be like S_number, right? Event, number changed. Looks like that. Function store, UN256, new value or new number. Public. This will be our only owner function, which this store function will be only ownable, will be only callable by our DAO. We'll say number equals new number. We'll even emit number changed with the new number. maybe this is s underscore number, and then we'll do a function read number or get number, public or external view returns UN256, return s number, and that's it. That's the whole contract. Boom, that's it. This kind of looks like box, kind of looks like symbol storage. It's kind of an amalgamation of both, but this is it. Cool. We'll make sure it actually compiles with forge build. Make sure it compiles. Looks like it's compiling. Okay, cool. Awesome. So we have our box. What's next? Well, every transaction that the DAO wants to send has to be voted on. We will use ERC20 tokens for voting. So let's create our voting token here. New file, govtoken.sol, and this is going to be our voting token. Now we could implement this from scratch, but again, what we can do for this is actually just come to the contracts wizard of OpenZeppelin, go to ERC20 and select votes, and literally just copy this to clipboard and paste it in, or copy this ourselves and paste it in here. And this is going to be our voting token. That's it. So let me talk to you about what we just copy pasted. And we're going to update this to be named imports, because named imports are awesome. For this draft ERC20 permit, we're just going to import this ERC20 permit and then ERC20 votes. So I'm just going to talk you through what this is actually doing. So it's a regular ERC20 token, exactly as we've seen, but it has these two kind of extensions. Let me toggle the word wrap. And we have the OpenZeppelin contracts installed. Okay, cool. So I'm going to command click into them. Again, you can open up the file viewer and type the actual name of the contract if you want. ERC20 permit. What does this actually do? This allows approvals to be made via signatures. Basically, you can sign a transaction without sending it and let somebody else send the transaction. That's it. It's based off of this EIP. We don't really need to understand this too much, but if you're interested, I would definitely recommend looking into it. The more important one is this ERC20 votes contract. And like I said, it's based off of this compound voting and delegating. It does a lot of important things here. Number one, it keeps a history of each account's voting power. It keeps snapshots of them. Now, this is important because when you start a vote, you want to use a historical snapshot. You don't want to use the current balance of everyone's tokens at the moment. Somebody could do something called a flash loan, which is something we didn't talk about, but they basically can use this DeFi thing to get a ton of tokens for a very, very short period of time and crash the vote. So we use a historical value, and the way to get that historical value is to keep checkpoints of people's values. We can also use a delegate function on our tokens. Sometimes we trust a person more than we trust our understanding of a topic. So we can actually hold on to our tokens still. The tokens are still ours, but we can delegate the voting rights of our token to somebody else. And these are some of the two main features that this token has. If we scroll down, we can see we have this checkpoints function, which gets checkpoints, and there's this checkpoints mapping address to checkpoint. We can see the checkpoint object says from block and then votes. And if we scroll down, there's this Afton token transfer function, which anytime you transfer a token, this gets called. It ends up calling this move voting power, which does a whole bunch of stuff in here. But the main things are, it calls this write checkpoint function. So anytime you move tokens by delegating tokens or transferring your tokens, you write a new checkpoint, right? So you say, hey, at this block, this was people's voting power. And you don't do it for every single block, right? You don't calculate someone's checkpoint in every single block. You only calculate the updates in the checkpoints. So if we scroll up to the top, for example, it says from block. This would be like, let's say you bought a token at block 5 and then you sold it at block 25. This would just have two checkpoints, block 5 and block 25. That's it. It adds some gas for every single transfer you make, but it allows us to do these sophisticated voting methodologies. So, and that's really it. Other than that, it's a basic ERC20 token, just has these checkpoints, has these additional delegate functions as well. And that's really it. And cool, like that's it. Our governance token is done. That's all you need to do. What else? Well, guess what? The OpenZeppelin wizard can help us with even more. Because what do we need next? Well, we need a DAO, right? We need a system. We need a contract to actually manage these votes, right? And guess what? The wizard has one called governor. We can go through this and update settings. So we can update the name if we want. I'm going to leave it as my governor. A voting delay, which is anytime somebody proposes something, it says, okay, we're going to wait at least one block for the voting to start. Maybe you do something like 100 blocks. It depends on your chain. The voting period for how long the voting will actually last. A proposal threshold, where it's the minimum number of votes an account must have to create a proposal. Most of the time, this is kept to 0. A quorum percentage of tokens that need to vote in order for something to pass. If there's 100 tokens in circulation, at least 4 tokens need to vote for it to pass. Make these settings updatable or not. This is to make the contracts fully compatible with Bravo, which is the compound implementation. The type of votes, you can have ERC20 votes, you can have ERC721 votes, which is an NFT or comp-like. A time lock controller. Anytime a vote passes, give users some amount of time to leave the DAO before it's implemented. And then upgradability. We probably want to avoid this as much as we can because, like I said before, security. And with that, I'm just going to leave all the settings to be default. We can literally copy this into our contract and not really have to do anything. So new file, my governor.sol, paste this in. And let's talk about what is going on in this contract. What are these different functions? So first off, let's update this to named imports. And we also need to import iVotes. This is going to come from governor votes. We're going to need to import this time lock controller, which is going to come from this governor time lock. And then we're going to have to import iGovernor, which is going to come from governor. And that's it. So just update these to named imports and we're good to go. So let's walk through what this is doing. So my governor is governor settings, governor counting, blah, 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 all this stuff. I'm going to give you the high level overview of what all of these does. This governor contract, if we command click into it or control click into it, is the core of the governance system. This governor contract, we control click into it. It brings us to governor votes, but let's go to the governor contract. This is kind of the main contract here. And how it works is it keeps this mapping basically of proposals, right? Each one of these proposals have a vote start, a vote ended, and then an executed or canceled. And that's really it. Every single time somebody submits a proposal, this mapping gets updated. And if we scroll down, we have this state function. This is the function that tells us if a proposal has passed based off of this mapping of proposals. If it's executed, if it's canceled, what's the deadline, has a quorum been reached, etc. This is what most user interfaces are going to read to see if a vote has passed or not. We keep scrolling down, we can see a proposal snapshot, which is basically getting the deadline, when the proposal is due. We can see some stuff like a proposal threshold, and then a whole bunch of unimplemented functions like quorum reached, vote success, get votes, etc. And this is because this governor function is this abstract contract meant to be extended on and implemented with. Governor votes is one of these extensions where it says, okay, ERC20 token voting. That's the way we're going to do votes. And this has a function like get votes, which reads the token voting weight from the token's built-in snapshot mechanism to get how often somebody can vote and that type of thing. Now in our governor, one of the main functions that we has is going to be propose. And these are going to be the variables it takes in. Targets is just going to be like a list of different contracts to make a transaction to. Values is going to be a list of values to send with each target. Call data, now that we know all about call data, is going to be the bytes data that we're going to send with each transaction. And then just a description, right? So for example, this might be like 0x0 blah, 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 some address here. And if it's just 1, it would just be like, 1 address here. If it's 2, it might be like this, etc. Values might be like, something like 0, meaning the transaction we send to this address, we're just going to pass 0 value. If there's 2 transactions with 2 addresses, like 0x, blah, 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 something or other, we could have 2 values, right? Call datas are going to be the call data for sending to here. And now that we know about function selectors, function signatures, and etc., we know that with this, this call datas section allows us to call any function and really send any data to this target that we want. So it makes it completely modular. And then some description, right? And this is really just for the internal state of the governor. It might be something like proposal to send money to Dawn, right? And so if this was like 123, this is Dawn's address. Cool. We've just made a proposal to send money to Dawn, right? If this was, like the link token contract, for example, we could have this be 0. We could find the function selector for transfer, and we could be like transfer function selector and encode, and then encode all the data for transferring some link. We could then say proposal to send link to Chris or whatever we want to do here, right? So this is how we can propose any transaction for our DAO to do and send proposals. So really, really important function here. And if we go through it, we can see it hashes the proposal. It does a whole bunch of checks in here. It adds our proposals to that proposals mapping. It gets a deadline, picks a snapshot for votes and everything, emits a log, and importantly, it returns a proposal ID. The proposal ID is a hash of all the inputs so that this proposal ID will be unique. Then we have another important function called execute. And all of the inputs you can see are the same as the inputs up here, right? The only difference is it's saying a bytes 32 description hash. This is just going to be the encrypted description from up here. And it's this function that gets called, and it's this function, this execute function that gets called once a proposal has passed to actually send that proposal, right? So here it first reverse engineers and gets the proposal ID from all those inputs, which should be the same as what was proposed, and then says, okay, let's get the status of that proposal state based off of how the votes go. And if it's good to go, then go ahead and execute it, right? So we do some execute stuff here. The execute internal function actually sends it with some familiar stuff here, right? We're doing targets.call, values, call datas, etc. This is this low level functionality here. Got some before execute stuff, some after execute stuff. We don't really need to worry too much about that. We can vote to cancel transactions. We can get votes. And then finally, another incredibly important function is going to be cast vote. And there's some derivatives of this, like cast vote with reason and params, cast vote by sig, a whole bunch of different ways to cast vote. But the main thing this cast vote thing does is it calls this internal cast vote function, which calls this internal cast vote function. And this is the actual function it calls. So it gets the proposal based off the proposal ID. It gets the weight of your vote based off of the snapshot of the tokens that you hold. Calls this internal count vote function, which basically just updates some internal state variables to add your votes to them, and then emits an event. That's it, right? And it updates your vote based off of whatever your weight is, which in the system that we're using, the more tokens you have, the more your vote counts. And those are the main functions here. So hopefully that made sense. I know I kind of went through that a little bit quickly, but that's kind of the basics of the governor. Now, governor is the main contract. Governor settings is just an extension to add stuff like voting delay, voting period, voting threshold, etc. Governor counting simple is also an extension, which is just an extension for a very simple counting mechanism. This extension allows our votes to be against, for, and abstain. And so we have this proposal vote. For each proposal, they get this struct, and this is where those votes get counted. We have against votes, for votes, abstain votes, and then a mapping of who has actually voted. Governor votes just implements this get votes contract. And governor votes quorum fraction. This is just an extension for token weight extraction. And then we have this important time lock controller function. Every single DAO should 100% always have this governor time lock control. Using this model means the proposal will be operated by the time lock controller and not the governor. Thus, the assets and permissions must be attached to the time lock controller. So we're actually going to deploy a contract called time lock that's going to own the governor. Anytime our governor contract votes on something and says, okay, this vote has passed, let's execute it, the time lock controller will say, okay, cool, but you have to wait X days or something. You can't execute without some delay. And it's really important to have this because if a DAO votes on something that a lot of people in the DAO hate, it gives them time to get out of the DAO before they get steamrolled, if you will. So really important to have this. And that's pretty much it. So we have some voting delay, voting period, quorum, state, propose. We have all these, which are just calling super, right? That's pretty much it. And that's all we really need for our governor contract, right? We have this constructor, which takes the token that we vote on as an input parameter and the time lock controller that's going to block us from executing proposals right away. The time lock controller contract is going to own our governor controller contract. And that's actually the last contract we need to create, a timelock.sol. So this is the only one we have to build ourselves, but we actually barely have to build it ourselves. SPX license identifier, pragma solidity, 0.8.18, caret, contract, time lock. And we barely have to implement this because OpenZeppelin already has one of these. So we just say our time lock is time lock controller. And then we can just import it, import at OpenZeppelin /contracts/governance/time lock controller.sol. Let's import it like this from, did I spell that right? Time lock controller. Okay, that's more right. Governance, contracts, OpenZeppelin, time lock controller. Okay, cool. That looks good. Now we'll just do a constructor and we'll pass some parameters in here. We'll say uint 256 min delay, which we'll put a little comma here. This is going to be the min delay is how long you have to wait before executing. We're going to have to pass, and we can find all of these in the constructor of this. Min delay, proposers, executors, and admin. Right? This is the constructor of the time lock controller. So we're going to need to have this be the constructor of ours as well. Min delay, we're going to need proposers is the list of addresses that can propose. So we need an initial list of proposers. We're going to update this so that it can be anybody. And then executors is the list of addresses that can execute. We're going to update this as well so that anytime a vote passes, anybody can execute it. So min delay, address array memory, proposers, address array memory, executors. Boom. And since this time lock controller parent class has a constructor, I'm going to toggle the word wrap. We got to put those in here, and it's just exactly the constructor parameters we created: min delay, proposers, executors, and then we also have to give it an admin, which we're just going to say is message.sender for now. And we need to give it an admin at first so that we can eventually move the time lock controller's admin so that only the DAO can do anything with the time lock controller. And you'll see us do that in a minute. But those are all the contracts that we need. That's it. We've written the contracts. We're done. Like I said, I'm going to do this kind of quickly. I do recommend that after this, you go back and you really try to understand what's going on here, because I know I'm kind of doing this quickly. But now we're going to write a test to show it actually work. And that's it. I'm not going to write a deploy script here. If you want to go back and you want to write a deploy script, that's great. But I'm just going to write a test to show you basically end to end exactly the process that happens in one of these DAOs. So let's go ahead. Let's write the test. My governor test.t.sol. And the other reason that I'm going a little bit quicker here is because at this point, you understand a lot of this, right? And you know and should know how to go back and flesh this repo out, right? With scripts, with tests, unit tests, fuzz tests, etc. And you know how to make this project badass. And I just want to give you the new stuff, right? Teach you the new stuff for here. Teach you about the DAO stuff. So let's write some tests just so that we can really see this process work end to end. And we're just going to have one giant test just to show the whole process. So you know the drill. Pragma Solidity here. Contract my governor test is test. You already know we're going to import test from Forge std/test.sol. And we're going to need a function set up. It's going to be public, of course. And we're going to need a whole bunch of stuff in here. Function setup. Oops. What are we going to need? Well, we're probably going to need at least these 4 contracts. So let's go ahead and import them. Import mygovernor from /src/mygovernor.sol. Import box from /src/box.sol. Import time lock from here. GitHub Copilot taking over a little bit. Import gov token. Okay, it failed. It almost took over here from /src/gov token.sol. Oh, is that not what it's called? Sorry. Let's change this thing to gov token. Like this. That's good. Okay. So now let's actually deploy some of these. So our gov token, we'll say, actually, let's create each one of these. My governor, box, time lock, gov token. Cool. First thing that we're going to need is our gov token equals new gov token. And I know this doesn't take any input parameters, but we should give our gov token, we should actually mint some of these. This gov token doesn't have a mint function. So I'm just going to create a mint function, but in your system, maybe you just have the constructor mint to the message.sender. I'm just going to go ahead and add this function mint address to UN256 amount. We'll make this public. This probably isn't what you want your token to have. You probably don't want anyone to be able to mint any tokens, but this is what I'm going to do. Mint to amount. That's it. There's an internal function called mint that we're going to call. So I'm just going to say, I'm going to mint to some user. I'm going to say address public user equals make address. This is going to be our user here. Do this capitals user like this. We're going to say gov token dot mint user, and we'll do UN256 public constant. Initial supply equals 100 ether. So we're going to mint ourselves 100 ether. Boom. All right, cool. Now, something that you'll often forget is that just because you minted tokens doesn't mean you have any voting power. So we want to run gov token dot delegate, that delegate function, and we're just going to delegate to ourselves. So we're saying, hey, we now have 100 tokens. We're going to delegate those 100 tokens voting power to ourselves. You could delegate it to somebody else if you wanted to, but for our test, we're going to do it for us. And we need to actually do vm.startPrank user, because only the user can delegate tokens to themselves. And we might as well stay as the user for these next ones, just that we can start off as owners of the contracts we're about to do. So now that we have our governance token, next what we want to deploy is our time lock. Because in order to deploy our governor, we're going to need both the gov token and the time lock. So we have the gov token. Let's actually create the time lock now. So we're going to say time lock equals new time lock. And what does this take? Min delay, proposers, executors. So let's create those. I'm going to scroll up. We're going to make UN256 public constant min delay equals 3600, which is going to be 1 hour. This is the delay after a vote passes, right? So this is the time lock's min delay. Nobody can actually execute a past proposal until an hour goes by. Boom, we'll do min delay. What else do we need? We need the proposers for stuff. And we'll just make this at the top, address array proposers, address array executors, and we'll just leave it blank because we don't care. Proposers, executors. And this is actually how, with the time lock controller, you say anyone can propose and anybody can execute. You just leave these arrays blank. Cool, looks good. Okay. Now that we have that, we finally can deploy our governor contract because we have these two. So we'll say what do we call it? Do we just call it governor? Yep. Governor equals new my governor gov token time lock, like that. Now we have to grant some roles. So the time lock actually starts with some default roles, and we need to grant the governor a whole bunch of roles, and then we need to remove ourselves as the admin of the time lock, right? We don't want a single centralized entity to have power over it. So first we got to get some of the roles. So we're gonna say bytes32 proposer role. And the way that the time lock has roles is that it hashes the names of stuff. So we'll say proposer role equals time lock proposer role. So there's this function on the time lock called proposer role. And we're going to allow this proposer role to be just the governor. So only the governor can propose stuff to the time lock. We're going to say bytes32 executor role is going to be time lock.executor role. We're going to give this to anybody by setting it to the 0 address, and then bytes32 admin role. Right now that's us. Time lock nope, it's going to be time lock admin role. And so, like I said, these are just kind of the these are hashes in the time lock, and we just need to update these. So we're going to say time lock dot. It has a grant role function. We're going to grant this proposer role to the governor. So only the governor can actually propose stuff to the time lock. We're going to say time lock dot grant role executor role to address 0, which means anybody can execute a past proposal. And then time lock dot revoke role, revoke the admin role from user. So the user will no longer be the admin. And then we'll say vm.stop prank this. And then we just need a new box. Box equals new box. And now we're going to transfer ownership of the box to the time lock. And the time lock is owned by the DAO. So we're going to say box.transfer ownership to address time lock. So transfer ownership. A common misconception here is, oh, shouldn't we transfer to the DAO? No, we should transfer to the time lock. So the time lock owns the DAO. So the time lock owns the DAO and the DAO owns the time lock. It's kind of this weird two-way relationship, but it's the time lock that gets the ultimate say on where stuff goes. So we transfer it to the DAO. And so we can even do a quick test. Function test can't update box without governance. Public. We'll say vm.expect revert box.store 1 like this. Since our box has a store function that's only owner, the owner is now the time lock / the DAO. Oops. If I try to run this test, right, forge test-m, paste this in, this should pass because you can't update the box unless it's through governance. And this will also be our sanity check to make sure all of our code is compiling, which it is. Okay, great. Let's keep going. So now let's make a giant function test governance updates box public. And this will show you the exact process from a code standpoint of how one of these DAOs actually work. So first, let's get started. UN256 value to store is going to be 888. Boom. So we're going to update our box, right? This box here, we're going to update this new number to 888. Okay. Let's come up with a proposal, right? Remember, if we show up my governor, we click into governor, and we click into governor function propose right here. First thing we need to do to kick off anything is propose something. Hey, we are going to propose that box updates the stored value to 888. So we're going to need to have all this stuff in here. Targets, values, call datas, descriptions. So let's start with description because that's simplest, right? String, memory, description equals store 1 in box. That's it. That's our description. Pretty easy, right? What else do we need? Okay, we're going to need some call datas. Oh, well, we know what call datas are. That's that function selector and all that other stuff that we learned in that NFT one, right? So we can say bytes memory. So if you go back to the Foundry NFT F23, we go to SRC, sublesson, we can remember, oh, wait, we can call anything that we want, right? And all we got to do is encode stuff, right? Like abi.encode with signature or encode with selector or whatever we want to do here. So we can actually say, oh, okay, so this allows us to make any function call that we want. So we'll encode it by saying encoded function call equals, well, what do we want to call? Well, we want to call this store function. So we know the function signature of store is going to be store uint256. So we can say abi.encode with signature. We're going to call the store function like this. And then what else do we need? Well, we need the value like this, and that's it. Cool. Let me toggle the word wrap here. Cool. So we have the encoded function call. So we have the call datas that we need to call it. Okay, great. What do we need next? And we're going kind of in this reverse order. Values. Well, we don't really care to send any value, right? So let's even just go to the top here. We'll make a uint256 array values. It'll start off as blank. We'll just say values.push 0. Cool. We'll just have it be empty. We're not going to send any ETH. And then the final thing we need is targets. So we want to call this on the box contract, right? Oh, and actually, call data is also an array. So we're going to do a couple things. We're going to do values, call datas, and targets. Targets, right? So the call data is a uint256. No, call data is a bytes array. And targets is an address array. So we're going to say values.push 0, call datas.push, that encoded function call that we just made, and then targets.push, the address of the box, right? So now we have all that. Now we can finally call our proposed function. And what does this proposed function return? It returns this uint256 proposal ID, and we need that to keep going. So first thing we're going to do is propose to the DAO. Propose to the DAO. So say uint256 proposal ID equals governor.propose the targets, values, call datas, and description. Boom. And we get our proposal ID just like that. Now we can even view the state of this proposal now, right? Because we can call that state function. So we can do even like a little console.log proposal state. We can call a state function like this. Actually, GitHub Copilot has this right, except for we want to turn this into the uint256 version. So we'll say uint256 governor.state proposal ID like this. And if we look up function state, we'll find this. There's like a million of these. In our governor.sol, it returns this proposal state, which if we control or command click on that, we can see all the different states it can have. Pending, active, canceled, defeated, succeeded, queued, expired, executed. So pending obviously is going to be 0. Active is obviously going to be 1. Canceled is going to be 2, etc. Right? And of course, we're going to need to import console from test. Okay, cool. So this should return what? Should return pending. It should return a 0. And it hasn't started yet. It's not active because there's a delay, right? So we want to actually update our fake blockchain to move past that. So we'll just do vm.warp. We'll use these cheat codes, remember? Block.timestamp plus, and then we'll just do voting delay, uint6 public constant voting delay equals 1. This is how many blocks till a vote is active, right? And from our wizard, we just left this as 1. Oh, well, if we go back to governor, we just left our voting delay as 1. So this voting delay is 1. So plus voting delay. And then actually we'll do voting delay plus 1. And then we'll also do roll to increase the time as well. vm.warp, or excuse me, to increase the number, block.number plus voting delay plus 1. Now, if you view the state, it should be active. So now it'll be active. Cool. 2, after a proposal starts, because we've proposed enough time has passed, we now can actually start voting on something. So I'm going to do this cast vote function, but I'm going to do cast vote with reason because I like cast voting with a reason. So we're going to do string memory reason equals, because blue frog is cool. That's going to be my reason. That's why I'm going to vote for something, because blue frog is cool. In order to vote, we're going to need to call this cast vote function. And if we go to governor, we'll look for the function vote, or excuse me, cast. If we go in our search bar, we can look for function cast vote. There's a whole bunch of cast votes. We can see in here, we need to pass a proposal ID and support. How do we know support works? Well, let's look at this cast vote internal function. This cast vote internal function down here, support count vote. We got to look at this count vote function. So let's look for function count vote. Okay, this is the abstract implementation. We don't want governor compatibility Bravo. We want governor counting simple because that's what we're using. Okay, support, how does support work? Aha, okay. So there's this vote type struct that it's checking for. Let's go to the vote type. Okay, against, for, abstain. So against is going to be 0. For is going to be 1. And abstain is going to be 2. So what do I want to do? I want to write vote for. So we're going to do 1. So we're going to say we have our reason. Uint 8 vote way equals 1, which means I'm voting for, voting yes, if you will. And now let's do our vm.prank, our user or our voter, and we'll do governor.cast vote with reason, proposal, ID, vote way, and reason. Reason. All right, cool. Now that we've voted, let's speed up this voting period because everyone voted because we're the only voter. Let's speed up this voting period. And we set the voting period automatically. If we go back to our my governor, right? Voting period was set to 1 week. In here, this number represents 1 week. So we're going to speed up this voting period. I'm going to copy this number. Scroll up to the top. We'll do uint 256 public constant. Excuse me. Voting period equals this. Oh, and this should have a semicolon. Voting period. We're going to speed through the voting period. I'm going to just copy these. Change this to voting period. Voting period. Now that we've voted and the voting period is done, what do we do? Well, we actually need to queue the TX before we can actually execute. So we have to queue it first. So there's a queuing process. So on our my governor, there's a function queue, and a whole bunch of them have this. Let me open this up. Function queue. On this governor time lock controller, there's this queuing bit because a queue means it's passed, but we have to wait to queue it up. We just pass the same bits that we originally did for propose. So we're going to go back here. We'll say the only difference is we need to hash the description first. So we'll say bytes 32 description hash equals get check 256 abi.encode packed description. Now we can call governor.queue proposal ID. Excuse me, this is not right. Governor.queue targets. We're gonna pass the same values that we proposed with, so that we guarantee it's the same proposal. So targets, values, function, call datas, and description hash. Oh, we don't need that 0. We're gonna queue it. And then we're going to finally wait this min delay, which we said, hey, after a vote passes, we need to wait this min delay before we can execute. So I'm going to copy this again, paste it here. Instead of voting period, this is going to be min delay. And then finally, we can execute. So we'll do governor.execute. It's going to be the same as what we did to queue it up. I even just copy this whole thing, paste it here. Targets, values, call data is description hash. Let me spell this right. And now finally, we can do assert box dot get number equals the value that we stored. Boom. We can even do like a console.log, box value, box.get number. Okay. Copy this. Open our terminal. Clear. Forge. Test. -m. Paste. -vv. So we can see the console.logs. Pull it up. Is this what we've been waiting for? No, we ran into an issue. We see these two logs. Proposal state is 0. We're getting vote currently not active. So let's add a couple more V's so we can see where it failed. It looks like it got to the cast vote with reason and it failed. So let's go to our test. So it looks like it proposed okay. It looks like this failed. So it says it's currently not active. So did we mess up our voting delay? Ah, it's because I did warp for both. This should be vm.roll. And let's see, oh, we messed that up for all of them. Let's fix this. Roll. Okay, cool. Let's clear. Let's run it again. Pull this up. Oh my goodness, it passed. And we can see in the logs, proposal state was 0. We waited and then it became inactive. And then finally, after we got through all the different states, we finally were able to update the box. I know we kind of sped through this section, but like I said, at this point, you're becoming a pretty sophisticated smart contract engineer. And I really wanted to show you the process of voting of a typical DAO from today, and for you to see it from the coding side as well. Now, if you want to go further with this, I highly recommend you look into some of the different methodologies and some of the newer methodologies that researchers are coming out with for people to actually do votes. Because like I said, plutocracy is not the best. So if you want to go farther, try experimenting with other ways to build DAOs. Maybe flesh out your own DAO. Maybe deploy a DAO. Do whatever you want to do here. But in any case, you should be incredibly proud of yourself because you got through the hardest lesson of this whole course already, which was the stablecoin one. And then you just learned this incredibly powerful advanced course in how DAOs actually work. Students, we're almost at our end. There is one more lesson for us to do, and it's our smart contract and security auditing for developers. Do not leave this course without watching this. I want you to have at least the fundamental knowledge of where you should look for security help, what you should have in mind for security, especially now that you have the ability to go out and deploy some amazing contracts. I'm not going to teach you how to audit step by step here, right? But I am going to teach you, here's what you should be looking for in an auditor. Here's how you can begin to start thinking about security. And I am working on some security and auditing education material as well to make those of you who do want to go down that path successful. So give yourself a pat on the back, do a little dance, do a little celebration, get some ice cream, and I'll see you in the next one. And then I will release you to the world. So pause the video and I'll see you soon. And as a special piece of bonus content, we have Harrison here to give us some tips on gas optimizations. So enjoy.
Hey guys, I'm Harrison Ledio, and I'm the CTO and co-founder of PopPunk LLC, where we're building Gaslight GG. Gaslight GG is a audit firm, but we focus specifically on gas optimization for protocols to ensure that your gas costs are as low as possible. In addition, we're happy to announce that we're now building hyper-optimized public goods tools for EVM developers to make sure that everyone has access to just the best and the cheapest contracts. So Patrick invited me on here to show an example of some common ways that you might be using too much gas in your smart contracts without really noticing. So I have a quick example here. We're going to look at an airdrop contract. This is a super basic airdrop contract, which I'm calling airdrop bad or bad airdrop. Very simple. We have a token. We're using a counter to iterate and count the number of transfers. So as you see in the constructor, we set the token here, and then we have our airdrop function. So we have two parameters for this function. The first one is a memory array of addresses, which is the recipients, and then we have a memory array of UN256s for the amounts. The first thing we're doing is we're checking to make sure that the amounts match, otherwise we're going to revert. The next thing here, which is really common, is making sure that you're batching your actions. So if we see in this case, we have to traverse through the entire input argument array a full time just so we can transfer the number of tokens from the message.sender to the contract. So let's say there's 50 amounts, we'd have to do 50 separate transfer froms. Definitely not ideal. And then lastly here, we have a super basic loop where we're just iterating through the array and we are transferring the tokens from the contract to the user with the respected amounts here. Lastly, we can see that we're iterating this counter every single time in the array, or every time in the loop, yeah. So keep that in mind. So now if we look at a more ideal example of this, the first thing that you're going to notice is we're using a mutable for the token. A mutable is good if you're obviously never going to change something because we set this value in the constructor and it'll be included in the contract deployed bytecode, which is cheaper to read from every time. If we look now here, we've changed our arguments for our function to call data and we've added a new one called total amount. This is done so we don't have to do 2 loops through the array, we can do 1. So if you see here, the first thing that we're doing is we're transferring this total amount from the message.sender to this contract. So that's going to cut a large amount of gas because we're only going to wind up looping 1 time. So if we see here, we've changed the way that we're going through the loop. Technically, we don't have to cache this array length because we're using call data. But if you do see here, it's the same thing. We're transferring tokens from this contract to the recipient. We're also using unchecked for our loop iterator because it's not going to overflow because the odds of someone doing an airdrop to more than the max UN256 of addresses is kind of crazy. And the final thing to look at here, we're using an unchecked block again, but rather than updating this state value of transfers every single time and paying that base gas cost each time, we can just update this amount at the end with the bulk length. So these are small things that you can think about when you're writing your smart contract to ensure that you're saving as much gas as possible. If we look at the results of this, the airdrop bad costs 1,094,690 gas. And the airdrop good costs 404,842 gas. So we've essentially saved 600,000 gas just by doing simple things. You know, it doesn't make the code unreadable, and you're just making sure that, you know, the end users of this will not have to spend a crazy amount of money. So I want to thank Patrick for having me on here. You can find me on Twitter at poppunkonchain. Or the business account is at poppunkllc. If you're a small protocol or a large protocol, feel free to reach out for gas audits, and pretty soon in the near future you'll be able to go to gaslight.gg and you'll be able to deploy super cheap, super gas optimized smart contracts, you know, through no code and just pressing 1 button. Thank you.
All right, welcome back to our last lesson of the course. I hope you're excited because I sure am. In this last lesson, we're going to give you just a teasing of smart contract security and auditing. This is especially for developers. We're not going to go over everything security. However, in here, I'm going to leave a ton of places where you can learn and grow, and absolutely be sure to sign up for web3education.dev because we're going to put a whole lot more security information in here as well. But we are going to give you the foundational information that you need to even begin to start thinking about where to go and how to work with security in the space. We have this repo, Denver Security, to talk a little bit more about security and how it works. But I want to give you all a couple of stats before we even jump into security to impress upon you why this is so important. This is probably the stat that's the most jarring to me. According to Chainalysis, as of last year, 2022, about $3.8 billion was stolen in crypto hacks. And about 3.1 billion of that 3.8 billion was specifically DeFi. And if we go to DeFi Llama, last year, DeFi had a total value locked of around 50 billion. So if we do the math there, 3.1 divided by 50, we're talking around 6% of all DeFi was hacked last year. That's like walking up to a bank and saying, hey, can I put my money in you? And the bank going, yeah, sure. Just a heads up, there's a 6% chance all your money will be gone next year. That is an insanely horrible statistic. And it's why we need to put so much more focus and so much more emphasis on security. There's a popular website called rect.news that has a leaderboard that if you go to, you can see a lot of the top biggest hacks, hugest hacks that ever existed went off of code that was unaudited, unreviewed by security professionals. Unaudited, unaudited, unaudited. NA, unaudited, 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 unaudited. Out of scope, unaudited, out of scope. And it is not acceptable. Some of these hacks were absolutely massive, losing over $500 million. So if you're a protocol, or if you developers go on to build protocols, here is what you want to think about. You can maybe spend $2 million of your budget on security or get hacked for $200 million. The spending money on security is a 99% reduction in costs. So if you approach security from a business perspective, it absolutely 100% makes sense for you to spend resources on security. So to kickstart this video, all of you protocol devs will probably want to get a smart contract security audit at some point, a security-focused code review before you launch your protocol. So let's start there. I've made a video recently on what a smart contract audit is and how to prepare for a smart contract audit that we're gonna watch first. Because even if you don't want to become a smart contract auditor yourself, you'll need to know what a smart contract audit is for when your protocol is going to go launch to mainnet. So let's start there. A smart contract audit is a time-boxed, security-based code review on your smart contract system. An auditor's goal is to find as many vulnerabilities as possible and educate the protocol on best practices and coding best practices moving forward. Auditors use a combination of manual review and automated tools to find these vulnerabilities. Now, why are these so important? Why is it critical that you get an audit before deploying your code base to a live blockchain? Well, for starters, there are entire websites dedicated to how many hacks happen. Last year, we saw the most value ever stolen from smart contracts, with almost $4 billion stolen. Due to the immutability of the blockchain, once a smart contract is deployed, you can't change it, so you better get it right. The blockchain is a permissionless adversarial environment, and your protocol needs to be prepared for malicious users. But even more so than that, an audit can improve your developers' team's understanding of code, improving their speed and effectiveness in implementing features moving forward. And it can teach your team the latest and greatest tooling in the space. Often, just one smart contract audit isn't even enough, and protocols go on a security journey that includes many audits and many different services like formal verification, competitive audits, and bug bounty programs. We'll break these down in a future video. There are a lot of companies that offer smart contract auditing services like Trail of Bits, Consensus Diligence, Open Zeppelin, Sigma Prime, Spearbit DAO, Mixbytes, Watchpug, Trust, and of course, Cypherin. Additionally, there's a lot of independent auditors that do great work as well. A typical audit looks like this: price and timeline. First, a protocol needs to reach out, and they can reach out before or after their code is actually finished. Ideally, they reach out sometime before their code is finished, so the auditors can have time to slot them in. Once they reach out, the protocol and auditors will discuss how long the audit will take based off of scope and code complexity. The scope of the audit is going to be the exact files and commit hash that's going to be audited. How long the audit usually depends on how many lines of code / complexity. You can see a very, very rough approximation of how long an audit takes on your screen now. Of course, this depends firm to firm, audit to audit, and tool to tool. So take these with a very large grain of salt. Additionally, it's this duration that sets the price. And same thing at the time of recording, prices range wildly depending on who's doing the audit, how many people are doing the audit, how complex the code is, and more. And these initial conversations are really just to get a ballpark estimate and slot you into the auditor's schedule. Commit hash, down payment, start date. Once you have a commit hash, you can finalize the start date and final price. The commit hash is the unique ID of the code base that you're working with, so the auditors can know exactly what code they're going to be looking at. Some auditors will ask for a down payment in order to schedule you in. Audit begins. The auditors will use every tool in their arsenal to find as many vulnerabilities in your code as possible. We'll give you some tricks in a minute to make this a successful step. Initial report. After the time period ends, the auditors will give you an initial report that looks something like this, with all their findings listed by severity, usually categorized into highs, mediums, lows, informational / non-critical, and gas efficiencies. High, mediums, and low represent the severity of impact and likelihood of each vulnerability. Informational, gas, and non-critical are findings to improve the efficiency of your code structure, readability, and best practice improvements that are not necessarily vulnerabilities, but more ways to improve your code. Mitigation begins. The protocols team will then have an agreed upon time to fix the vulnerabilities found in the initial audit report. Sometimes, depending on the severity of the findings, this might mean you have to start from scratch, but more times than not, you can just implement the recommendations the auditors give you. This is usually much shorter than the audit itself. Final report. After the protocol makes these changes, the audit team will do a final audit report exclusively on the fixes made to address the issues brought up in the initial report. Then, hopefully, the protocol and auditors have a great experience together and will work together in the future to keep Web3 secure. Now, there are a few key things that you can do to make sure your audit is successful as possible. To get the most out of your audit, you should have clear documentation, a robust test suite, ideally including fuzz or invariant tests. Code should be commented and readable. Modern best practices are followed. There should be an established communication channel between developers and auditors during the audit, and an initial video walkthrough of the code should be done before the audit starts. The most important part of the process is going to be during the audit. To get the best results, you want to think of you and your auditors working together as a team. One of the best ways to do this is to have a dedicated channel where auditors can ask questions to the developers. The developers will always and forever have more context over the code base than the auditors ever will, because they have spent so much more time working on the code base. And the more documentation, context, and information that you can give to the auditors, the better. This way, it can be easy for anybody to walk through the code and understand what it's supposed to do. In fact, 80% of all bugs are actually business logic implementation bugs. This means that these are bugs that have nothing to do with some weird coding error and are just somebody not knowing what the protocol should be doing. So it's vitally important that the auditors understand what the code should be doing. Having a modern test suite and tooling can also make auditors spend less time fidgeting with your tooling and more time finding issues. Post-audit. We highly encourage you to take the recommendations your auditors give you seriously. Additionally, after an audit, if you make a change to your code base, that new code is now unaudited code. It doesn't matter how small the change is. We've seen a ton of protocols saying, oh, I'll just slip in one line of code, and sure enough, that's the line of code that gets exploited. And often, depending on the seriousness of your protocol and how many users you want to use it, one audit might not even be enough. Working with multiple auditors and getting more eyes on your code will give you a better chance of finding more vulnerabilities. What an audit isn't. Now, here's the thing. An audit doesn't mean that your code is bug-free. An audit is a security journey between the protocol and the auditor to find as many bugs as possible and teach the protocol different methodologies to stay more secure in the future. Security is a continuous process that is always evolving. No matter how much experience someone has, people at all levels have missed vulnerabilities. On the unfortunate day that happens, be sure that you and your auditor can jump on a call quickly to try to remedy the situation, and maybe consider getting insurance for your protocol as well. So now, with that being said, now you have a good idea of what a smart contract audit entails and what to expect end to end. A smart contract audit is a security journey end to end, leveling up your protocol so that you can have all the best practices and security know-how to deploy your code to a live blockchain forever. And of course, if you're looking for an audit, be sure to reach out to the Cyphren team, link in the description. And as always, stay safe out there, and we'll see you next time. All right, great. Welcome back. So now that you know a little bit more about what a smart contract audit is, let's talk about the process that smart contract auditors and security professionals take and the tools that they use. Security is both for protocol developers and for auditors. You as a smart contract developer need to know all these tools and probably should use all these tools before you even go to audit. At the end of the day, it is you who is responsible for the code base that you launch. And additionally, you often can't just do security at the end. You have to have security built in from the architecture from day one. For example, if you build a car and the car is a total piece of garbage, and you say, hey, cool, it's time to race, you're probably just gonna have to start over, and it's not a very good use of time for you to even go to the audit. There are some tools like Solidity, which have opinionated security and code quality standard for Solidity smart contracts. And we showed you the simple security toolkit from Nascent XYZ for great places to read before you go to audit, and make sure you have checked off or you've looked at this doc to make sure you're even ready to go to audit. But anyways, let's talk about the audit process. So there is no silver bullet, but typically the smart contract audit process goes through a process of manual review and then using tools. And there are a ton of tools security professionals use to make sure code is secure. Now, manual review is probably one of the most important, if not the most important tool that we have in our toolbox. Manual review is literally going through the code line by line and going through the docs and making sure the code actually does what it's supposed to do. There's kind of a joke in the developer community where If you just read the documentation for 15 minutes, you'd be way better prepared to actually do code, but a lot of people don't do that. So step one on any audit is really getting some understanding of what the protocol should do. Most bugs are actually business logic issues. And the only way you'll know if business logic is wrong is if you understand what the protocol or the business should do. And repetition is the mother of skill. So the more you read code, the more you read docs, the more you do these audits, the better you'll get. For example, if we had a contract like this caught with test, we have this set number function. This code technically isn't wrong, right? It'll compile fine, it'll deploy fine, but maybe if we read the docs and we read that set number was supposed to set number to new number, we would then read this function and go, oh my gosh, you're setting it to new number +1. That's clearly wrong, right? And the only way we would have caught that bug is by understanding what the function should be doing. So that's manual review. Now let's talk about some of the other tools that we have in our toolbox here. The first line of defense is going to be test suites, which is why we spent so long in this course writing test suites. All the most popular frameworks out there have test suites. I don't really need to go over them because you have already done so. Static analysis. This is something we haven't gone over. Static analysis is going to be automatically checking code for issues without executing anything. Hence, the debugging is static. Most of these tools will sort of just dumbly look for keywords in specific orders. And AI is actually going to be an example of static analysis as well. And we'll show you an example of all of these once I get through this. Fuzz testing, we've gone over fuzz testing. It involves providing random data as inputs during testing. We have stateful fuzz testing, which we've definitely gone over in this course as well. Differential testing, which we aren't really going to go over, but it's a way to actually write the same code multiple times and compare the code against each other. But then finally, there's formal verification. Now, formal verification is a generic term for applying formal methods to verify the correctness of hardware or software. Applying FM means anything based off of mathematical proofs. In software, often used as a proof of correctness or proof of bug, or just mathematically prove that something in your code can happen. This can be a little bit confusing, obviously. But to me, the way that I generalize it is you basically take your Solidity function, you take your Solidity code and you convert it to math. And math can be solved. Math has right and wrong answers. 1 + 1 = 2, right? So we convert our Solidity code to math and then mathematically prove or disprove it. Symbolic execution is one of these formal verification, these formal methods. And symbolic execution involves converting our code to a mathematical expression. There's some tools here like Mat, Manticore, Z3, Certora. Even the Solidity compiler actually has a symbolic execution client. There is a fantastic article on HackMD by Paulina who goes over some of these different symbolic execution clients and compares them to each other. I left a link to this, of course, in the GitHub repo associated with this course. Symbolic execution is one of these tools that is the most time intensive. And a lot of protocols and a lot of audit firms don't even go down this route because even symbolic execution isn't a silver bullet. It's not a guarantee that some code has no bugs. It's not a guarantee code is bug-free. But especially if you have some incredibly math, computationally heavy process, symbolic execution or formal verification might be a good tool to use. AI tools. AI tools are a work in progress. Long story short, sometimes they're okay and sometimes they're absolutely terrible. All right, so now that we know some of these tools, let's actually see them in action. And I'm going to go kind of quick here, but what we could do is if we're in the GitHub repo associated with this course, we can actually download this Denver security repo. Now this does not have the -F23 at the end of it because this is a lesson that I've done in the past, but it is associated with this course. And what we'll do though is we'll just clone it. We're not going to build a project from scratch here. We're just going to look at some code ourselves. So we'll do git clone, paste it in, do code Denver security, and we'll open that up in a new tab here. And I want to just show you how bugs can be found with some of these different tools here. So in our SRC folder, we've got a couple of files here. We have caught with fuzz, caught with manual review, caught with slither, stateful fuzz, symbolic, caught with test, etc. Each of these has a bug in them where one of these methods was going to be how you catch it. Our first one, caught with manual review. We'll do a toggle word wrap. The way we can catch this bug is just with manual review, right? So we have this function, do math, and the comments or the docs here say dev adds 2 to number 2 add and returns it. We can then easily read the code and say, oh my goodness, we're only adding 1. Boom. That's an issue. That's a bug. That's something that we would want to fix. That's how we would catch this one. Next, caught with test.sol. This is the one that we saw in the presentation that we gave. Set number should set the number. A unit test would easily catch that this was wrong. All right, what's next? Static analysis or slither. Now, this is something we haven't really gone over, but one of the most prevalent hacks in this industry is going to be something called a reentrancy attack. And you can read more about it in the Solidity by example, reentrancy. I've left a link to this, of course, in the GitHub repo associated with this course. But there are actually tools that will automatically check for stuff like this. If I pull up my terminal and I use this tool Slither, I've already gotten installed. You can go ahead and check out the install instructions yourself. But if I run slither dot, it'll automatically compile my code base. And then it'll give this massive printout of a ton of the issues that it found. And right at the top, right in red, it can see, hey, there's a withdraw issue. There's a reentrancy issue with your withdraw function. And then obviously we could go back, update it, rerun slither, and this would go away. So a lot of these issues have tools that you can just run and it'll automatically detect. So Slither is one of these tools that I think everyone should run on their code base before going to audit. What's next? We've caught with fuzz, which we know what fuzz is. We learned about fuzzing. We have this massive function. We see this here say should never return 0. So there's probably a fuzz test. So if we look in our fuzz tests, we actually smartly wrote a test fuzz here where we say, hey, the return number from that function should never be 0. We can then grab that, forge test -mt. What's it called? Test fuzz. And we see we get a failing test here. We see we found that if it passes 1, 2, 6, 5, it actually will fail. Come back to our test here. And we can see there's a conditional if my number equals 1265. 1265 modular 1265 is going to be 0 plus 1 minus 1 times 1 is 1, which means it returns 0. And we don't want this to return 0, which means we break our invariant. If we call change value with 0, it'll set my value to 0 up here. And then we can call do more math again with 0. We're going to get 0 divided by 1 plus 0, return 0, and boom. This will break as well. And then finally, we have symbolic here, where we can actually just use the Solidity compiler to do symbolic execution. We have these two functions, function 1 symbolic, where we have this revert in here. This is going to be the bug. In Solidity, we can add asserts to our code base, and we'll go over a video that explains this more in depth to tell our Solidity compiler, hey, this should not hit and this should hit. This conditional should not be hit, this one should hit. In Foundry, in our foundry.toml, we can add information in here to send to the Solidity compiler. We're going to tell our Solidity compiler to use the CHC model checker, time out of 1000, and to look for those assert keywords. And if we just run forge build or forge build -- force to force it to rebuild, it'll compile and it'll give us this output here saying, warning, CHC assertion violation happens here. Meaning it found an issue, it found an input such that this assert line hit. So if we pull up our terminal, we can scroll down, we can see exactly what the input is. 8088 is the input that will allow that to hit. If we look, 8088 divided by 4 does indeed meet this criteria, so it would go ahead and revert here. So those are some of the tools we have in our toolbox. We'll go over symbolic execution a little bit more, but let's wrap this lesson up. So to talk to us more about the process of manual reviewing, we have legendary Ethereum smart contract researcher Tincho to walk us through his process in a real process of him going through ENS. He did an audit on ENS just for kicks and ended up getting paid out $100,000 for finding a critical vulnerability. So let's learn from legendary manual reviewer, Tincho. This is Tincho, Ethereum security researcher, previous lead auditor at OpenZeppelin, and creator of Damn Vulnerable DeFi. And today we have the pleasure of talking with Tincho, going over his auditing process so that you can learn how to make damn unvulnerable DeFi. To do this, we're going to be doing a live mock audit of the Ethereum name service GitHub, seeing exactly some of the tools and techniques that Tincho would use to audit this.
I don't have a super formal auditing process. I really think that everybody will find their own ways. I will just show you briefly some things that I do today.
Link to the full interview in the description. Let's get froggy.
So this is a repository for ENS. The first thing that I would do is obviously go to a repository. You would clone the repository to my local environment. But if you're like very unfamiliar, you should probably go to the documentation, at least, I don't know, read the introduction.
Now, he says there's no formal audit process, but this sounds like a good step one. Download the code, read the documentation. Read the fucking documentation.
Here we have the architecture. It's telling us like already some keywords that we will need to understand at some point, such as what a registry is, what a resolver is. Already I will get familiar with this. Probably these are contracts that I'm about to see in the code, and so on and so forth. One thing that you can do also after reading some documentation is looking at audit reports. If we go to the actual code, we will realize that there are lots of things.
Wait a minute. What the heck is that logo? What wonky text editor is Tincho using? That, my friends, would be VS Codium. It's different from VS Code. VS Code is a product owned by Microsoft that actually sends a lot of your usage information over to Microsoft. VS Codium doesn't do this.
They have removed, I think, telemetry and some things related to Microsoft.
Tincho said he's just been trying it out recently, but maybe it's a security alpha leak.
So multiple contracts in here. Already we see lots of folders. It's using Hardhat from what I can tell. These days I like projects that use Foundry more than those that use Hardhat. So in that case, what I would do is I created another folder in which I have a Foundry local setup.
Why do you like Foundry better? Why do you make this Foundry local setup?
It's faster, and I can write quick tests only using Solidity. So I will do whatever thing that I want to do here, but just an easy way to have something quick and dirty to test things quickly.
Bring and use the tools that you're most familiar and best with. I think that's super important. And don't be afraid to bring your disgustingly horrible, dirty tests.
But anyway, already we saw that it's quite complex. So what I would do in this case is there is a command line utility that I would use, which is called CLOC. CLOC will help you count lines of code. And so I would use CLOC. It would give me a nice output that you can actually parse to a CSV. And instead of doing this here, what I would usually do is I would move that to a spreadsheet that I have the scope for ENS, right? All these files are now ordered here. And now I can have a better view in terms of how many files do I have, how complex they might be. So apparently I have 59 files, and now I know the name wrapper will be one of the most complex contracts, perhaps, right? Because it has more than 700 lines of code. Another approach to do this scoping phase, you can actually use this tool by consensus, which is called Solidity metric. So you can run it on a project and it will actually give you a nice report of the code base and its level of complexity. And then I will have a column stating where the thing that I'm doing is not started, it's in progress, or it's done.
So this is his next step. He either uses Solidity metrics or CLOC, ranks all the contracts that he needs to audit based on complexity, and starts going through it, moving contracts from not started to in progress to done. A very organized approach.
When you do this alone, it might seem silly, but when you work in teams, it's quite important. As the audit progresses, I will be less and less focused on this file, because probably this is super complex and will be related to either, but most of all, it's very useful, at least for me, at the beginning of the audit, just to understand what am I looking at. Once I have this table, I usually start with the little Legos, and then I go move up in complexity. So in this case, I will probably, start with the ERC20 recoverable contract. Here it is, and it's quite short. Say, okay, it's ownable, inheriting from OpenZeppelin. As an auditor, probably I can take that for granted, which is out of scope, and I will assume that's working correctly. And it has a single function to recover funds. Okay, it has access control, so this is probably fine, as long as they are handling access and controls in the right way. This is fine. And it's actually doing this, right?
So we start with the small little building blocks, or Legos, as Tincho said. And now you're going to see Tincho's brain start switching into, how can I break this?
As an auditor, you might start wondering where this is good for any token out there, right? Where it's possible to actually execute a transfer on any address that the owner passes here, and where that could be problematic for well-behaved ERC20 tokens. And if you're familiar with USDT, for example, that could be problematic in this.
Now we're seeing him drawing on his expertise, knowing that USDT is a weird token. USDT actually doesn't return a Boolean on its transfer funds, whereas a lot of other tokens actually do. What the fuck, USDT?
When you see that only owner function, do you think, okay, is this a DAO? Is there a single person who controls? What are your thoughts?
At least at the beginning, I wouldn't worry about it too much. At some point, I will read documentation about roles of this. But yeah, at some point, I should probably understand at some point who's the actual owner. Okay, let's say that you think that this is okay. So what I would do usually is I would take notes in the code, right? So in this case, I would say like access control, okay, for example, just to have a note saying that I was here. Or you can have a question like Patrick said, is this governance, right? And let's say this was an issue, so I would do this. Shouldn't be, I don't know, let's say shouldn't be owner. Another thing that I do to take notes is actually have notes files in the same place. Very raw notes, having a file where I can quickly dump ideas that I have. At some point, things don't go well. I would have an issues list here, and I will start listing, I don't know, in line, blah, 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 of file, blah, 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 list issues.
Take notes in the code in a notes file somewhere. Just have a place where you can dump thoughts. Maybe you can even use a note-taking plugin.
I don't use any plugins. That's because I don't like having the UI clutter too much with stuff.
Yeah, a note-taking extension was a dumb idea.
And one thing that you have to be careful when you start with the very little things, so it's very easy to go deep into the rabbit hole of the single thing that you are trying to audit, is that, for example, I have very little knowledge of DNS. I'm not like super familiar with and I got like very like down into DNS because I was just paying attention to this single resolver. And that led me to realize that after, 2 days, I was growing familiar with DNS, but I was losing the big picture of actually, hey, I'm actually auditing ENS. So it's very easy to go deep into the rabbit hole of the single thing that you're trying to audit.
Remember to jump out of the rabbit holes.
Perfect. So at some points during the audit, you will realize that you might need to test things. So in this case, I saw these two functions. One is going from a bytes thing, returning an address, and the other is doing the other way around. You might say it's okay, but if you're lazy, you can actually use Foundry to help you in that. So what I did in this case, I used my very handy, hacky Foundry repo that I have in here, and I actually copied these two functions to a contract. Like I just took them, not even trying to do fancy imports or whatever, just raw copying and pasting them here. And I did a quick test, a fast test in which I provide an address. I pass that address to this first function, and the result of that, I pass it to the other function. And I want to make sure that I always get the same address as a result.
A lot of times, yes, you're going to write code and not just do manual reviews. Tincho here wrote what's called a fuzz test, which you should absolutely smash that like button because we're going to have a video on that sometime in the future. Use your tools to validate findings that you have an inkling are wrong.
In the cases where I have to set up more complex stuff, perhaps having a separate folder with a single project is not that convenient because I would need to set up the whole ENS system, and that wouldn't be that convenient. So in those cases, I would go to the actual testing environment of the project.
If you're doing a private audit, how important is the process of talking and interacting and keeping communications with the client open?
I would say it's almost fundamental. Usually developers will have much more context than you as an auditor on what the system is intending to do. So you can spend a whole week trying to figure out on your own where this modifier should be in this function or not. But if you actually send a question to the client and tell them, hey, should this be here or not? And they will tell you, yes, it should be here. You can see it in test, blah, blah, blah. You can see them as companions during the audit, and you should rely on them.
You can rely on the client. AO protocol. Is your code good? You think so? Hell yeah. My work is done.
Having said that, it's also important not to trust too much. At the end of the day, they are trusting you as the expert. So in that sense, I would advise, okay, keep the clients at hand, ask questions, but also be detached enough.
Since they built the code, they have spent more time thinking about the code and looking at the code than you ever will. Ask them questions and don't be afraid to ask questions.
I guess at this point, what's the next step? Are we wrapping up now? Are we writing the report up? What do we do next?
The thing is, I always get the feeling that you can be looking at a system forever. There's always one additional line that you can check. There's always one additional attack that you can think of, one additional potential code smell, vulnerability, and everything. So what I do is I time bound myself to have a certain level of confidence when you're shipping the report that you did your best and you thought of every single possible attack or vulnerability that you could think of in that limited amount of time.
Time bound yourself.
When you're going through this code, how are you thinking of different attacks? Like when you're looking at a piece of code, how do you get that context of what different types of attacks to think of?
Yeah, I don't have a checklist. Very difficult to translate experience in doing it. Have this adversarial mindset, or try to at least. There's lots of knowledge that can come from every single day reading vulnerability reports, every single day reading responsible disclosures that are published, reading all these reports. I read newsletters. Like, I don't know, I have this constant influx of security-related information to Solidity that little by little, I think you start growing the intuitions, the experience that actually help you identify quickly things that can happen in smart contracts. And always remember that you can miss things. There's no perfect auditor. I think that everybody has audited sufficient enough and complex enough systems, they have all missed issues. And it's okay. Security is a thing that we have to approach from many different angles, and auditing is just one thing that must be done, but it's not the only one. Knowing that you're doing your best, knowing that you're putting your best effort, every day growing your skills, learning, grows an intuition and experience in you. Something that I always say is to audit, to me, is 50% finding vulnerabilities and 50% delivering readable report. Once the client starts fixing the issues, they will send you the fixes for the issues. And what you have to do at that point is actually review the fixes and make sure that not only the vulnerability that you highlighted in the report is fixed, but actually this have been introduced by the fix.
And then you wrap up your whole auditing process with writing a very good report, and take the time to do so. Once you give them the report, they will go ahead and fix the issues, come back, say, hey, we fixed them. And then it's your job to make sure that they fix the issues and they didn't reintroduce new bugs.
Let's say you give your audit report, you've done your time box, you've done as much as you can, you think you did a good job. 4 months goes by. Oh my God, $100 million hack. They've ended up on Wrecked. What do you do? What happens?
Let me approach it slowly, okay? So I will first say, I have always been of the idea a security code review should be valuable enough beyond the fact that I find or not find a critical issue. So I should be able to provide value to whoever is working with me, to whoever is trusting me, beyond the fact that I did or did not find a critical issue. Obviously, the less critical issues that you miss, the better, the safer, and perhaps they miss something. And that can happen and has happened and will continue to happen. But it's naive to think, in my opinion, that just because an auditor missed something, the whole blame of thing is on the audit.
This, I think, is a really important final thought. You as an auditor, it is not solely your job to make sure their code is bug-free. You share that responsibility with the client. However, this doesn't give you free range to suck at your job. People will notice.
Tincho, thank you so much for being here. Thank you for all you've done for the Web3 community, and I'm sure everyone will get a lot from this.
Okay, Patrick, thank you for inviting me. Bye. Bye.
So to understand symbolic execution a little bit more, we've got some members from the Trail of Bits team to teach us about symbolic execution and formal verification. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. Symbolic execution is one technique used for formal verification. Symbolic execution explores different paths in a program, creating a mathematical representation for each path, or more plainly, converting your code to a set of mathematical expressions. Is this the silver bullet for your auditing journey? Let's get froggy. I had the absolute pleasure of interviewing Trail of Bits head of engineering Jocelyn and security engineer from Trail of Bits as well, Troy, about fuzzing, testing methodologies, and importantly, formal verification. I have links to the full interviews with both of them in the description. And in this video, we're going to summarize a lot of that and focus on what formal verification and symbolic execution actually are. But to do that, we need a quick refresher on some of the testing methodologies that we use in Web3. If you haven't seen my invariant testing video, be sure to watch that first before coming here. And to really understand this, you do need at least a high-level understanding of Solidity as well.
What tools do we have in our toolbox to have high assurance about our program?
Layer 1, the unit test.
Obviously, you have unit tests, which is you do a very specific thing like this function does this. And then you start looking at things like test code coverage, like statement and branch coverage. And I think that's kind of the bare minimum.
The absolute bare minimum in security is a unit test. For example, if this is our Solidity and we have a set number function, which should set our number variable to whatever new number is, a unit test would be able to catch this. And if we're using Foundry, we could get an output that looks like this. Some assertion failed, and we can go see our test and see that when we call set number to my number, we assert that we get what we want. And if that breaks, cool. Our unit tests have saved us. Foundry, Hardhat, Apeworks, Truffle, Brownie, and all the most popular frameworks have unit tests built in. Layer 2, the fuzz test.
Fuzzing is where you take random inputs and run them through your program. So you have to define things in your code that you always want to hold true.
And fuzz testing is the new bare minimum for Web3 security, because I decree. And as Troy said, you need to understand the property or invariant of your system to do fuzzing. Once you have your property defined, you throw random data at your system in order to break that property. If you find something that breaks it, you know you have an edge case that you need to refactor your code to handle. For example, if I have a function like do more math, and I know that this function should never return 0, I can throw a whole bunch of random numbers in here to try to get it to return 0. I can have a fuzz test that looks like this, which passes in a whole bunch of random numbers and tries to assert that we never get 0. And we can see from our fuzz test, it was able to pick a random number in order to break our invariant or property. Now, like I said, we recently did a video on fuzz testing or invariant testing, and I highly recommend everybody watch that video because I decree it. Foundry, Echidna, and Consensus Diligence Fuzzer are some popular fuzz testing tools. Okay, what's next? Layer 3, static analysis.
So the things that we've been discussing, unit testing and fuzz testing, are dynamic testing, which dynamic just means like you're actually doing something.
Dynamic analysis is when we run or we execute our code. In unit and fuzz tests, we do exactly this. We are running our code to try to break it. In static analysis, we just look at our code or have some tool look at our code. For example, this code here has a classic reentrancy vulnerability in our withdrawal function. If we run a static analysis tool like Slither, it'll automatically detect, hey, you have a reentrancy vulnerability. And this is great for very quickly picking out very specific parts of your code that are known to be bad practice. Some popular tools for static analysis are going to be Slither, created by the Trail of Bits team, and even the Solidity compiler could be considered a static analysis tool. So now that we have a little bit of a backstory on some of the popular layers of testing and keeping ourselves secure, let's jump into formal verification and symbolic execution now. Layer 4, formal verification.
So on a high level, formal verification is going to be the act of proving or disproving a given property of the system. This is usually done through a mathematical model of the system and the property.
There's that word again, property. You're seeing that almost no matter what you're doing in your testing, you need to understand the properties of your system. And right there, Jocelyn gave us some of the keys between fuzz testing and formal verification. Fuzz testing tries to break properties by throwing random data at your system, whereas formal verification tries to break properties using mathematical proofs. And there are many different ways to do formal verification, such as symbolic execution and abstract interpretation. For this video, we're going to focus on symbolic execution, as that's one of the most popular ways currently done in Web3.
Symbolic execution is then one of the techniques that you can use to do formal verification. Symbolic execution on a high level is going to be a technique where you are going to have your program and you are going to try to explore the different paths of the program. For every execution path, you are going to create a mathematical representation.
Additionally, if you want to learn more about symbolic execution outside of Web3, I left a link in the description to an MIT OpenCourseware video, which does a great rundown of symbolic execution. Now, let's look at Jocelyn's example of using formal verification and symbolic execution. Let's say this is our function that we want to do formal verification on, and we're going to do symbolic execution to do formal verification. Well, let's go back to what formal verification actually is. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. So the first thing we need to do is figure out what we want to prove or disprove. For our demo, we should say our invariant is this should never revert. And that's what we're going to try to prove or disprove. Now, this might seem like a silly example, but you can imagine that this was a function called withdraw money, and you want users to always be able to get their money out. which would seem like a much less silly example. Symbolic execution is going to be creating a mathematical formula for this function f from our code. We're going to convert this function to a mathematical/logical representation of every execution path from our code. Once we have a set of math functions, we can push those into a solver, which will tell us if a property is true or false, or if our invariant is true or false. When we talk about the different paths of our function, we can imagine, okay, one path that our function can take is going to be a plus 1 being returned. That's going to be one of our paths. But we can also imagine that a plus 1 is actually going to overflow and therefore revert. If we pass in the maximum uint256, a plus 1 would revert. So that would be a second path that our function could take. And a symbolic execution tool would find this second path for us programmatically. And then of course, convert these to a set of mathematical expressions. This set of mathematical expressions might look something like this: A and also not A. Imagine if you ask somebody, can this set of mathematical expressions be true at the same time? The answer would obviously be no. It is impossible for both A to be true and A to be false. This is what our solver is going to figure out for us, but with much more complicated expressions than this. In our example, the solver is known as a SAT solver or an SMT solver. And there are many different types of solvers, but I'm not going to go too deep into that right now. So running our symbolic execution tool, we would see two paths. Our first path going to be if we give it the maximum size of a uint256, we try add 1 to it, the function will revert. Solidity doesn't allow you to add 1 to the maximum size of a uint256. The other path is anything lower than the max size of a uint256. We'll just add plus 1 and then return. So those are going to be our two paths. Path 1, a is not 2 raised to the 256 minus 1, and then a returns normally, and a is 2 raised to the 256, and it reverts. However, instead of A, B, C, not A, etc., our symbolic execution tool will give us an output that might look something like this. Now, what you're seeing on screen is an SMT lib language. And it's a language specifically made for working with these solvers to solve our mathematical representations of our code. I'm not going to go over too deeply what this is doing, but you can consider this just a list of Boolean expressions, kind of like A and not A, and if A, therefore B, and A, B, and C, etc. Now, if you take this code and paste it into a tool like Z3 or run it locally on your machine, it'll give you an output that looks something like this: SAT and SAT. This first SAT is saying they were able to find an input for path 1, and they were able to find an input for path 2. They were able to satisfy the Booleans in those different paths. Since it was able to satisfy an input for path 2, and we know that path 2 reverts, we know that this invariant is now broken, because our invariant is it must never revert, and our mathematical representation said, hey, I've mathematically proven that there is a scenario where path 2 is executed and your function reverts. So SAT here means we mathematically proved that this invariant breaks. Now, I manually created this SMT lib list with the help of ChatGPT. However, symbolic execution tools like Manticore, HEVM, and even the Solidity SMT checker can give you this SMT output. But all those tools come with a Z3 built in, so they'll even just skip this step and just give you, hey, is my invariant broken or not? Even the Solidity compiler itself can do this entire process behind the scenes. Explore the paths, convert the paths to a set of Boolean, and check to see if those paths are reachable or not. Using the Sol compiler, we can run with model checker engine, and we can look for an overflow in small sol.sol. And if we run this, you'll see the Solidity compiler was able to do symbolic execution to find out, hey, if I add the maximum uint256 as an input to here, you're going to get an overflow, and that function is going to revert. Now, obviously, reverts are pretty easy to find, but we could even add assert a does not equal 1, rerun this, but instead of overflow, look for asserts, and we would see that, again, it was able to mathematically find an input to break our assert, or our invariant. It said if you add 0, you're going to get 1. Asserts are what you're going to use if you want to use more complicated and more specific symbolic execution, rather than just overflow or underflows. A tool like Manticore will also give you an output with the revert, as well as a much more hyper-specific list of SMT lib that it's inputting into its Z3 solver. So a lot of stuff just happened here. Let's recap. We built some Solidity, we understood our invariant, and the next two steps happened at the same time with Solc or Manticore. We used a symbolic execution tool like the built-in one to Solidity to create a set of Boolean expressions that represent every execution path of our code, and then we dumped them into a solver like Z3 to see if our property could be broken. Just by running this one function, Solidity was able to do all those steps behind the scenes for us. We go through a full walkthrough of this example with the interview with Jocelyn, so be sure to check that out as well if you want to learn more. And don't be afraid if this seems a little bit complicated. Be sure to ask questions, leave comments in the descriptions, and leave a like as well. And hopefully I'm going to clear this up for you.
Sometimes the solver might not be able to solve the equation too. Like if the equation is too complex, you usually provide a timeout to the solver just because, if you have to invert hash function, good luck to do that with the solver.
Well, so you're saying this isn't a silver bullet for auditing? Like any technology, even formal verification and symbolic execution, abstract interpretation, these are not a one-size-fits-all approach. Using symbolic execution can run into something called the path explosion problem, where there's too many paths for a computer to explore in a reasonable amount of time, and a solver would never be able to finish.
How practical is it to take all these steps? How hard is this to really do?
So there are a couple of things to consider. The first one is that this specific technique, symbolic execution, has a couple of limitations. As you're going to explore the different paths of the program, there is a problem which is called the path explosion problem, which is basically if you have so many paths to explore in the program, it's going to take forever. If you have an infinite loop, this technique requires significant effort to be used. You need to understand how they work, and you need to understand their limitation and how to help them. And also significant effort to be maintained. At the end of the day, I think what really matters are the properties. If you want to know if a bug can occur and if the property can be broken, you don't necessarily need formal method for that, and you can use a further, which is way easier to use and provide like kind of the same type of value. Something that is sometimes difficult for people is really to understand how to create this property and how to create invariant for themselves. If someone wants to learn a bit more, we have this website. It's called securetrack.com, where we go over a lot of guidance and best practices, and among other, we have tutorial on how to use Echidna, how to define invariant, how to think about properties.
There's a high skill requirement to using these tools effectively at the moment. People are working on making them easier and easier, like the built-in Solidity SMT checker. However, as Jocelyn's been saying, sometimes a sufficiently powerful fuzzer is all you need. And if you combine a fuzzer with a symbolic execution backend, the fuzzer can pick better random numbers based off of the symbolic execution. And maybe you can find all the answers you need without having to do a formal verification test suite. And the most important piece here is that even this isn't a guarantee your code is bug-free. All it does is mathematically prove your code does that one specific thing correctly. I'm hoping as AI takes off, doing a lot of this will become much easier. And I guess we'll have to see. But for now, hopefully you learned at least the basics of symbolic execution. If you'd like to learn more, leave a comment in the description. If you want to see more videos about formal verification, let me know. But the takeaway from this is that you should become a stateful fuzzing wizard. Thanks all for watching. Be absolutely sure to go watch the interview with Troy and Jocelyn, links in the description, and we'll see you next time. Now, for those of you who are looking to become security professionals, smart contract security wizards, there are a ton of resources you should absolutely check out. I've left a link, of course, in the GitHub repo associated with this course to this comprehensive list of known attack vectors and common anti-patterns. It's got a ton of different Solidity attack vectors that you should 100% know about. Additionally, if you want to learn more on doing security, there's a phenomenal game by a developer named Tincho called Damn Vulnerable DeFi, which is a way to learn offensive security of DeFi smart contracts in Ethereum. And they've got these amazing games that you can check out and play to learn security. Ethernaut is another game that is absolutely phenomenal that will help you to learn and understand Solidity and smart contract vulnerabilities. For those of you who are looking to become auditors, definitely be sure to check out Solidity, which is this amazing tool for you to check out audit reports from the top smart contract security professionals in the entire industry. Of course, be sure to check us out at Cyphren. We do smart contract security and auditing as well. If you are building a protocol yourself, definitely be sure to check us out for your next project, for your next protocol. For any and all of you, absolutely subscribe to web3education.dev. We have some amazing surprises coming for you in the next couple of months, and I don't want you to miss it. There's going to be some awesome opportunities for you to participate, learn, and grow in top security. So be sure to put your email in here. And this is really just the tip of the iceberg. There's so much more to go when it comes to security. We are working on more security-based education as well. So stay tuned for that. But the prerequisite for the security course is this monster Foundry course anyway. So you have already taken the first step to becoming a smart contract security badass as well. But all right, guess what? That's it for the security lesson. Congratulations. I and the Web3 community as a whole want to congratulate you for completing this absolutely monstrosity of a tutorial. You have done an amazing job to get this far and to watch me talking to you right now. And if you haven't finished the course, go back and finish it before coming here. We have learned so much on this journey. And I can say from the bottom of my soul that I am so glad to have you in the Web3 space, the smart contract space, the blockchain space, the cryptocurrency space. We are so excited that you're here. I'm really looking forward to seeing you in the Web3, in the blockchain community. Now, a lot of people ask, well, where do I go now? I have all this newfound knowledge. I'm armed with the intelligence of the Web3 developer space. Well, I've left some links in the GitHub repository to lend you to those next steps. But the biggest thing that you can do for yourself right now is go take what you've learned and apply it somewhere. This is going to be probably the most thorough course you will ever go through in this space. And you can go tutorial to tutorial and bootcamp to bootcamp all you want, but at some point you have to make that leap and you have to dive in. And that's where the majority of the growth is going to be anyways. So if you're here wondering where to go next, go join a hackathon. Go start jumping onto issues on GitHub repos. Go start applying for grants. Go start applying for jobs and say, I took Patrick's massive course, here's my GitHub repo. Work on a personal project. Work on somebody else's project. Take this knowledge and apply it. The challenges that you'll run into and the challenges that you'll face, really trying to do something without me hand-holding you, is where you're gonna learn 10 times as much as what you've learned here. I've walked you as deep down this rabbit hole as I can take you. Now it's up to you to go out and do something with it. So thank you everybody who helped me create this course. Thank you for taking this course. And I am so excited to see you in the community and see what you build and see what we can create with this technology.